Good morning, sir. You hear me?
Yes, I do. Can you hear me?
We can. You sound great. All right,
Woohoo!
let's move back to Lansdowne. He should be up now.
Okay, perfect.
are currently the only person in this conference.
But I will be talking about that. Yeah, so that's like
Okay, that's double check.
I am your microphone.
Hello? Hello?
Yep.
Are we, hey, Stefan, do you want to tell us when we're good? Is it 10 yet? 10 o'clock.
Mhm.
Are we good to start? Yeah. Okay. I assume all the cameras are rolling. I assume all the cameras are rolling. Welcome to IoT is a four-letter word. Just to give a bit of a background on the title here, there's a bit of a joke. What does the S stand for in IoT? It's security. I mean, that was a joke 20 years ago, but today we're all very secure and it's very mature. It's been a long journey, but here to lead us on the rest of our hike is Mr. Josef Holzmeier. Thank you.
Thanks a lot, Chris, for having me. First, I owe you one real big apology because due to excellent planning, I have to speak at 11:15 over at ELC, which means that I will, after my slot, be heading straight out to the next taxi and ride off. So I will be as interactive and welcoming during the next 25 minutes as I can be, but after that, I have to invite you everybody to heckle me either in the afternoon over at OSS or in the evening party, because I will be at the evening party. And with that, let's get going. So just really short about me, my name is Joseph. I currently serve as head of developer relations for Mandaro.io, which is an over-the-air solution. I've got a really strong background in the Yocto project, which actually put me on this stage in some way or the other. Huh? This full screen, fuller screen. How does this go? Actually, full screen. 3 dots. Woohoo! Make full screen. No. On my slides. Is that better? No. Okay. No, on that laptop. Yeah, I am a man. Oh, I apologize. I am a male, which means that I cannot multi-compute. Not at all. So I'm gonna skip the rest of my usual introduction. I'm really easy to approach. There's a mail address. There's Twitter. There's that guy with the ugly non-Garth Brooks hat running around everywhere, and that's me. This project will involve a number. Sorry. Why a hike? Whenever I do a real life project, I feel like it's a kind of a hike or a hill to climb until you have reached the top and you are able to finally ship it. And that hike usually will involve, like, if it's a real and non-trivial project, it might involve a number of bare metal or firmware components that might incorporate some RTOS. It usually, if it's a bigger one, will involve some Linux main system, a bigger one. But that's not the only thing you need. You actually need to be able to do something useful with it and not just boot it. And in order to provide value in your project, you usually need some application, middleware, connectivity, and OTA, which is my business. And all of these stages together often feel like the stages in a hike to me. You know, sometimes it's really easy. You're walking to some woods. Then on the other hand, it's a steep climb. There's rocks that come falling at you. And that's why I actually chose the title.
You are currently the only person in this conference.
lot of single points of failure, everybody is a build guru on their own. A possible solution is doing it. I know it's an ugly word, but let's do it the DevOps style. Persons A and B are not supposed to build anymore. They are just supposed to produce code. That's a big difference. They're supposed to only provide their sources to some pipeline that can pick them up and take care of the rest. Same goes for person C. Probably person C is more persons and produces more complex code, but nonetheless, those who do the code should not be responsible or not be responsible as part of the coding process to actually build it, because we should have one pipeline that is not only like the secret job security knowledge of one deployment master, but that is properly managed and understood, and that can take care of all that rest. And be the person or be the team, I call that ominous entity that takes care of all this, person D from here on. So what does a person D expect from such a pipeline? It should be composable, obviously, because it's not enough if it can only build A or B or C. No, it needs to be able to build everything, which can mean different architectures, different operating systems, different, maybe even not operating systems at all. If it can only do Linux, then it's not a fit. And it also needs to be able to actually build real applications, middleware. So it needs to be able to compose everything. It should be reproducible. So it's not a good pipeline if it yields a different result in the morning before coffee and in the afternoon after beer. That's a bad pipeline. We want the same result every time. And while we're at it, we also want the result to be compliant to not only regulatory, but also for the greater good. I mean, we are open source people. We know about the license, and we should make sure that we adhere to them. So the SBOMs are actually just like what should fall out for the more organizational side. But I feel that we as developers should care for compliance with the licenses that our other fellow developers chose, because they probably did not choose them lightly. And last but not least, once the pipeline has run, we actually want to know about the patch and security quality of the result. So we should have some form of checking, and I just picked CD checking as an example for this. And Chris already mentioned it, like a hike on, and I explained why the analogy was also like chosen by me. I tried to make it a talk about different stages, and when I looked at the requirements again, sorry folks, I realized it's gonna be a Yocto talk again. because when I looked at what I would expect from such a pipeline, the thing that I realized is that Yocto just ticks all of the boxes. I can do multi-config builds, which enables me to do builds for ARM, builds for PowerPC, builds for x86, and munch everything into one. It allows me to compose applications and infrastructure layers, like Mender as an example, but there's a lot of others. And it is world-class in reproducibility. We're close to 100% by now due to the heroic efforts of our maintainers. We have super license tracing and SBOM support by now. Heckle Kate for this. Yeah, and there's also a pretty neat CVE check that you can kick off by just saying, "Hey, yeah, I want CVE checking." And so, actually, this was the concept. Now we're just gonna look at the different stages that are involved. I said we're going to compose stuff, and how do we get an RTS or bare metal build inside? Obviously, I chose Zephyr as an example of such an RTOS. And surprise or not, the Zephyr project provides MetaZephyr, which enables Zephyr to be built through the Yocto pipeline. Again, heckle other people for details about me, not Kate, but Pidge. She's talking about that later. But it makes for a perfect first stage in a multi-config setup. And once that build is done, the firmware blob falls out and you can consume it in a later stage in the bigger build. So we've got the first composability. Second composability thing, you want your applications and your middleware to be provided as metal layers, hopefully. A lot of people do, we also do. And if you're doing such applications, please try to be a good citizen, which means your layer should be completely inert until you specifically enable it, because it's a real unpleasant experience if you try to build like a bare metal application or Zephyr and your fancy Linux application magic kicks in and just makes your build go boom. So it's not only about providing it, it's also about making sure we're all nice to each other. And you can see we're already quite a bit up on the hike because I feel we're on a good road. Now I need to grab a drink. It has been a lot of beers yesterday. And now that we've composed all those things, we should not be able to do it just once. We should be able to do it many, many times. And that is basically the final step. We pour everything into a configuration file. By the time I made that presentation, CAS was my choice of preference. Only 2 weeks ago, Alexander Kanabin merged mainstream support to Pocky to create and load a setup, which means this might change in the real near future. But essentially, this defines, and these are the layers that I want at these and these revisions. This is a machine I'm going to build for. This is the image I'm going to build for. These are the settings that I want. So essentially, the only thing you want is one CAS file. And to make it happy, or make it even prettier, it can be incorporated into a layer.
Joseph, I have a question.
Sure.
So Zephyr has many modules, as you're probably aware. Are those incorporated into this CAS file, or is that a separate thing that's handled within Meta Zephyr?
Modules as?
Different repositories, sort of like the repo tool has different Git repositories.
So, I mean, we are using that, and normally that is part of like the receipts, how they are. Yeah, carefully. So normally like the modules are part of like the receipts. So there's some magic in the BB classes of Zephyr to handle that in the layer. So it's not like, if you want to bring in new models or something that is not part of the Zephyr project itself, that might be a bit more work, but in general that it's working quite well. So for example, I'm using that with like things like OpenThread and so on, which is a extra module you need to enable, but that is very easy to do in the receipt for the Zephyr.
Okay. Thanks a lot, Chris. And thanks a lot for answering, Stefan. This is how a CAS file basically looks like. And yeah, we are over with the slides now. This is exactly how long I planned for it. Questions we have already started with, but I owe you a live demo. Or more, to be more precise, I owe you a proper link to what I've done, because this is not just making it work. Whatever I did, as promised, I put into a GitHub repo. So this is your blueprint if you ever want to do something like this. There is the CAS file. There is the machine configuration that made this work for an IMX7. There is the image that is able to pull in the Zephyr blob. There is the recipe that is able to pull in the first stage from a multi-config. If you ever want to do Zephyr into Yocto Linux, just take this and go wild. And to prove that it actually can build, I will take the question in only 1 second, because let me kick off the build as the final proof that it actually builds. This is just CAS build and the configuration file. It runs off, it pulls in all of the layers at specific revisions. And during the next, I think, 2 minutes, a completely finished image of both builds will fall out with a nice and neat, fresh STVE check report and everything that you could ever imagine. So while we're looking at this with one eye, I'm happy to take any more questions. Thanks for having me. Thanks for listening to my quick babbling about crazy things. Yeah, and for being such nice targets to throw chocolates at.
Hi, Michael here. So let's talk about person B. They're debugging something, okay? They want to throw a bunch of code in their thing. They might do print K debugging. They really don't want to commit it. They would really like a 5.5 second recompile and download to their test machine, and they don't want to mess. They don't even want to wait 2 minutes for all of this.
Yes.
So how does that work?
You can either go through the Yocto route, which has something called DevTool, where you, so there's 2 stages involved. There's pointing the source repository to his working code, and DevTool can then run off, build just that one package and push it to the target straight through SSH. So if your target can be reached through, obviously it needs a little bit of polishing for whatever use case you have, means like firmware loading or inputs, outputs. That is one option. And the other option is obviously like using some SCP stuff, whatever happens to move the binary around. I am specifically focusing on the non-developing, but deployment and like getting out part here. I know that developing is, or the development side is a little bit different and sometimes complicated. Thanks for the question.
So in addition to that, so I mean, for the Linux side, the deploy stuff from Yocto is quite convenient to do. But if you want to do the same for the Zephyr side, that is a bit more tricky if you want to do that through Meta Zephyr. So when we tried that in practice, it was more not really working that well, I would say. So what normally happened is that people have been falling back to having like a VEST build or whatever built directly from Zephyr and flashing directly with manual tools instead of like going the extra routes there. So there's definitely room for improvement to get these kind of setups working where you have like an Zephyr built inside and then you want to flash that from the Linux side or something. So right now, that is not really working so optimal.
Josef, you said, I think we were chatting offline, and you had mentioned that someone had already done a similar kind of RTOS on the M4, Linux running on the M7. I know that you might not be able to do it right now, but maybe on your Twitter, would you be able to post a link to that work? Because
if I happen to be lucky enough, then I can just find it right now.
I thought it was really interesting how you pointed out there was communication between the 2 cores with OpenAMP or something like that.
Yeah, it is certainly there. Yep, here it is. The presentation is called Linux and Zephyr Talking to Each Other on the Same SOC by Diego Suera, Sepura, and Pargaderos. Where am I supposed to drop the link where you can find it?
Just put it on your Twitter is fine. I think we'll probably add it to the notes later.
Here is the chat. I'll just drop it into the... Does this work here? So I just dropped it into Matrix chat. So like I said, this is out there, and I just thought it would be not a good use of your and also my time to just regurgitate it. Yeah, we've got a couple more minutes, and I've got a couple more chocolates. I like people who can say yes. because usually everybody is afraid of asking for chocolates. I have no idea why.
Go for it,
Oh, too short.
Okay.
Hey, so I have a question. Say I run the CAS build and suddenly it takes longer to build. How do I find out why?
That's a good question because there are so many different reasons, as you probably know, in the Yocto land.
Like something starts rebuilding.
Something starts rebuilding. Okay, then
Why?
there's bitbake diff6 or dump6 or whatever that can actually show you the one thing that changed between builds. So that exists. I don't have the syntax on my mind. I have to look it up each and every time too. But you can bitbake stores the signatures, the big hashes of the recipe each time, and you can get a diff between those, and that tells you let's say an evaluated diff that tells you which variable changed from what to what else, so you can actually hunt down the source of the rebuild. So it's not exactly pleasant to use, but there's tooling for it. Bitbake, diff6 or dump6.
Thanks.
Okay. Where can I learn more about the CAS files? The CAS files?
Yes.
One of the concepts that's missing in the SBOM world right now is the deployed SBOM, i.e. what has been configured to run on a system.
Mm-hmm.
We've got source ones that you've captured right now. We've got the build ones that are coming out of Yocto. But the actual deployed image and the information around what was deployed is still missing as part of the software lifecycle. So I was wondering if the CAS files could potentially be something that should be pointed to for that.
First, I owe you chocolate. Sorry. I don't think so, because the CAS file does not deal with
Config deploy?
with the software as is. If you're really on an abstract level, the CAS file is a meta information.
Okay.
So the CAS file, the CAS is the tool that gets metadata, which tells you which Yocto metadata you need, and that metadata again tells you which software you need. So it's like a two-step setup process, and only bitbake or Yocto in the end can tell you what actually.
Okay, I'll start talking to more of the Yocto group.
So Kate, what we are doing is we are also doing all the compliance stuff, but we do that externally of Yocto. So we have like all the SPDX classes and so on, get that as a feed in, but then we have like external tooling, just like for solidity, scan code and so on around that to actually understand what's going on. And then we have like people manually looking over that. So I'm not sure how we can really get that integrated in Yocto, so pitches.
So the subtlety that's here is the fact that we want to move SPDX to be able to record more than sort of the source licensing. We want to be able to record what's actually the reproducibility factors. And that's where it's heading to.
Yeah, I think that a lot of this information is stuff that we already kind of do in license BB class.
No, there's license BB class that, but license BB class serves as, or can serve as a very specific use case, because it can collect the license text plus the license manifest and put that into the image.
But it can also collect local conf and BB layers. We can extend it to do that.
Okay.
As well with the it's been ages since I looked at license BB class, but we can kind of gather the entire source and how everything was built.
That's Archiver.
Is that archive? That's Archiver. Thank you. Thank you.
Yeah.
Apologies.
Thank you very much. I know you have to go catch your taxi.
Really.
I kind of want to follow you out like David Letterman, you know?
No, we can do that. I'm gonna take off this microphone here. Like I said, I apologize so many times for the real bad timing. Thanks a lot for bearing with me. Thanks a lot for listening to me. Here's some more chocolates, and see you around.
Okay, Carol, please.
Oh, I think I didn't click the button. There we go.
Okay. Hello, my name is Karol Guga, and today I'm going to talk about open source accelerators and VM accelerators. That's a pretty long title, but I think it summarizes, all the pieces and the bits and pieces that are combined together to build the system that I'm going to talk about. So first, a few words. Who am I? Where I came from? I'm from Antmicro. We've been here for quite some time. Basically, we're doing services. We build devices from open source components. And this presentation is actually a pretty nice example of what you can do by just combining a bunch of open source pieces, combining them together, and integrating into a bigger, better system. So what is it all about? I mean, the whole long title, what is all about? The whole story is that together with Western Digital, we worked on building a platform for research on computational storage. What is computational storage and why do we need it? I will tell about it in the next slide. But first, a few assumptions that we took when we started building the whole system. So basically, we wanted to create a platform where researchers can work on which researchers can work on development of those computational storage devices, accelerators, and technologies that can be used there. So first assumption was that it has to be open source. It has to be available for researchers. It has to be flexible. So we used Xilinx FPGA SoC. So we have like a freedom of like adding new logic and re-implementing software and adding new stuff, and develop it in a way that it's easily extensible with some new comments, with some new ideas that I would like to test. So why do we actually need accelerators in NVMe drives, those computational storages? This is because we're developing into a world where everything is processed with machine learning, with AI and stuff. So typically those applications, they consume a lot of data. And this data is stored somewhere, mostly in data centers. So getting them back from data center into some like a bulky machine or spawning new machine somewhere in the cloud and getting the data there basically causes a lot of traffic on those in data centers, and we don't really want that. So having possibility of like processing the data near to the storage is actually pretty fine. And also it can address things like you can process the data on the fly. So imagine a situation where you want to store like video and the video contains like sensitive data, like faces, maybe plates or something like that. So if you want to store it, you have to comply with a bunch of regulations. But if you anonymize it on the fly, you don't, because you don't really store sensitive data, which is pretty nice. So having accelerators somewhere there in the data center, somewhere there near the storage is pretty fine. But to have it, you need to have a hardware. And Western Digital actually built pretty nice hardware that can be used there. It's a 2.5-inch form factor, so looks like a disk drive, but it's not a disk drive. It's basically a development platform with this ultra-scale MPSOC, this thingy here. And bunch of RAM and so on. So with all the connections and all that stuff. So this is there, we can work with it. But to make the whole system available for wider audience, we also make it usable on off-the-shelf platform. This one is not as fancy as the one from Western Digital. It's quite bulky. It's like that big development platform, but you can buy it. That's the plus side of that one. So yeah, let's take a look at how the system works. The most interesting part of the system is within the chip, within the Zinc MPSoC. So you can divide it into two pieces. There is a programmable logic, FPGA, and there is a processing system which is composed of CPUs, interconnects, and a bunch of peripherals. So let's first focus on this side. We added, I clicked something. Escape? Oh no. Maybe this. Okay, and now full screen. Okay. So how can I remove this T thingy? Because I will click something again. Okay, let's maybe try to not click it. So we have this PCI core that connects this device to a host system, then some logic around it to implement NVMe stuff, and that one connects to a CPU part. This way, host system can actually send NVMe comments to the device, and we can handle that. And those comments, like typical NVMe, like standard NVMe comments, are there are two groups of those. Like there's admin comments required for like discovering the drives, setting what's there, or like handling, managing the instructions. And there's of course I/O comments for reading, like moving the data. So on the other side, when we have this logic that runs there, we have a CPU part. And if you look here, there are like two CPUs. There is Cortex A53. That one runs Linux. There is Cortex R5. I will talk about it in a moment. And if you look at the connections, Cortex R5, only Cortex R5 is connected to the NVMe logic within the FPGA itself. So we run Zephyr on Cortex R5. We use that one because Zephyr implements a bunch of, it was there, I mean, the port was there, so that was one thing, but it implements a bunch of functionalities that were really useful and made it really, I mean, made it way easier to implement the whole system. So we use Cortex, we use the Zephyr application running on the Cortex R5 to handle all the base NVMe comments. So every time the host wants something from the drive, we handle it in Zephyr on Cortex R5. So basically, it works in a way the host builds like a command queue in its own memory, then it writes some registers in this programmable logic within the FPGA that may, some of them generates interrupts, so we just handle that, we fetch the data, process it, and so on. And every unknown comment a comment that is not from a standard set, we pass it to Linux system running on Cortex A53. And I will talk about how this is done and how we handle that in a few slides. First, let's see how let's take a few slides on the FPGA part. So one of the problems with building a system where you have FPGA and you put piece of the system in FPGA is that FPGA is reconfigurable. Reconfigurable in a way that you change the logic there, and you can change like register layout, you can change memory map, you can change all those things. And there is not really, convenient. There are no convenient mechanisms in operating systems to handle that, unless you implement some kind of a discovery mechanism, which will then consume like some of the resources. So we didn't want that. So how can we actually handle that? And in our project, we decide to generate this code on the fly. It's not a new idea. I mean, it's done in many projects to just generate like dynamic code on the fly, but we made it one step further. So besides generating C and header codes, we also generate FPGA code. And there is actually one source of truth for NVMe. It's NVMe specification. The problem with that is that NVMe organization distributes that as a PDF. So we implemented like a set of scripts that just read this, pass this PDF, gets all the tables that are required, just gets the data from it, and builds the whole stuff. So the stuff is like header file C code for low-level accessors. That's pretty easy. That's pretty obvious. I mean, a lot of projects do that. But we also generate FPGA code, this Chizo code. If you're not familiar with that, Chizo is a Scala-based hardware description language. So we can develop digital logic, low level, very, very low level, but with all the features that modern programming languages give you. So all the, yeah?
Just a question. So Chisel, is that was that LaTeX that's done in Chisel, or I can't remember?
No, it's LaTeX is a framework
collection
for
of
building
IP
SOCs. That one uses MyGen,
Okay.
which is Python-based, something similar but in Python.
Okay.
Chisel is in Scala, so that's slightly different. The whole generator code is available on GitHub, so we can take a look at that. And if you feel it, if you just fork it and adjust for your needs. So this Chisel code for the registers look more or less like that. So this is an object. Basically, that's a dictionary. You can read it as actually this dictionary mapping integer something to a module implementing the logic. So later, when we generate Verilog code from it, the code that we are actually synthesizing and placing routing into the FPGA, we can quite easily generate a logic for accessing the registers and the whole the whole accessor, like multiplexing logic for that. So it looks readable, and also we generate a bunch of definitions for the registers that defines like a bit field. So the code in the end is readable. Yeah, the code in the end is you can just access simply access a field that you're interested in. So getting back to the software. As I said, we have this flow where a host sends us gives us information that there is a new instruction, new command, NVMe command. We pass it. If it's standard NVMe command, we just handle it in Zephyr application. We don't bother with the rest of the system. But what if there is a command that we don't know? We just move it. We just take it to Linux. And this way, you can actually implement whatever you want in Linux to handle that. In our case, we used, for cross-communication between those CPUs, we use remote proc for sending messages back and forth, and we use OpenAMP implementation. That was pretty obvious choice because both Zephyr and Linux implement that, so it was there. We even did support for Zephyr part on this Cortex-R in this particular chip. So there was everything was there. We just could take it and combine it together. So in our implementation, in this first implementation of this platform, of this framework, we run a service in Linux, and this service basically handles all the intercommunication between those CPUs, and it also runs a BPF virtual machine that can run any payload that you provided. So this BPF virtual machine is to show how you can implement an accelerator. So basically, standard NVMe is there. You can just send the data, but then you can use custom NVMe commands to provide the whole system with a BPF bytecode, and this BPF bytecode can refer to certain memory blocks somewhere on the NVMe drive. So basically, you can just load it with data with simple DD, then use NVMe CLI to provide the BPF bytecode. BPF bytecode can be, of course, generated with LLVM, so that's pretty easy. And since we wanted to make it extendable, we wanted to have something that can run machine learning and AI payloads. So to do that from a BPF code, first of all, we had to run a BPF virtual machine, and we used microBPF, which is implementation of userland BPF virtual machine, so you don't have to run it in kernel. In the kernel, you can run it there, and that made it pretty easy to extend the whole system with additional instructions to just provide the system with some payloads to be run. But how to actually get some acceleration, some runtimes, machine learning or AI runtimes accessible from BPF code. BPF is a virtual machine, and you would like to, at some point, probably talk to the hardware. So how to do that? So we choose a TensorFlow Lite as a runtime, as a machine learning framework runtime, which is pretty cool because TensorFlow Lite, you can compile it into our library and just load. So it's not like a hardware dependent per se. Of course, you can make it hardware dependent, but it's not like that per se. It provides already implementation for most of the operations that you typically have in machine learning models. So you can quite easily run almost any model on a CPU. But it also provides you infrastructure for implementing something which is called delegates. So you can quite easily extend the library with some custom code that would allow you to run any payload on any hardware accelerator. I will show how it's done later. But how to actually access external code from a virtual machine from BPF code. So there is an option. You can extend, I hope that's visible. You can extend a virtual machine and micro BPF itself and register new calls for the functions that are external to the machine itself. So basically, as you can see here, there are like two functions. The third is not defined, but you probably know how it can be done. And then you just register it within the machine with some kind of a number, and it's there. And then from a BPF code, this is of course C code, but cross-compiled with LLVM to then BPF bytecode, you can use this function by just first defining a pointer with a very dummy value, like 1 to 3. And if you compare it here, they were registered with the same numbers here. So in the end, bytecode just references to external function 1, and you can use it. It's not very convenient because you have to upfront have a virtual machine that knows what's there, what functions are available to be able to run your bytecode that you compile. So we have already something working. It's not yet published. That's why I have this coming soon here. We have already a mechanism for dynamic loading that. I mean, the virtual machine can just load a library, and then if a symbol is referenced from a bytecode, just check if the symbol is there. If it's there, just jump to it. So this makes it way more convenient for the user in the end to use external functions and to use some like external accelerators. So with those, with this runtime in place, with TensorFlow thingy, TensorFlow Lite thingy in place, with delegates in place, we could actually, think of adding an accelerator, right? Like a physical hardware accelerator to the system. So for the first implementation, the system basically is not, the whole framework is not really constrained, like you have to use this one. You can use whatever accelerator you want, even connect it with a USB, for example, some additional external accelerator. But for the first implementation, for the first showcase, we chose VTA, which stands for Versatile Tensor Accelerator. That one comes from Apache's TVM project, and this is a open source accelerator that you can deploy in FPGA. Of course, you can make ASIC from it, but FPGA is way faster and way cheaper to play with. And it's implemented in Chisel. Basically, it's like a coprocessor where which you can program, which you can feed with like again, I would say bytecode that it can process, fetch the data from a memory, process, and write back. Yep.
Hey, Carol, just had a quick question. So I don't know how many slides there are left exactly. I just wanted to say there's tons of stuff, but also, so I'm sure a lot of people are wondering, we're talking about NVMe here, but we're also, this is an IoT micro conference. So, and maybe I'm leading a bit, but do you think it's possible to kind of take the server class AI accelerator that you've designed and kind of scale it down to something?
Yeah, of course.
Yeah, okay.
Yeah. I mean, this TVM is not that big. I mean, VTA is not that big. It is configurable, so you can shorten like pipelines. You can short the memories there, and I'm pretty sure you could fit it into like a smaller device,
like a smart camera or something like that, where you're using AI for.
Yeah, actually, with all the, not sure if you heard of, but there is this whole MPW shuttle program from Google where you can basically design your own chip, open source chip, give it to them, and you will get it for free. Of course, you have to wait a few months to get it, but you can produce your own chip. So with that one, you can probably put it there. Yeah.
So do you know how many resources of that ultra scale does the VTA consume in percent, give or take?
I can check it, but I don't have the number right now. I can check it after the presentation.
And I have another question regarding the NVMe. So when the host PC sends a command to the NVMe in the ZingMP, and that command gets propagated to the Linux system, that probably takes a while, right? Is there a possibility that the command on the host PC would time out?
It could time out if you do like a lot of stuff before ACKing the command. But the only thing you need to do when the command is there is to ACK it, basically. And that one is pretty fast. Then, of course, if you like wait for the results, you should do something like check if there is a result, and if it is, just get it. Just not try to get it like immediately, because it may take some time to process the data at some point. But just send like if you send like a load firmware command, for example, you just have to ACK it. You just set a flag like, okay, I handle that, and then that's all. Yeah. Okay, so with this TVM there, the TVM there is sorry, VTA there is just a first accelerator that can be used. And basically this is what the delegate, what the software have to do. So you have like a payload with some like machine learning pipeline, machine learning model. So the delegate have to translate it into set of commands that are fed into the accelerator, in this case into VTA. So basically that's load some data, process it with that kernel, for example. Kernel, I mean like a piece of small piece of software that runs on the accelerator, and so on, so on. Write the buffer somewhere else and use the next kernel to process it further, and so on and so on, so on. So in the end, you have a result that you can write back to some space in the NVMe drive, or just send back to the host. So yeah, that's how it works. And if you'd like to get on with the project, like grab some piece of it and then use it, it's all open source. Right now it's on Antmicro's GitHub, but it's going to be donated to Chips Alliance soon. For now, like today, if you want to grab it, it's there. We'll just follow this link. There is more directories than just, there are more repositories than just this link. The main one collects all of the pieces to build the entire system. So basically, you can just clone it, grab all the submodules. There's even a Docker file, and like make Docker targets to build you like a development environment if you don't want to play with all that stuff. You have to have FPGA tools, though. Those are not provided in the Docker, and those are unfortunately proprietary, so we cannot use them. We cannot provide them like in the repository, but fortunately they are free, so we can just exchange your email address and some like private data to get the tools. So if you're interested, just go there, grab stuff, and please you can play with it. Just to wrap it up, the system there kind of presents, it kind of builds like a pretty nice research platform. It's all open source. It's all, you can use it on off-the-shelf development platform. So I hope, researchers will just start using that. You can use it to develop like a bigger, smaller accelerators and just use them without worrying of like how to interface it with the rest of the system. It's there. Contributions are welcome, and if you want to just grab like a piece of the code, not the whole system, feel free. Most of the code is licensed on Apache 2.0. Of course, the pieces like Linux, U-boot, and things like that are licensed with GPL and whatever license that they had originally. But the rest is permissively licensed, so feel free to grab it, use it, and combine it with whatever you want. Thank you, and if you have any questions, I'm happy to answer.
Thanks a lot, Carol, for that. That was really impressive to see. I think we have like one question here, and then I have one from the internet. So we can...
Well, I was curious. I had heard Western Digital is very much into RISC-V, and so I was surprised to see the ARM Cortexes, and I wonder if that's a transition that you think that's relevant to you, or not?
Yeah, I mean, we're also deeply involved in RISC-V with Antmicro. So the whole system could be easily implemented on RISC-V. There's nothing really like ARM related. Yeah. Yes. The SoC we use, the SoC we used had already those ARM CPUs, but there is pretty nice support in Zephyr for RISC-V microcontrollers. There is really good support in Linux for RISC-V. So combining them two together shouldn't be that hard. You just need a platform that could do that. There is a microchip FPGA that could potentially do that. I mean, there's this PolarFire SoC, like RISC-V SoC with FPGA. It doesn't have like microcontroller part like easily accessible, but still the system could be ported into that one.
Okay, thanks. So there's another question on the chat. So let me read it out. When do you know when the data processing has finished and you can get it back on the host system? NVE interrupt, polling?
So NVMe, you have to pull it from the host side. Basically, just read register if it's ready.
Okay.
So yeah.
Thank you. So any more questions in the room here?
I was wondering, with CXL, would this also apply to devices on like computational storage with CXL? And if so, is there like open IP for that instead of NVMe?
Open IP for NVMe controller itself?
Well, like, I mean, I don't know too much about it, but one of the new protocols for attaching things is CXL. So I was wondering if that's relevant at all to the computational storage, or is that different thing?
It's not tested here. I'm not sure. To be honest, I would have to read a bit more about if there is something. But probably if there is, it should be pretty easy to implement here to extend the whole stuff here.
I think the main advantage there would be that you don't need as much in terms of DMAing stuff around, because CXL is the direct memory access. So then you're just really relying on interrupts, which is kind of nice. Are we at time?
1 more minute.
1 minute. Any other questions? Okay, well, Carol, that's pretty fantastic. He did this talk at ZDS too, and I thought it was super impressive. So thanks again for coming out.
Thank you.
And this is like fantastic. So round of applause, please.
Thanks. Wait a minute. There are 2 more chocolates here. If somebody wants.
A demo because I do stupid demos. Let me take this off. So I'm going to be talking about abusing Zephyr and MetaZephyr and doing really bad things with them that make BSP maintainers cry. So who I am, my name's Eilish. Most of you know me as Pidge. I'm a software developer for 30 years. First Linux installed with Slackware somewhere around 1994. And if you've known me around the Yocto project world, I'm the Yocto project ambassador, and I also make cute embedded nonsense demos. So yay, you've seen the Yocto blimp go out of control and veer into people, the Yocto portable DJ, which has gotten noise complaints, and the embedded hurdy-gurdy. One of the things I'm less known for is I led the initial team that was responsible for the work on MetaZephyr, which brought the ability to build Zephyr into the Yocto project. Earlier last year, I got a new job, and I was asked to go revisit MetaZephyr, and I did. And I wasn't happy. So this was through my work with the Anero project. And what we have basically is we have open embedded and MetaZephyr using 2.7, and we have like a machine config in there, and we have like 8 machines. And, you know, we want to use some Zephyr modules. We're using machine overrides for that, which is kind of silly. And then we have not even the entire Zephyr, we have part of Zephyr, and we're just, instead of using West, we're going to use CMake. And this worked in a way, but it didn't make me happy. So there were a few problems here. First problem is that all of the things that we use to, how we're using Zephyr is generally I check out Zephyr, I check out my Zephyr project, and all that configuration sits in there. So why am I going to go and replicate that up here in an inexact way? So what I'm building if I do a Zephyr West build is not exactly what I'm building if I do a Yocto project build. The other thing, and this is where I really kind of hit this, is that we're hard coding what the Zephyr modules are by using machine overrides and passing those into -d Zephyr modules to go tell CMake what we're actually doing with this. So if I add any of the Zephyr modules in my project, they're not known about. So I have to replicate that metadata both in my Zephyr project and in my MetaZephyr BB appends. So that didn't make me happy. And also there was an incomplete source URI. I ran into that trying to build something, and I'm just like, why is this not finding this module? Well, we're not checking it out. And then there were only 8 machines available for Zephyr, and there's 390 machines. And my boss was like, ooh, boy, it would be really nice if we got all those 390 machines. And I'm like, all right, I'll take a look at it. Oh, and then last, just because I was being pedantic, the MetaZephyr layer was not Yocto project compatible because it basically had BSP definitions mixed in together with the operating system. So if we go down through what the MetaZephyr issues were, we're treating Zephyr projects as CMake projects, which they are, but really Zephyr, the canonical way to be building this is by using West. So maybe we should just use West. MetaZephyr had no knowledge of Zephyr modules unless it was told. And we were using machine overrides for this, which was kind of sloppy and lazy, and putting this in the machine definition, which we really shouldn't be doing this. Zephyr should really be taking care of this, and we shouldn't be replicating this. And if we wanted to add extra Zephyr modules, we could do that, which was great. And again, 8 supported machines out of 300 plus Zephyr machines, and how to support as many as possible. And then last, the layer structure wasn't technically Yocto project compatible. So let's go to the last one. Last one was easy. BSP layer should stand alone. So we have MetaZephyr, BSP, and then MetaZephyr. That was pretty straightforward. We just split those out. Then the other thing is that Zephyr should control as much of the compilation as possible, which is the premise I'm working on. We shouldn't need to replicate all that metadata from Zephyr back up into Yocto project. No point in doing that. I also wanted to get more machine support, which means we need to get a full Zephyr checkout. So we need to go through what all the source URI and the submodules are and get all that and get it into the Zephyr recipes. So let's get rid of machine overrides first. I spent about a week trying to figure out the right way of doing this. And I actually went down, well, let's read the kconfig of this and figure out what all modules are and do this. And then we can auto-generate machine overrides from the kconfig, and that was a really bad idea. There's a lot of work to build and maintain. And again, we still have machine overrides doing what essentially shouldn't be something that it shouldn't be doing. And I started poking through the Zephyr code and I found module YAML. And I'm like, oh, okay, that's interesting. And it references Zephyr module.py. And then it's pointing to West. And I'm like, I've been trying to avoid West. And the reason why is if you buy me a beer, I will go on and on and on and on and on about how I dislike one ring to rule them all tools. So like, if you want to hear me kvetch about certain tools repo, I dislike them, buy me a beer, I'll go on for about a half hour about it. And then I started looking at West, and West is one of those one ring to rule them all tools. And I'm like, oh, I hate this. But it's actually, God, I'm gonna hate this. It's pretty good. It wraps Git, CMake, all the manifests, uses plugin framework to extend. And then I was like, wait a second, West List gives us exactly what I need here. So I need to ensure that the checkout compiles with the West workspace, which was a little bit of a interesting thing that I had to do. I had to kind of munge that workspace file, create a West native recipe, and then create just do get Z mods where I West list and spit out all the Zephyr modules that West is aware of. And then just populate these Zephyr modules, and then we can still do these Zephyr extra modules. So if I have an extra module sitting in my source URI that is not necessarily there, I can still pop that in. We can pass that all in. Excellent. Machine overrides, go on. So now let's go get 200 and some odd machines into Zephyr. This stumped me for a bit. I was poking around Zephyr going, okay, how am I going to do this? How am I going to take all these board definitions and make Yocto project machine definitions out of them? And I was looking at the makefile exports and I'm like, let's abuse this. Let's say that, so the Zephyr project has this ability to export makefiles based on what you're building. And I'm like, wait a second, I could just do this. I could just go and for West boards do blah, 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 and spit out as many Zephyr machines as possible. And I did. So out of the 395 Zephyr machines, I got 323 of them generating mostly correct with the correct tool chain and all that. And 291 of them will actually build. This is great. My boss was ecstatic. He's like, yes, we have all these extra machines. And if you want to see a BSP maintainer cry, post 291 recipes to the Yocto project mailing list and watch John Mason's vein in his head start twitching. Because, yeah, this solved my problem. My problem was solved. John Mason and other BSP maintainers were not happy. They were like, hey, wait a second, we have our own BSP for this. And our BSPs are tested. And we have actually the hardware. Do you have 291 boards sitting on your shelf at home? No, I do not. So this fixed my problem. It didn't fix John's. John was very unhappy, and you can see that on the mailing list if you want to go back through the history there. So the solution here was to create a little recipe called generate machine configs and just leave that there. If folks want to do that, they're more than welcome to, but not put those 291 machine definitions into the actual layer. So this fixed my problem. Does it fix everyone else's? And this is the thing that we have to ask ourselves when we do things, especially when we do things when we're stomping on BSP layers, because the BSP vendors get very cranky about that, rightfully so. And when I was working on this, not all the machines made sense. POSIX didn't really make a lot of sense to be able to do this. Didn't really need to do this. So post-SAC changes. We still have open embedded. We've now split MetaZephyr BSP into its own layer, and we have the machine comps, which is great. We also have a recipe called generate Zephyr machines. We can generate all the machines that we could possibly get out of it. So somewhere around 291 additional machines. And we've now reduced the metadata replication. We don't need to, we can rely on what's in Zephyr to actually be able to pass that information on up the stack. In Zephyr Core, we have Zephyr BB class that's now using West, compiling using West, not using CMake directly. The Zephyr kernel recipes now have the full source URI, which is great. So, and the Zephyr modules are now automatically generated by using WestList and a really nasty awk. So this is the status of where we're at now.
Pidge, I have a quick question.
Sure.
I'm the LTS maintainer, so it made me ecstatic when I saw version 2.7 there, so thank you very much. But for Zephyr, I should say.
Yes.
But of course, I mean, it's been years since I've used Octo, unfortunately, because now I live in firmware, but presumably you've versioned this too, right? So people can choose the 2.7 LTS or 3.2 or whatever,
Yeah,
right?
yeah.
Okay.
They can. I believe 3.1 is currently in Meta Zephyr, and I think
2 is almost, it's on the cusp.
2 isn't there yet, but I think that's the plan.
Awesome.
Last I heard.
Yeah. Awesome, thank you.
Yeah.
So I think 2.7 is still there. 2.6 they deprecated at some point, and now it's like 3.3.0 and 3.1 or something like that. So, but that was there. That was already there before Pitch started all the work there.
Yeah. Come on, questions. This is interactive.
Anyone else?
Yeah, yell at me for annoying John Mason.
So Michael here. So one of the, I think, stresses in many, many OS projects is, can we actually test all the things that we can build? And then the question becomes, should we bother pretending that we can build things that we can't test? And is it better to let them rot and knowingly not build than say, oh, I built this thing, but it probably doesn't work. Right? Like, what's better? Then you said there's that vendors have BSPs, which they're not contributing to Yocto, to the Oniro project?
No. So there's the Meta ARM layer, which those BSPs are tested with Meta Zephyr specifically. So what I ended up doing was basically stomping their machines by generating ARM-specific machines from what's in Zephyr and dropping them into Meta Zephyr, which made people unhappy, rightfully so, in my opinion. I was thinking about my problem solved and not John's problem that I created. Kate.
Yeah, have you turned on the SPDX generation for this system and looked at the outcomes of the SBOM's outcomes from this?
Have I?
Yeah.
No.
You?
Can I? Yeah, sure.
Okay, because I'd like to compare and contrast it with what comes out of West SPDX too.
Yeah.
I think it'd be fun. Thanks.
Cool. So I wanted to follow up on the testing problem. It's here. There's something that you said that you don't have this 400 bolts on your desk. And the problem, actually, we did address exactly that with Zephyr. We built something. If you Google Zephyr dashboard, we run more than 400 boards right now that are in Zephyr, generate like hardware description by basically parsing device trees in Zephyr, and run them in emulated environment. It's not like 400 boards on somewhere, but the results are published on a web page, so we can basically go there, check what demos actually built, which demos work. So we test like Hello World, Philosophers, Shell, MicroPython, and TensorFlow Lite module. So it's probably it could be somehow adapted to test.
No, that would be interesting.
We after the meeting we can. I mean after
and I think that the generate Zephyr machines recipe is interesting because it takes what we're exactly building in Zephyr and brings it up. Because if we're using Meta ARM, we're using a kind of a different BSP configuration. And that's not necessarily a bad thing, but it's not necessarily testing what we're doing within Zephyr. So I think it kind of takes it depends on where you're coming from on this. If I'm producing product that I want ARM to support, then using MetaARM is a smart thing to do. If I want to test just what's in Zephyr, then using the generate machine configs is probably a smart thing to do. But it's, you know, 6 one way, half dozen the other, in my opinion.
I mean, one of the reasons your boss gave you this request was like to make sure that if you have partners or something that come in, they want to get kickstarted with something easily instead of just. I mean, you can always go and working with the MetaARM guys to figure that all out and stuff like that and have maybe the best tuning. But if you just want to get started, it's really like convenient to have that.
Yeah.
And also like very interesting to, I mean, we are not going ahead and saying we will test all of these things in Oniro or something. That's not going to happen. We are not going to maintain all of that. So that's why we are settled for having like just a receipt to actually generate them. So I think that's like a good middle ground here. And then if you really want to build a project or a product out of it, then you might even tune the machines later on anyway, or switch to a different layer or whatever.
I think there's just about 5 minutes left, so I didn't want to derail from your slides.
No. Well, there's not many slides left, so like this is one of those talks that's more interactive, and there, you know, the moral of this story is just because it solves my problem doesn't mean that I haven't created a whole bunch of problems for other people, but you know, that's kind of the beautiful thing about this.
I think we have a few minutes for your glove demo.
Oh,
if you want
really?
to do that.
All right.
I think we have that.
So if you end up going to OSS, hopefully Linux Foundation gives me another warning about sound. Hold on here. This is only part of the demo. This is actually a Zephyr Bluetooth MIDI or Bluetooth Low Energy over MIDI. Here's a little MIDI keyboard here, and hold on, let's actually get something other than, let's do power synth. Yeah, this one's dead. All right. So yeah, there's I don't know if folks have seen DJ in the Box. DJ in the Box used to be about yay big. DJ in the Box is now about yay big with a glove. So yes, this is my cute embedded nonsense demos.
Built with Yocto or?
Built with a Nero project. So this is Zephyr and the base station is Yocto project based. So, or as Joseph said, and I'm going to get him on this, Yocto Linux based. So, yeah, any more questions? Perfect.
Okay, that's good. So thanks a lot.
Who wants chocolate? Chocolate? All right, there we go.
You're taking over then. Thanks a lot, Pitch.
All right, John Bob.
So the next speaker will be presenting remotely. So I mean, you need to figure out how to set that up. So
yeah. So can you hear me? Hello, can you hear me?
yes, we can actually. So you can take over the presenter, and then you might be able to upload your slide.
Yeah. So this is done. This is done, and now I need to upload the slides, which are here. Let me just. Okay. Should be uploading. Not sure if it was accepted. Oh, it's converting. Okay, it's still going on, and now it should be.
Yeah. So that is working well. I will leave it like that because then we can see the video as well.
Okay. Yeah.
Okay, cool.
So there's still like 2 minutes, Bartosz, before we start.
Actually, this whole remote thing seems to be working quite well. Can you see the output from my camera as well?
He's controlling them.
Yeah, I do seem to have control.
Does anyone know on the live stream whether or not Bartosz is showing up with his video?
Okay. Perfect.
Fortunately, I will not be able to throw chocolates at you. Just making sure, is the audio muffled or anything? But I'm not sure which microphone I'm using, if this is the right one.
There's a little bit of like room echo you have in there, but besides that, I mean, maybe, so if you can check if you're using the microphone of the headset, that might be better.
Is this better now?
No, it's still the same. I mean, we can hear you, it's fine.
I can use this one. Test, check.
I think that's a little bit better.
Okay, so let's stick with this one.
Okay. Yeah, I think we are on time now. So let's welcome our next speaker, Bartosz. Bartosz will talk a little bit about the libgpio-D version 2. So a new design, new major release going in here. So he's presenting remotely. So please give him a welcome.
Hi, hello. Nice to be here. Okay, so about me, I have been doing embedded systems for 14 years. I do kernel and user space work. I authored and maintain libgpio-D, which is the subject of this talk, and I maintain the GPIO kernel subsystem in the Linux kernel. I also contribute to various open source projects, including various Yocto layers, and since recently I started maintaining the LVGL stack in Zephyr. So this talk, before I dive into the libgpio-D itself, I will just do a little recap of why we're doing it. So it turns out that despite our best efforts as maintainers of GPIO or the GPIO subsystem in the kernel, people still want to use, still want to control input-output ports from user space for various reasons, mostly for prototyping and also for simple, for user space control over various switches, buttons, and sensors that not necessarily have or require a Linux kernel driver. Or for devices that don't really plug in well into any of the existing Linux subsystems. So for that, the Linux kernel exposes a GPIO character device per chip, or rather, should I say, per bank, per GPIO bank, and it exists in /dev as GPIO chip number. And this interface has been around since 2016. It's meant to replace the old sysfs class that was an earlier invention. And unlike the sysfs, which is accessible using command line tools and basically with some simple scripts, this interface consists of a bunch of ioctls and C data structures, and that is pretty cumbersome to use. So libgpiod's goal is to wrap that functionality first into a higher level C library, then high level languages bindings, and eventually command line tools that can be used in scripts. Oh, the animations don't seem to work. Okay, so this was supposed to be animated. Anyway, so this is the whole software stack going down from the hardware, where we have the specific GPIO drivers in the kernel that use the interfaces provided by GPIO lib, which is the subsystem code in the kernel. Then we have the layer that exposes the character device. We cross the boundary into user space, and now this is the part where libgpiod lives. We have the C library, then we have the language bindings, we have the shell tools, and users can build their user programs on top of languages and obviously shell scripts using GPIO tools. So I wrote that somewhere in, like, the first version was written in somewhere in 2017, and coming from more like in-kernel development, I learned very fast that API design is hard. So I used the old Soviet method of reconnaissance in force when writing that. I would just work with use cases and write C code. And it turned out it's a problem when the library was finally released with a stable API, that certain shortcomings became visible. So lessons learned from that period is that you should always plan to throw one away. And when looking around, it's true that most projects, like most libraries, have versions 2 that are much more successful than versions 1, that are incompatible due to various API reworkings. And certain things to look out for is that when I was writing the GPIOD, it was like a home project, and then it turned out that people actually started using it and started sending me email with bug reports and questions. Why does it work like this, or why was this done this way? And also you should think about whether the users that will be the target audience of your projects are experts, because it turns out that many people that work with hardware are not necessarily expert programmers, and if you make your API difficult to use, they will bounce off it or bombard you with email about things that you would assume are obvious. And also another thing is that when you try to write an interface in a programming language that you don't know very well, then you can get into trouble. At the time when I started writing the C++ bindings for libgpiod, I wasn't really an expert. I'm still not an expert in C++, but when I wrote it for the first time, it turns out it was actually low quality C++. So we had actually the same problems with the Linux character device interface, the user API, because when we wrote it, we had something very minimal in mind, so that not to tempt users to overuse it. But the minimalism aspect of it made it so that it was really impossible to modify it when users came up with valid reasons for modifying it. And those reasons were something like, we can monitor interrupts from user space, but we cannot set the debounce period, so that makes it not very reliable. We don't have sequence numbers in edge events when we get them in user space. We cannot set the internal pull-down resistors, which we can from the kernel. Kernel has different clocks that can be used for time stamping. We couldn't modify them or set them from user space. We don't have any means of getting notified about changes in line status. So when lines get requested or released,
And finally, this is a new development. People are asking to get the process ID of the consumer and user space, so that one process can figure out what other process is actually holding given GPIO line. So all these were very much valid use cases and space for improvement, but it turns out that we could not modify the existing kernel interface because we didn't leave any padding in the structures that we are exposing, and other reasons too. So before I go into libgpiod, so now we do have the character device version 2 ioctl interface in the kernel, which is much more, which offers a lot of, already implements a lot of those features that I spoke about here, and also has some space for future improvements if that's needed. So before I go into libgpiod itself, I would love to say that it's out yet, but it's not. The work is still kind of in progress. Most of it is complete. We have completed the API for C and C++, and now we still need to update the Python bindings. And we have some changes queued for the command line tools. I already committed to a date some time ago and didn't make it, so I'm not saying that this will be released in a month or two. I would just say that it will be released when it's ready. So libgpiod v2. The goals for the new major release was to make the usage more intuitive, make it as difficult as possible to commit programming errors, and also, when using high-level bindings, allow for concise code. So basically, use whatever syntax advantages a high-level language provides to make the code as brief as possible. And also, don't try to needlessly represent the kernel model as it exists in the kernel, which was one of the reasons why the previous API was so cumbersome. So yeah, this was also supposed to be animated. So this is the model basically that we have in the kernel. So we have the providers; these are the GPIO chips, and consumers, whatever device driver needs to control these GPIOs. And what you do in the kernel is that the driver will request a line or a set of lines for exclusive usage, making it impossible for anyone else to request it. And we followed that model I followed that model in libgpiod v1, where you would have objects. So I'm not going to bother you with code snippets because it's boring. I will rather describe the API in terms of data structures and their relationships. So we have the chip structure, and you would get your line or get a set of lines, and then you would keep those objects alive, and you would run all your operations on these objects, whether they are requested for exclusive usage or not. You would continue to use that line object. I'm sorry, are you still there? Because the camera from the room stopped. I don't see anything. Hello? Okay. Okay. I will just keep on presenting. I'm not sure if you're hearing me. So in V2, we're still going to have the chip object. But for the information about chips or lines, we're going to get immutable snapshots of information, unlike where you just read, unlike in V1 where you would read properties of those line objects, regardless whether they're requested or not, whether their status in user space is up to date with what we have in the kernel. Here we're being very clear in V2 that what you get when you request chip info or line info are really immutable snapshots of information. So for requesting lines, what we did in V1 was we would have a single request config. And whether we would reconfigure the lines or request them for the first time, we would use the same, despite the fact that certain properties would not be suitable for reconfiguring an existing request. That would be quite unclear. So we split that into two. Right now, when requesting, we use the request config and line config. And when we are reconfiguring an existing request, all we use is a line config. So this is it. Next thing in the model overhaul is reading line events. So this is one of the main functionalities where you can set up callbacks for your.
That's the local.
Sorry. Hello. Hello. Are you hearing me? I'm not sure if you're hearing me.
Yeah, no. Okay, so sorry. The room got dropped out or something. So you have to go back a little bit. Sorry for that. We tried to tell you, but we completely lost you. But
when did you lose me?
There. When you started that slide, basically.
Okay, sorry. Yeah, I was thinking because I stopped seeing the input from the room and I wasn't sure if you're still there. Okay. Where was I? Okay, so I said I'm not gonna bore you with code snippets because that's usually not very clear. Instead, I will talk in terms of more data structures and relationship between them. So V1, what we would do, we would represent the kernel's chip as a chip structure, and then we would represent each line as its own line structure, and you would get lines separately or in bulk. And this line, like this line object, would then be used to retrieve information about the line status, read its value, wait for interrupts. It would live throughout. It would be closely tied to the chip, so you would not be able to drop this chip structure as long as you have your line. And this is not very clear because, for instance, the line state can have changed in the kernel, but you don't have any information about that. You would have to manually update that state. So what we did for information in the V1 is we have now immutable snapshots of information. So when you have your chip and you get your chip information or get your line information, you get a structure with certain properties that you can read, but this is clearly said in the documentation that this is an immutable snapshot only valid at the time of the call. So if something changes in the kernel, this snapshot may no longer be valid. But about that in a second, how we can now get informed about those changes in the kernel. So requesting lines. So what you do with your chip structure, you want to request your lines from user space for exclusive usage. So previously, we would have a single big config structure that would also be open coded in the header file, which was also a big no in C libraries. So whenever you would request the lines or reconfigure an existing request, you would use the same structure, but certain properties would not be suitable for a reconfiguring of the request. So that would be not very clear, would lead to errors. So for V2, we split that configuration into two parts. So we have the request config and have I been dropped again?
No, we can hear you. It's fine.
Oh, can you hear me? Because the on-site room icon just was okay. I can hear me. So now for V2, we have split it into two configs. We have the request config that is usable only at the request time, and it's in conjunction with line config, which you use for setting lines, configuring various line settings. About that in a minute as well. And line config, which can be used for reconfiguring an existing request. So that is all. That is in order to make it clearer and easier to use. One of the main functionalities of libgpod, what you can do with those requested lines is waiting for interrupts and reacting to interrupts in user space. So previously, you still have that line object, and once you requested it for reading events, you call a function called GPIOD line event read. And you would do that for each line, or you could, of course, do that in sets. But we thought that it's much better to do it differently. So the request, when you get the file descriptor in user space for the line request, it actually can live independently from the chip. So we created this new structure that is called the request, line request, which you can use for everything from reading and write and setting GPIO values to also reading the edge events, which is how we refer to those GPIO interrupts. And we have another structure that is called edge event buffer. this edge event already existed previously. So what happens now is you allocate your edge event buffer. This is the buffer that stores, keeps the memory basically for those events, because if you have lots of events, you don't want to reallocate those events all the time. So this is where they are stored. You read it from the request, you read your specific event, and only if you want to, you can copy that event. But in general, the memory itself is stored in the edge event buffer, which makes it much more efficient in terms of memory allocations. Next thing, so now I'm going to go into the new features. So I said before that we did not have previously any way of being notified about changes in line state, which means has the line been requested, or has the line been released, or has its config changed. So right now we have a new interface that is called Line Watch, where you can basically use your chip and set a watch on a line or a set of lines, and then be notified with something called an info event about changes in the line state. The info event actually internally contains this immutable snapshot of the new line information. So you can imagine that you can have your first line info that you got when first opening the chip, and then every time something changes, you get a new info event describing exactly what the diff between the two is, whether this line and this line has been requested, released, and so on. Next new feature, well, this is still the previous one. So this is how it works. You have your chip, then you call your watch line info on a line. You see that the line info that you retrieved with this call, you see that the line is not used. The used field is false. And then you, from the kernel or from user space, someone requests this line. You are notified about, like your file descriptor says there is something to read on it. You read your event, and now you see in this line info contained in this info event that the line is now used, which is how you can keep track of what's happening to the lines that you're observing. This is the thing I mentioned previously. So it's a better demonstration of the mechanism. So you have your request, you read your edge event into your edge event buffer, and now you say, okay, give me this event. This will only give you the address of the event stored in the buffer, but you can also copy it, and then you have an event that will outlive the parent buffer, so to say. And this is actually like this mechanism is used in I think a nice way in C++, where this is done seamlessly. So as long as you get a constant reference to your event buffer, you're not copying anything. If you call a non-constant, if you call it in a way that you will get a non-constant reference to this object, you will actually copy it. You will actually be able to copy it to some other user into a different object. So now, how do we configure the lines for a request? So previously, I was mentioning we had this big structure with various configuration options. What is a very major feature of the new kernel interface is that we can now have a compound configuration. So you previously, when you did a request of a line, you needed to have a very like use the same configuration for all requested lines. This is no longer the case. Now we can have compound, very complicated properties for settings for lines. So you can have a single line in output, another line in input and wait for events, another line in input but don't really wait for events, and set pull up resistor for one, don't set it for others. This is what the new kernel API allows, and for that in the library we represent that in the following way. So we have the bottom structure is line settings. This is just a structure that contains a set of line settings. These are not all of them, but just examples. So you can see that this line settings object contains specifies that any line using this settings object will have its direction and input, will listen for both edge events and so on. So now a line config object, what it does, it stores mappings of offsets to line settings. So what you do now is when you're preparing to request your lines, you create your line settings. You can have multiple, and then you map those to offsets. So you say offsets within the chip, of course, like we were talking about the hardware offsets of the lines with the chip. 3 and 5 take these settings. So offset 1 takes this setting, and so on. And and so then what you do is you request your lines. You get a single request object, which is internally represented by a single file descriptor on the kernel user space boundary, and you can use all these offsets within the single request, whatever their configuration is. So this is how it works. Next feature is we now have sequence numbers. So this was a request where people would play with bit banging, some other protocols. They would want to have their want to be sure that the line that the events arrive the correct sequence in correct order. So we now have like the edge event structures that we expose now have line sequence, which means that sequence numbers, which means that we increase it every time. An event happens on a single line, and we have global chip-wide sequence numbers. That means that this is increased for every line that from this single chip that has been requested within this request. So you can see that you have first event, both are 1. Second event, this is still offset 0, both are set to 2. Third event is a different offset. So now we're only increasing the line sec number for this line will be 1, but we're still increasing the global sequence number, and then we have again an event for the offset 0. So both are increased. So basically this 1 to 3 and the global to 4. So you can now keep track exactly of how the kernel sees the events. Okay, so for testing, for libgpio v1 we had this testing kernel module that was called GPIO Mockup, but this was very old invention and quite cumbersome as well. So we have written an entirely new testing module for GPIO in the kernel module for testing GPIO from user space, which is called now GPIO Sim. This, unlike the GPIO Mockup, doesn't require module reloading when the configuration for the chips, for the simulated chips, needs to be changed, because it's much more flexible. It uses config.fs for configuration, which you can simply change in real time and modify your layout of your chip. So this is how it works. You have your config.fs file system. You create config.fs basically works. It's like the reverse of sysfs if you're not familiar. Inside you create your device as represented by a directory. Then you create your GPIO bank or multiple banks per device. You enable it by writing to a specific attribute, and the new GPIO device, the simulated GPIO device, pops up in sysfs and dev, of course, and it can now be used and can be controlled from sysfs using dedicated attributes, so that you can set the value that the user using the character device sees. And this is how this is the interface that we're using for testing libgpio, both libgpiod and the kernel UAPI. Okay, so implementation-wise, in C, we went with opaque objects so that we can easily extend them. Same for C++. Python interface, I've been given a lot of advice on how to make Pythonic interfaces in Python, so I'm trying to make this one much more stick to whatever PEPs recommend. And we have Rust bindings that are coming up thanks to Viresh Kumar, who's working on that at Linaro. We also, as I said before, we have the command line tools in libgpio. So they are getting a rework. We will have a new program which will be called GPIO Watch. This is the one that will allow you to monitor changes to GPIOs in the kernel. We will have something that has been long requested, and that is the interactive mode for GPIO sets. So you will not be forced to just run your GPIO set and put it in the background, or just keep it in your script like an open existing process. You will be able to run GPIO set in the background and then open a pipe to it and simply send commands to change values or change the configuration of the lines using the interactive mode just by human readable strings. And also we will put more emphasis on specifying the lines by name, because it's much clearer than just using offsets and translating them manually using the GPIO find utility. So this is just an example of how the new command line will now look like. So we're pushing for human readable strings instead of numbers, and this makes it much clearer. So all that, why am I speaking about all of that? So this is an example of how a high-level language will use the underlying interface to make it as clear as possible. So this is just an example of C++ where you're using these chain mutators, Rust-like, to set the configuration for a request in a single line, basically, well, multiple lines, but technically it's a one-liner, and you do your request, and then you do whatever with this request structure. You have lots of interfaces for interacting with it, but this is how you would request a set of 3 lines for input and reading line events in C++, and this is another example, and this time in Python, where you would use the positional arguments to just specify the config, request the lines, and then read events and print them, because these events are printable. So the libgpiod lives here. This is the Git repo. You can have a lot of reference. You can see for reference the tools, tests, and high-level language bindings for examples. This is the branch in this repo that contains all the changes that are queued for the next release. Development happens on the Linux GPIO mailing list, just the regular rules for mailing list here. And yeah, if you want to help us review or request any features before we make the API and ABI stable, please reach out to me. Special thanks to Kent Gibson, who's done a lot of work on the kernel side of the GPIO, of the GPIO character device and the GPIO as well, and reviews all my patches too. And yeah, I'm open for questions if we have time. I don't know, probably we don't have much time left, but we had this technical break. So
I have a really quick question, Bartosz. So thanks very much for the presentation, and apologies for the brief audio interruption. So this is going to sound a little bit crazy, but I had to implement something recently where I was bit banging SPI on GPIO on an 80 megahertz microcontroller, and the latency was too much. So I'm sure you get bit bang questions all the time, but and hear me out. Have you ever considered hooking into IOU-ring for programmable GPIO, even though that sounds really kind of off the wall?
Yeah, this is like IOU-ring would be something like what the Raspberry Pi library uses, just memfd directly, and I have considered that, but I don't think anyone would be happy with that, and I haven't done any work in that direction. So I understand the rationale behind that, but
so we have another question coming here from the room.
Yeah, so related to this bit banging, maybe you can put like a BPF program in the kernel and have that do the protocol bit bang.
It's funny because the same thing came up during the GPIO BOF on Monday.
That was from me.
Okay.
I don't think that was me.
Yeah, I admit that I would have to educate myself on eBPF. I have not yet discovered all the possibilities. It does sound like a solution, and I'm not sure. Would anyone in the among the Linux maintainers be happy with a solution like that? Is that what eBPF is meant for? That's a question. I really don't know. And you would still have to cross the bound.
Well, I don't know if it's relevant, but I know Benjamin, I'm not sure how to say his last name, but he's doing it with HID. He gave a talk about it at Embedded Recipes, which was kind of interesting to like control what a HID device can do.
Yeah,
so.
I mean, he gave the same talk here, but he used it mostly for like having a faster development cycle with the user. So like giving the user like something he can run there instead of like recompiling the kernel and doing all the debugging there. So that was like one mechanism for him to make it a lot easier. I think the quirks still end up in HID in the kernel side, but it's like one mechanism for him to help there. I mean, yeah, eBPF is interesting for some subsystems, but if it's really going to fit for you, I think it would really up to the GPIO maintainers to look and think if it's like worthwhile to do that. I mean, there's no general rule for that. Okay, I think we need to close down. You have one quick question, or?
Actually, just a comment. As far as I understand the eBPF part from Benjamin, they plan to replace all the little hit drivers in the kernel with little eBPF programs in the user space.
Okay.
Which would then be compiled and injected into the kernel.
Okay, so maybe I need to look at that again because I was understanding it differently, but it's fine. Okay, thank you. So there's no more questions. Okay, so we have like, thanks Bartosz.
Yeah.
And for everybody, so we have like a 50 minutes break now, and then 50 minutes we are back in the room with the next talk. Thank you.
Done.
Oh, let me pray.
Straight to center.
depending on how the hiring is working.
Perfect. Thanks.
the physical layer and the data link.
But there are other application layers. Wireless HART and other things. If you out back to your have to do that. High layer. Not done his job properly.
Is it the problem? Something in the lab.
Sorry for that.
But just real life example, I brought the cover from started talking.
Yeah.
So I was like, no.
Really? Wow, that's good.
Remember Ziggy? Ziggy 06.
Okay. So I think we are ready to get started again. So I hope everybody in the remote stream can hear us. So we have now Miguel talking a little bit to us about his work doing in the 15.4 layer in the Linux kernel. So please give him a warm welcome.
Thanks. Okay, so thank you for attending this session. Well, can I mute myself because I'm hearing myself back? Now, okay, that's better. I'm sorry? I think so. No, that should be fine now. I just turned it off on my laptop. Okay, sorry for that. So yes, this is about the i3z 802.15.4 Mac layer. I'm Mikkel. I work for Bootlin, and besides other activities in the Linux kernel, I recently got involved in the WPAN subsystem. So I'm going to go through the specification very quickly, just to give a little bit of context of what I'm trying to bring upstream, and then I'll show what's now ready and some issues that I've had. So very quickly, this is a figure that I tried to, well, that captures where the specification, all the two layers that are defined in the specifications are. It only defines the PHY and the MAC layers in the OSI model. On top of them, you'll find 6LoWPAN and the ZigBee applications. What I'm interested in right now is the MAC layer, which offers two kinds of services. The data services on one side, that's, well, the data, and the MAC management services through what we call the MLME, the MAC sublayer management entity. So that's all what is related to the peers around you. So we want to make networks, and in this case, wireless personal area networks, PANs. So in a PAN, you'll find a PAN coordinator, which is the most powerful device. It's usually mains powered and should have quite a lot of computational resources. It may serve as a bridge with the internet. Aside, you'll find coordinators. So coordinators are also mains powered and fully featureful, while at the endpoints, you'll find leaf nodes, which are usually battery powered and much less featureful than the others. So how do we find the peers around you? Because that's the main target. Instead of having to describe the network statically in the lab and then bring it to the field, we want the devices to connect together automatically. And that's how we do that. We use beacons as very short frames being sent by the coordinators to advertise the PAN. So the PAN is the network in which they are. So the beacons can be either sent at a given rate. So the rate is important for power consumption for the leaf devices. And so you have a coordinator that sends those beacons at a regular rate, or other networks where there is no, so they are called non-beacon enabled networks, where you can request a beacon from the different coordinators that are in range by sending a beacon request, which is typically an MLME command. So while just after sending this request, you have to scan the channel. So a scan usually takes different channels because you don't know where the other devices are talking. So there are three types of scans. We are interested about two here. The passive scans would just change channels and wait a bit of time on each of them to gather the different beacons, or the active scans to actually trigger a beacon emission from the different coordinators around. What's interesting also with the scan is that you'll get an LQI, a link quality indicator value, which is actually pictured on the edges here. So this link quality indicator just tells you the strength of the signal. So maybe if you want to associate with a coordinator, you'll choose the one with the strongest signal. So my journey started by trying to add scanning and beaconing support for the discovery of the surrounding devices, and then enlarging and shrinking the network with the different associations and disassociation commands. We try to keep all those devices synchronized either by having those beacons being sent at regular intervals, or also by acknowledging some frames just to tell the other device that yes, we received the frame and it is still synchronized with the rest of the network. And for the last point, the faulty situations, that's actually something that I haven't implemented yet. So that may happen if you have a loss of contact with your coordinator, or also when two PAN coordinators have the same PAN ID and are too close to each other. There are PAN ID. Want to receive beacons. So if you have very strict hardware filters, address filters, the beacons might not get received because there is no destination field in a beacon frame. And once everything as well, you create we created a structure and started a background thread to handle the request. The background thread, of course, can be aborted at any moment. And for the beaconing thing, you can also change the interval while it's running. For the associations and disassociations, we don't really need a background job, but we absolutely need the MLME commands to be acknowledged. So that was an additional problem that we had to solve. And very often send also a response to the request we would receive. We should probably forward the association requests to the user space or to the user, which one it is. That's something that was asked by Alexander, but I didn't implement it yet, just because, well, I wanted to focus on the main features for now. Right now, an association is being accepted immediately. But adding this ping pong would not be very complicated, I guess, just because all the infrastructure is already there. And this operation is not very time critical.
But I mean, at some point we will need it. Right now, that's completely fine to go down that path. But at some point, we will need some kind of coordinator, daemon, or something in the user space to like handle all the leases for the different devices and so on, handle short addresses, like have the mapping and so on, and like expose this to other components in the system or something. We had that before when the stack was initially merged like many years back. We had a component for that, but then we changed the NetLang interface. That wasn't working. So I mean, before we merged it in. So just saying, at the moment it's fine, but at some point we will need that to get it up to user space and then handle that.
I guess yes, we will definitely. So yeah, I just wanted to make a short demo to show you how all this is working. So hopefully that will be quick and will work. Let me try that. It doesn't want to enter full screen, I guess. How am I supposed to turn this, make full screen? This one? We tested it right before it worked. No? That's what it makes. Well, maybe I can just try with that. Yeah, okay, it's working, right. Well, it's not full screen, I'm sorry. I cannot make it larger. I don't know, the arrows don't work. Yep. Oh, okay, on this one. Right. So, here is I'm on a virtual machine that is connected to my devices here. So I have 3 AT-USB devices there that run the Linux stack, as well as an Arduino Nano running Zephyr. So I'm going to start with setting one of those 3 devices as a monitor interface. So let's start Wireshark so that we can get a better view of what's ongoing. I can now show you just the association strip that I'm going to run. So it just basically sets up all the 2 other interfaces on the same channel. It creates a coordinator. Then it sets a PAN ID and an address on this coordinator. This coordinator will start emitting beacons, so advertising the PAN. Then the other device, the leaf node, will scan around on a single channel because I know which one it is, just to save time. And once it will have received a beacon, we will extract the address of the coordinator and we'll try to associate with it. I will list the associations on both sides. So one has a child, the other has a parent, and then I'll just disassociate the device. The leaf node will ask to be disassociated and list the associations once again. So here, of course, it's a bit big. So here are all the interfaces. We start the scan. We now get the coordinator. I try to associate with it. and it lists the associations. Now I deassociate and I get no other associations. If I open Wireshark, we can see that we first had 3 beacons being sent by the coordinator, then an association request sent by the Lyft node. The association request was first ACT, then it received an association response. If we look at the association response, we can see that there was a short address that was provided, so EF66 and a status which was successful. So EF66, which is the address that we find here in the end, because the device accepted this short address and will answer on the network with this address. Let's go back to the presentation. Yeah. Oh yeah, I need to enlarge once again. Now I can do it. No. Well, maybe I should do it on the other one. Yeah. All right. So those are the patches that I've sent. You have the links there. If you want to check out, I advise you to take the ones from GitHub, because I have like a 60 series patch waiting. And of course, I'm only sending the 10 patches or so each time. So those are most up to date. I also had, well, I skipped the Zephyr demo, but it works also with the Linux stack. On Zephyr, I had to make a few changes as well. So this is ongoing. I've asked a few questions and sent a pull request. So now let's talk about the major issues that I had. I'm going to be quick on the first one because they were more or less fixed. For the transmission, the MLME transmissions, I had, of course, an issue with the fact that the subsystem expects asynchronous transmissions. This cannot work for MLME transmissions because we want a status. While for data, we don't want to wait for the overall operation to be over because the transceiver will receive the packet to transmit and then wait a slot. Maybe it won't get it and wait even more. If it doesn't get a hack, it will have to retry again and again. And for data purposes, this doesn't really make sense. So we had to create a synchronous API on top of the asynchronous one. In order to do that, we actually used existing helpers which would help us track the number of ongoing transmissions, just to know that the data has been transmitted. Now we can send our own frames. And upon sending our own frames, we want a status. So we need to know if the transmission went well or not, if the medium access failed or not. And we added a reason byte to the error helper, just to give us this information. This information, of course, is only available if we have if the device is able to provide that byte. So I don't think this is something that has been included in the specification. The devices that I used here had a track status. Hopefully, this is widespread. But unfortunately, in my case, the firmware didn't support it. So with the help of Alexander, we brought support in the firmware and in the driver for those track status, just to be able to know if there was a medium access failure or if there was an acknowledgement failure.
I'm sorry that you had to go through that, because that is something I was supposed to add to the firmware like a few years back. And I talked to that with Alexander already a while back, but we never had a real need. So now it was falling back to you to get it fixed. So I'm sorry for that.
Okay. Well, he was really quick to answer, so now I get it. All right. We then had filtering constraints, filtering issues, because in the subsystem, so far we only had 2 filtering levels, either nothing or full filtering. The problem is with the no filtering at all. So the community called that promiscuous mode, but in the specification, if you look, it's not called like that, because promiscuous mode in the specification means we check the validity of the frame. Here, it's this promiscuous mode, that how it is implemented doesn't check anything and is here just for implementing monitor interfaces. So we wanted to have a middle level filtering thing because we had to receive the acknowledgements, for instance, and well, for the scan we had to receive the beacons, which I repeat don't have a destination field. We had another issue with the acknowledgements, of course, because the acknowledgements, well, anytime you want acknowledgements, you cannot use the no filtering level, because no filtering means that the frame doesn't go through the address filters, so you don't know if the frame belongs to you, so you cannot emit an acknowledgement in response. So, well, we had to uniformize a little bit what was in the stack, in particular the promiscuous mode, which was a function completely aside of the other filtering levels, the address filters. So Alexander provided a patch to have a first unification. But well, this is still ongoing. We're still discussing it. I think we agree, but we need to find the right way to implement that.
But does that mean that one will be able to monitor on an interface that's actually active and is sending ACKs?
So on the same PHY,
yeah,
we won't have an interface in promiscuous mode and an interface actually interacting with the other devices, just because of this acknowledgement issue.
So we still need two devices, one to watch and one to debug.
I guess so.
One to debug with and one to be active.
Yeah.
Yeah. Okay.
For now, that's the solution that we went for, because we don't know how to handle those acknowledgements. I actually tried to handle them manually, but anyway, they are time critical, so that doesn't work.
I mean, if it's time critical, I mean, that is something I was thinking about for a while now. It might be possible to do that on the Linux side, but as a soft Mac implementation as well for the ACK. But I'm not sure if you really want to do that. I mean, the hardware is supporting that, and that's way more reliable than if you do it on the Linux kernel side, and then we might miss whatever one, and then you have to resend and so on. That would be not a good. But I mean, if we would have it, it would be a lot more flexible. So I know that, for example, all the RTOS systems, they often have like a soft Mac implementation for ACK as well, and they use it for like piggybacking extra data in the ACK frame back to the other device. So.
You mean they have acknowledgements handled in the Mac, in the soft Mac?
Yeah, but that's RTOS, so that's not on the Linux side. So I know that at least one, it was not Zephyr, not Riot. Anyway, there was some wireless sensor network coming out of academia. Contiki. There was in Contiki there was like a way of doing that, and then because I know they use that to like piggyback a bit of data back in the ACK frame back to the actually sender. So.
Okay.
So the practical operational side of this is that if you actually deploy devices into the field, right, and as you say, the one running Linux is probably the one plugged into the wall with power and the ability probably to have an SSH or something into it. So as soon as you have a network problem, of course, what do you want to do? You want to TCP dump Wireshark it, and the requirement that you then plug in another device to do that is it's a break. That's breaks, right? So somehow being able to do it would be really nice, and is probably operationally critical to figuring out why networks are broken when they're broken. Otherwise, people would just say, okay, this sucks. We're going to go back to, I don't know, BACnet or something, right?
But I mean, it's not really that easy to do that. I mean, we have been, I know what you mean. And I mean, for my development purpose, I just plug in another HUSB and run Wireshark on it. But I completely understand why you want to have that for a deployment scenario where you see that's a problem. But I mean, it's very hard to get that all right in the Linux side, where we have like one PHY exposed with like no filtering at all, like to get all the data, and then one where all the names and so the filters are set correctly to like make sure. So you have to see, but I mean, it's work in progress right now. We see what comes out of that.
All right. So the two last problems that we've had, and they are fixed, but I don't really like how it's today. So it's with the log dep, and bottom line, the RTNL is a pain. So for scanning well, scanning involves having a background job that changes channel, well, in the background. When changing channels, we need to acquire the RTNL. When we are in this background job, we need somehow to protect the structure that describes the background job, because it can be asynchronously accessed by user space through the netlink commands. So we also have implemented a lock there to protect this structure, which makes a dependency between the two. And of course, the RTNL must also be acquired whenever you start a scan or do whatever else with the channels, just because right now, as it is implemented, you don't have any other choice than acquiring the RTNL when you need a net device structure. I know in the wireless subsystem, it's been removed. This, well, in some places it's been removed. In the WPAN subsystem, it's not yet the case. So we had to find another way.
Did you find a way?
Well, yes.
Okay.
It's a bit crappy. I just acquire the RTNL at the top of the background job for now, and then I acquire the scan lock. I know the scan lock is not really useful in that moment, but at least it shows where it should be taken. And if we ever remove the RTNL at some point, we might not have any other issues with the locking thanks to this scan lock that I've already introduced.
Another possible approach would be just putting things into a work queue structure of some kind, because then they will be asynchronous. There won't be any contention, and because you've ordered things properly. So that's just one alternate approach.
Oh, you mean not depending on the RTNL, because you create the request somewhere else in another deferred work queue?
Yes, yeah. And then so if you queue access to this thing, you've obviously done your mutual exclusion that way. So.
Yeah.
I mean, the idea would really to be also to get rid of the RTNL stuff in WPAN, like wireless is doing it basically. But we really, yeah, that means basically someone needs to sit down, look at all the stuff, and make sure that nothing bad is happening if you are going to remove that part. So yeah. Maybe I think like getting your work done with like as you said, like taking at the top of the process. That's okay for now, but we really need to make sure that we figure that out. Sorry.
Do we have time for the last one? This one. So yeah, the last locking issue that I had was with the work queue of the device. So the device already had a work queue which I used to queue my background jobs. The problem is, of course, now I take the RTNL in the well, I have to take the RTNL in the background job, and the work queue itself also has a work queue completion lock. At stop time, the RTNL, of course, is taken, and within the stop callback, we also need to flush the work queue. Flushing the work queue involves acquiring the work queue completion lock. Well, at least that's LockDep told me that it was taken, so this could not work. So what I've ended doing, I think it's fine, is creating a second work queue just for the Mac commands. And because I know in my implementation, we can no longer have any background job for the Mac commands running when we stop the device, I don't really need to call the flush work queue call. So I no longer have this dependency. I suppose that would work. Okay, great. Yeah, I'm fine. So thanks everyone for your attention. And if you want to talk about that, I'll be there today.
Thank you. Peter, your turn now.
Well, while you're changing, I just wanted to say that I think we just need to find a way to have more people involved with the 802.15.4 stack, and I can't keep up with Miguel's reviews. I stopped trying. I'm sorry, but somehow we need to have a bigger group of people with the code swapped into their cache.
I absolutely agree. So it's kind of ironic because I had worked at a company 10 years ago that had done most of this stuff, but it was not a very open source friendly company. It was a Zigbee outfit.
Right.
And so that was never upstreamed. It was never a priority. But I think a lot of people are moving towards the Matter framework now, which is a little bit more friendly, I suppose.
Yeah, but it's a year late.
Yeah.
So the spec's a year late, and it's not very, yeah. It's
Stefan knows all about that.
Perfect. Yep. Hi, folks. My name's Ped Robinson. Bit about me. I've been Linux user for some time, working on ARM and sort of embedded edge IoT devices since around 2010. Been employed by Red Hat doing various different roles since 2012. And for the last 6 years, I've been the lead of device edge and IoT. So why am I talking about wireless? I'm co-maintainer of Linux firmware in Fedora, one of the ARM64 leads in Fedora. I've worked on numerous edge and IoT devices, like literally hundreds of them, with upstream Linux generic distros, worked with Linaro, ARM, and the wider ecosystem on like device standardization, system ready, all sorts of other specs. This talk, it's not a rant. I want to have a discussion. The wireless experience, and in this case, I'm mostly talking about Wi-Fi and Bluetooth. It's generally just not pleasant. The amount of regressions we get, the amount of devices that just don't work out of the box is just astounding. So the main ones I deal with, the Intel Wi-Fi, the Broadcom stack, which is now a group of 3 different companies, the Marvel ones, Realtek, Qualcomm, MediaTek. So why are they bad? The Intel stuff used to be the best Wi-Fi for Linux. It might still be, but we end up in situations where they'll ship a Bluetooth firmware update and suddenly like hundreds of people in Fedora can't connect to Wi-Fi anymore.
Who is they?
Sorry?
Who is they? Is it a hardware vendor update or a kernel firmware update?
No, like the Bluetooth firmware update that Intel ships and sends to Linux firmware. And so you'll reach out to maintainer, oh, but it's fixed in Next. But we're at RC1, so we'll see like Next land in the next 6 months. What are users supposed to do between then? And they're like, oh, well, just don't update Linux firmware so regularly. But the GPU drivers need new firmware for the latest GPU hardware. Am I supposed to split out hundreds of things and ship everything separately? They also just like randomly stop supporting the older devices and firmware updates. I'm sure there's CVEs. I have no proof, but it's interesting. It's just like, and like in the case of like Bluetooth updates breaking Wi-Fi, I'm guessing it's because of coexistence, but nobody knows.
I'd just like to point out in Zephyr, we do actually list CVEs that are fixed. So, you know, message, use in your firmware.
Broadcom Wi-Fi, the menage a trois, also the good, the bad, and the ugly. So back in 2017, Broadcom sold their IoT wireless division to Cypress. And then in 2019 or 2020, something like that, they sold their IoT wireless division to Synaptics. Interesting how they can sell it twice. They kept the Wi-Fi for their high-value customers, also known as Apple and Dell and other, like the tier 1 vendors, basically. So when that happened, we managed to get a discussion with Cypress and came to an agreement with them that they would ship generic firmware for Linux firmware that was maybe not the most optimized firmware for all the devices, but would generally work across all the regions and people could get wireless firmware that would work. They would ship us new versions every quarter, dealing with CVEs and various other bits and pieces. But then they were bought by Infineon, and the people we were dealing with stopped replying to emails, or their emails would bounce. So I don't know whether that was legal or they made redundancies or people decided that they didn't want to work at Infineon and moved on to bigger and better things. Broadcom sort of ships wireless firmware for the parts they still support, except when they don't, or there's a new one. And every time they need to do a firmware update, they apparently need to go and engage with legal to get release. I mean, why not just have a generic agreement with legal where you have a process which legal agrees is fine and update regular ones? You know, I've seen quotes on the list where they say, oh, but it's not affected by CVEs, except that, you know, your site lists all these CVEs. Oh, but that's a different driver. Can't tell me that the firmware is completely different and that it won't use the same code, even if it's a slightly tweaked firmware. You know, and other vendors, and like literally the firmwares that you can go and get for theirs has like a line in there basically saying it's not redistributable. Then we get Synaptics. Well, they're ugly. I spoke to one of the high-level people within the Synaptics wireless division at a conference in London. We don't sell to Linux vendors, so we don't have to support firmware on Linux. Well, that's interesting. I have at least 3 or 4 devices sitting on my desk that have your parts in there. Oh, that's not possible, sir. Bullshit. And then just don't even start me on their Bluetooth. It doesn't work. They don't ship firmware, any of them. In the case of Synaptics, I've been working with vendors. Like one of the things of dealing with Edge at Red Hat is that I'm speaking to vendors that are selling devices or planning on deploying thousands of devices, millions of devices, even a couple of customers that are looking at devices running Linux in the hundreds of million ranges. Funnily enough, when they want to run RHEL, they actually listen to you about what hardware is and what hardware is well supported. I've had vendors that are changing Wi-Fi interfaces to ones that are different. So this is going to affect your bottom line eventually. So, you know, come and engage with the Linux ecosystem. Moving on to Marvell, or is that NXP? Or half a dozen other companies that resell their parts. Upstream only supports old hardware. Again, Marvell sold their IP to NXP, but Marvell is also still producing new IP. Sounds familiar. Similar IP, similar firmware, not quite the same. You know, it's horrible. Like NXP doesn't support anything at all upstream with regards to this stuff. The Marvell stuff seems to be mostly just kernel-wide updates for locking or various other bits and pieces. Realtek, another piece of hardware, another driver thrown over the fence into staging. In some cases now they just don't even bother. The new, you know, RTW8889 has support for PCI, but not for USB or anything else. Still no firmware for lots of the modules. And the ones in in staging are mostly just abandoned. Firmware, when they do update it, regularly regresses, random devices, sold in tier 1 vendor laptops and things. All the rest are no better. Firmware regularly regressing on stable releases. Firmware regularly just crashing because, you know, someone's deemed to use something like WPA3, 5 gigahertz, or, you know, maybe if you've just looked at it the wrong way. How do we fix that? I don't know. How do we fix vendors? how do we encourage them to care generally about Linux users? How do we remove the terrible Stockholm syndrome with Linux Wireless?
I have one suggestion. I mean, like these vendors, they have hardware. They can donate hardware. They can donate money to set up like an actual continuous test service and system. And if something's broken, like if you get a regression, shoot the person an email, make someone accountable for that, right?
Yeah. So like as soon as I get a report, I email the maintainer. Sometimes you'll get a reply 3 months later. Am I supposed to stalk them? Like there's literally...
Well, it's got to be bad advertisement. It's got to be on the web. People have to see like, these are the vendors who are causing regressions and like have like a score, have like a top 10.
I mean, I've considered for some of the vendors actually just like submitting patches to the wireless mailing list to move the whole vendor driver to staging to like start a discussion about it. And like it won't achieve anything, but at least like people will start to be aware.
So I actually play with all the wireless stuff pretty extensively. I like know which one is better. But for MediaTek, have you actually had like a lot of issues with their recent stuff, or?
Yeah,
like not the 7663s, but like the 7610s, the 7612s, the 7921s.
For the MediaTek stuff?
Yeah.
Yeah, off the top of my head, I don't know.
Oh,
like,
okay.
I would have to go back through bug reports and things like that.
Yeah. But they're generally, the USB ones at least are generally pretty reliable.
It varies.
It varies, yeah.
Well, and like part of the problem here as well is like, you know, the quality of access points are variable.
Yeah.
And so like, I mean, I've seen myself where I used to have a widely available access point from a vendor at home, and then I switched to a different vendor because it stopped getting security updates. And suddenly like 4 or 5 devices that I'd never managed to get working suddenly started connecting to the access point. So it's like wireless is hard because you've got a lot of variables, but like in the case of some of them, like you try and connect to an access point and the firmware crashes. Like it shouldn't be like, the experience shouldn't be that bad.
Hey, I wanted to ask, what is your experience with the Intel maintainer? Do they actually respond to patches? Because I never got them to.
So the Intel ones are sometimes like 3 or 4 months to get a response. And like the Intel driver, like about 5.17 regressed on a certain situation. And like we worked out that there was this new firmware blob that was shipped. And it turns out that this new firmware blob was designed to work with the Intel management engine so that it could use the Wi-Fi interface to send traffic. And then, so there was bugs filed and various other bits and pieces. And like eventually, literally only the other day, an update was said, oh, you shouldn't be enabling that. Oh, that's interesting. And then, so I started to dig through this. It had been tested on one wireless interface card, basically didn't work. And there's now been a patch submitted to that to basically mark that whole thing as broken. But, you know, in, say, Fedora, for example, we get a request from a user or someone to enable something so that they can use that functionality, but it regresses for everyone else. And so it's a balancing act and a problem. And it takes significant amounts of people's time. But even when it does, like, you know, and I was chatting to someone earlier today where they were just like, I'm so sick of the Bluetooth stack. It's horrific. It regresses all the time. And I went, yeah, no kidding. Like, you know, it's constant, like, and like I also co-maintain the Blues subsystem. I don't know what I did wrong in a past life. To like, I think I just like pain or something, but like, you know, the amount of times it all just regresses, like it is just a terrible experience.
Do you have any automated tests to track how those things break?
Well, that's really like, so Red Hat themselves, we have a wireless lab with Faraday cages and things like that. But it's changing so constantly and all the time, like basically have to get in a queue to get access to all the hardware to be able to run the tests.
Yeah,
And like, this isn't my day job. Like, this is something that I've ended up doing because I need this stuff for IoT and Edge. But so it's like, I don't have, like, I could literally deal with this stuff and deal with regressions full time. And
so that's why
not my
that's
job.
why I'm asking, because I'm from Red Hat to CKI project. We do continuous integration for the kernel. If your hardware is available in Beaker, you can talk to us. We can help you set up.
I'll speak to you afterwards.
Yeah.
So I feel your pain. I was the one who sent that patch for marking the IWL thing as broken. And this has been an issue for so long. I think I will encourage public shaming, as you were saying. I'm not sure it's going to help.
Yeah.
I have, like, Intel is not the worst, but we do
No,
get
they're
those
not
kinds
the
of
worst,
issues.
but it's not a pleasant experience.
Qualcomm Atheros don't really care. The firmware is a mess. Like, I know people who have access to the source code and refuse to touch it with a, like, poking stick. MediaTek is probably the most responsible vendor so far. Like, they at least write a good driver. I'm not so sure about the firmware problem. So I don't have a good solution. Just having CKI with the hardware would be nice. The problem is it's hard because you need to actually have devices connect. And there's this thing where different clients will trigger different bugs in different firmwares. So you really need to spin up everything and do.
Well, and you also need to, like, change the access point as well to support just WPA2, enterprise, WPA3, all sorts of other things. Like, you know, to be able to cycle it, you almost need, like, to be able to cycle both sides, like the access point side as well as the client side. And then you also need to throw in Bluetooth into that as well, and various other bits and pieces. It's a very complex problem to solve. And like, I've been working behind the scenes with vendors as well to try and improve the situation. And like, some vendors respond and go, well, give us a list of the clients that are buying the hardware. And it's just like, well, I don't have an NDA with you. I can't tell you our clients, but I can tell you they're taking pieces of hardware out and putting different pieces of hardware in. It's...
For the firmware thing, like, in the kernel, if a driver breaks, we revert the patch, right? Like, can we refuse to skip firmware updates and, like, revert them? In the case you said it's fixed the next, okay, until the next thing lands, we're just going to revert your latest firmware update because it broke something. Is that will that help apply pressure to vendors?
Possibly, and it's certainly something that I have considered.
Yeah, like, if we have a CI system that can catch it really early, we can sort of...
Yeah, and like, ultimately, this is why I put this talk in, is to start to do the public shaming as well, because I've tried the sort of softly behind the scenes, and, you know, it gets to a point where you just have to call them out on their bullshit.
So one suggestion I have on that we know we need carrots and sticks here, is I would really encourage you to do this talk with a little bit more graphic shaming, in a slightly less technical way. You know, there's dozens of these IoT or industry of things, etc. conferences, and I think you know, that list. You know, CEOs in the room will be like, oh, shit, I'm going to deploy 1 million devices on, you know, my Raspberry Pi variant. And I just bought chips from a bad vendor, right? So you said you have an NDA that prevents you from talking. The question is, who doesn't?
Yeah.
Right.
Well, and like, from a Bluetooth point of view, I now actually tell vendors, like, look at someone like Nordic and use Zephyr for the Bluetooth controller to interface to Linux, because at least you'll get a stable platform. and like someone like Nordic specializes in Bluetooth, and if they're not going to do it well, you've got a problem. But like that doesn't solve the Wi-Fi side of things. And it like I noticed like Nordic, and like you could put in like a which does Wi-Fi, but like that in itself brings in other problems.
Have you had any dealings with Atmel Microchip or Red Pine Signals, now Silicon Labs?
Like I'm aware of their wireless stuff. It doesn't come up that much with customers.
And like the quality is what, in your opinion?
I don't have any, so I don't really know, to be honest.
Thanks.
So, all of this came up this morning in the regressions talk too. And one of the, in fact, they asked, is there a kernel subsystem that is, or are there kernel subsystems that are particularly bad at regressions and dealing with regressions, and are there kernel subsystems that are particularly good? And Greg immediately called out Bluetooth as being the worst.
And I'm not surprised.
No, but one of the things that came up, again, the waiting for RC1 and those things, and that's been discussed and it's been problematic for years, but now that Thorsten's doing this regression tracking a little bit better, and you find, oh, well, there are patches here, and these patches haven't been pushed, and they haven't been pushed to Linux, and it's been 2 weeks now, or so it looks like there are becoming some slightly more formalized escalation procedures.
Yeah, I actually spoke to him about that this morning over coffee.
Yeah, so that's one thing that might help. The firmware is a little bit harder to deal with in that sort of a regard, but at least on the kernel side, we do have some methods, but somebody's actually got to develop the patch.
Yeah.
Of course, if somebody goes through the trouble of bisecting, the other option is using the hammer and just forcing a revert of the patch that introduced it.
So sorry to interrupt. We're actually at time, but I think this is like such an important topic, and I totally encourage you to public shaming, continuous tests. This is something that the vendors need to invest in. In any case, our next speaker, actually, can I get a round of applause for Peter? Because this is a recurring theme. Second, yeah, thanks very much.
I'll just add a short comment saying it's probably going to get worse with the firmware because there's also regulatory pressure to move more logic into the firmware.
Yeah.
We really need to solve that.
So our next speaker is remote. This will be Michael Welling from QWERTY Embedded. That was great.
Michael, can you actually hear us remotely? So if you can, you would need to take over the presenter. If you click on the plus button, you can take over the presenter, and then you can like either share your screen or upload your PDF. But first of all, you can actually make yourself audible or something, because we can't hear you here. Yeah, we are just still waiting for our speaker to actually join the channel, so stay tuned for a few more minutes. Hopefully we can get that sorted out. We need to get us somewhere here. Yeah, but I mean, I'm not going. I have no idea what he's talking about. Yeah, I mean, if he's not. Upload the slide. If you're familiar with this work, then maybe.
Michael is just getting online right now. He had some difficulty logging in again. This is kind of unusual. Oh, there he is. Good, good. Michael, you need to upload your slides to BBB if you can do that. Go to the plus button. And then I believe you can take presenter with the plus button. Got presenter now? He has presenter.
Hello?
Upload. Oh, I think we can hear him. Yes, there's Michael Welling. Everybody, let's give a warm welcome to Michael. He's remote from California. And just remember to use the plus button to upload your slides. And you should be good.
That'll take a second. Let's see here.
Hear you. I don't know if we have video yet.
Okay, hold on. Okay. Not seeing my slides on this list here.
Okay, so if you press the plus button to get take presenter. After that, you would like press the plus button again, and then you can upload the slides. And
Okay.
once you're doing that, they should get converted, and then they would show up in the system here. Is that possible for you to do, or?
No, I think I have it. I thought that, let's see, documents, downloads. All right, there we go. And then to be uploaded. Upload. Okay. Shouldn't need to convert it. There
Oh,
we go.
there we go. Now they're getting loaded.
Okay, and thanks very much, Michael. And just remember, I think I don't know if you have your video available. Is that on?
Let me turn it on now.
Okay.
Yeah, I thought I was going to go on in an hour. So.
So yeah, it's very confusing sometimes.
Well,
okay, I'll let you to it.
There we go.
There he is. Okay. Hello.
So, I guess since we're about 10 minutes late, we should start right away. So let's have at it. So my name is Michael Walling. I am an embedded systems contractor. I have my own consultancy called Incordia Embedded Design. I've been doing this for many years, and I usually do printed circuit board design and firmware and combination thereof. Today I'm going to talk about Libre Silicon, some of the projects that I've worked on in the space, and kind of how we got here and where we're going eventually. So we're going to talk about Libre Silicon in general. What is it? Why is it important? And how is it possible? Until recently, it really wasn't. And we'll talk about that a little bit. And then we'll talk about the role in IoT. And IoT is a big space, but it doesn't necessarily require the latest technology. So it kind of makes sense where we're at now. Then I'll talk about Pi 5, which is a the Libre Silicon project that I've been working on with the community for 2-some odd years, and talk about where we're at, what we're shooting for, and how to contribute. And then I'll skip over to the ICE5 wireless if we have time, and this one is like a small combination PCB, which uses Lattice ICE40 FPGA in combination with ECP5, or not ECP5, the
ESP32.
Yeah, my brain just went for a second there. But the ESP32 is the wireless component, and we'll talk a little bit about that and towards the end of the presentation. So for like kind of anybody that couldn't really figure it out, Libre Silicon is like, the final form of open hardware in that the entirety of the chip contents are actually available and inspectable and reusable. So if you have the Libre Silicon design, that means that anybody could take that and go to the fab that you designed that chip for and create new ones and make variations and all the good stuff that comes along with open hardware. This wasn't really possible all the way down to the silicon until very recently. A lot of things happen in the FPGA space, and cores and processors were all designed in RTL and then targeted towards FPGAs. But more recently, someone being Google, Skywater Foundries, and eFabless worked together to create an open PDK. And what happened with that is it allows somebody to have the standard cell design for a specific process that's actually fabricatable. So usually you have to sign an NDA, and then you have to go on and download some super secret PDK, and you can't really share the design afterwards because it has all these pieces that are, you know, proprietary. So people worked along with, you know, grants and other various, you know, entities put in money to build up tools and eventually release a PDK that is actually manufacturable. And the first one of its kind was the Sky 130 PDK. And I guess you're wondering why this is important, and it's pretty easy sell for an open hardware conference, especially one that's based on Linux. Why it's important. You're able to really reuse design and share freely your design. You could previously share the RTL being the high level specification, and that's usually Verilog or VHDL or higher level abstractions like Chisel, Spinal HDL. This is all shareable, but the core, the inside of the chip, you really couldn't share, not freely without breaking NDA. So this further allows people to inspect your design, and it just wasn't possible until more recently. And I'll talk a little bit about, you know, how they made that possible in the upcoming slides. So this is like the overnight success that happened over the course of many years, and so many contributors were involved in the process that it's hard to kind of list them all. But like, if you want to learn a bit more about Libre Silicon or Free Silicon, FOSSi is a good source, and the FSI Silicon Conference is also a good one. There's plenty of other places you can learn about it, but they have some good pointers from there. So how did they do this? So it came about in about 2019. Google was like dead set on opening up the process, making chips accessible to the world, and they forged a partnership with Skywater Foundry and eFabless to open up that process. So at the time there was this new thing, the Open Lane Flow, and it was funded by DARPA, I believe, and it allowed people to create designs from RTL to digital layout or physical chips in like 24 hours. Is kind of like the thing that they were going for. And it's essentially an open source version of the old-fashioned synthesis flow. So once they had that piece, you could make chips, but you couldn't really share them because the PDKs were still proprietary. So the team at Google worked with, I think it was Oklahoma State and other people to create a PDK that leverages the SkyWater Foundry, and of course the Foundry was involved, and they created a standard cell library and various macros, and there's a lot involved, and it happened kind of a little bit behind the scenes before it was released, and then when they finally announced the shuttle, which was even further, they said, hey, we'll make these chips for you for free if you open source the design, encouraging collaborators and people to come in and make their own design. So there are a lot of pieces that are involved in this process, and the important pieces came together with this flow, and for the first time, you were able to make an open hardware or Libre silicon design. eFabless shuttle program. I have some links down here that you can check out the various pieces. They're very important pieces that came along. I mean, eFabless's shuttle is kind of like the kind of the carrier for everything, and the original VLSI open source program Magic was used, and Magic was created many years ago. It typically targeted like an academic PDK, which meant you could design chips, but you really couldn't fabricate them afterwards. You could put PDKs into the back end, but they weren't free. So you could actually make chips with Magic before this, but it's really kind of the chip layout. It's like KiCad for chips. And OpenRoad is the kind of like the synthesis approach to go from your Verilog specification to an actual GDS, which is the kind of the manufacturing files for chips. So OpenRoad has a fork called OpenLane that specifically targets the Sky 140, and it has the standard cells for that process that were released to the public. And then, you know, the front end is uses Yosys, which was work that was originally done by Claire Wolf of Yosys HQ, and that was initially targeting FPGAs and the bitstream documentation and all that good stuff that happened isn't really leveraged, but the front end, the synthesis, and it also uses ABC from Alan Mashinko, which is really old. It's been around forever, and it's kind of the core of synthesis flows, and it takes the designs and maps them to some technology. Either way, there's a lot of pieces to the flow, and I can't really get into a huge amount of detail for each one, but we're able to take a Verilog file and create a chip from it, and that's the magic. And there's you know, a lot of pieces that went into this thing, and I can kind of show you that with the project that we did. And yeah, so what is the role in IoT? Well, these trailing edge nodes are older foundries. They aren't going to be making your flagship SoCs that go out on your cellular phone, but they are definitely capable of making microcontrollers and anything in that space. So, and 130 is particularly good for analog circuitry. The SkyWater Foundry used to be Cypress So it's plenty capable of creating a IoT device, and there's probably going to be the first type of hardware that's going to leverage this type of flow. And RISC-V is going to be there along with it because it is an open ISA architecture, so you don't have to pay any royalties for that. Along with the free shuttle, you can't really lose if you're not paying anything. So I had to try. Of course, turns out it's a lot more work than initially expected, especially to make a full SoC. So our goal was to make a RISC-V microcontroller that has the ability to run CircuitPython, mainly to get the specs that would be required for that, which is USB, and also you need a timer interrupts or further actual constructs to actually support CircuitPython beyond MicroPython. MicroPython can run on practically anything. We got it running on the Low 5 microcontroller, which was based on the Sci5 chip, and it has very little RAM and it doesn't have a lot of the fancy features, but it definitely doesn't have USB, and that's what we're looking to contribute. And that was the first thing that we taped out, along with some other simple peripherals. The overall goal of the project really hasn't been met yet, but the tape out of the USB core actually did happen on the first shuttle. So it was just the tape out of the USB core and a couple of simple cores like UART, and there was a video core and a PDM, which is a pulse density modulated output, so you can make analog output. And the funny thing is, we really were only concerned about the USB core, but it turned out the only thing we can get to work were the filler cores. And you can learn about the project with the links down here. And once we found out the MPW1 had some hold time violations, it was kind of a sad thing. And we thought, hey, there's very little chance we're going to get these chips working. And but we pushed on anyways, and my group actually developed a post-mortem carrier, which was something that allowed people to bring their chips designs up, sort of. So there was an Icebreaker FPGA that was plugged into this board that would control the voltages to the core and allowed you to tweak the voltages until you had closure on the timing. And there's a video on this if you wanted to take a look, where TNT, which is the main contributor, actually brought up the chips and actually demonstrated the RISC-V core and everything running. So when we were waiting for the chips, we also developed a CircuitPython port for an ESP5 version of the chip. It had PSRAM working, and it was one of the big things that we needed to be productive in CircuitPython is memory, and you really can't put a ton of memory in these. So we wanted to bolt on in the PSRAM core, and it became the heap of the implementation. So yeah, this was actually designed by Greg Davil, pretty famous Australian developer, and he was just kind of like, hey, could you do this for us, when he was doing his advent of hardware design. And then we took and ported CircuitPython to that. And, things kind of slowed since then, because there's been a lot of hiccups with the shuttle, and we're just trying to get everything in place before we contribute again. So it's openly developed on GitHub and my Discord server. If anybody wants to get involved, there's a link for that. And also the Pi5 ASIC, we launched a simple funding initiative to try to help pay for the developers. This is it's not like everyday work. It's actually like a job after a while because there's a lot involved. So I wanted to make sure that people weren't losing time. And you can support that through that, as well as going into the Caravelle / Open Silicon community and contributing more directly. And there's a Slack for that. And of course, you can follow people like Matt Fenn on Twitter, and you'll see the latest. He's proprietor of a Zero ASIC course, and Tiny Tapeout is the new cool for MPW7. So there's been a lot of people showing off there, and it's really neat to see the software developers and people creating new things that weren't really possible in the not too near past. Or so that since we do have very little time, I could talk about
Michael, I think staff for this is lunch, so you're free to just go over by 10 minutes. Don't worry about it.
Oh, okay. Yeah, yeah. Okay, so ICE5 was a collaboration that I did with Eric Brombo, and it is a simple combination of the ICE 40 up 5K FPGA and the ESP32C3. The ICE5 kind of tells you that it's using the ICE5 or ICE40 FPGA, and also that it's got RISC-V somewhere in there. And the Espressif ESP32C3 is their first RISC-V offering, and Espressif actually moved towards using RISC-V for all the designs. We learned a little bit about the kind of limitations of this chip. It's a lot less powerful than their previous ESP32 designs, but then again, it's more than enough for programming the FPGA wirelessly, and it's plenty good for that. It's not going to stream super fast to the device. There's not a lot of peripheral I/O. I mean, adding that FPGA really makes a more productive actually implementation. So that there's the Espressif IDF or their SDK, and then for the FPGA side, we use the OSSHQ open source toolchain, and that allows us to develop IP for the FPGA with completely open flow, which is very nice. And then we have, the design is in KiCad and everything it's out there in the world for everyone to see. It was completely transparent the whole time, and yeah, it was actually one of my more recent developments. So there's some links down there for those things. We've actually crowdfunded this guy on GroupKits, and you can't really buy them anymore. The campaign closed, but there will be some available beyond the ones that were backed for the campaign shortly after the campaign is fulfilled, which is happening soon. They're actually in manufacture right now. And yeah.
I have a prototype I can show later on if anyone's interested. Take a look. Sorry.
Yeah. I sent Chris one of the prototype boards because he was actually doing the support for Zephyr, which is a really nice addition, and it really kind of rounds off the support for the board. So yeah, there was a lot of people working on firmware. Eric himself, he put in a lot of time with the bare metal / MicroPython support, and he also provided Arduino support for the ESP32. I actually brought up Rust on the board, which was relatively straightforward because there's somebody that did a port for it. And for Zephyr, we actually have Zephyr support for both the ICE40 and the ESP32, if I'm not mistaken. So there's going to be a soft core that will be thrown in here, and then you can run Zephyr on both cores. It's really not necessary to do that, but it's also nice to have that option. So you have a soft core that can drive the PMODs in a productive way. So PMODs are the actual outputs of the FPGA are here. There's a few spare IOs for the ESP32 over here. And then they're interconnected to so I could say I can run a script that actually programs the FPGA wirelessly, and it's kind of like the cool factor or whatever. So there's been a lot of work on the firmware on the ESP32, and I've been doing a little bit of working on trying to make more demos for the FPGA. I got the Nintendo NES running on this more recently, but there's I want to do a Doom port so they can actually do something cool like that. We have a PSRAM on here that we can load up with various things and use that to drive the core and any cores that are inside of this FPGA, etc. So yeah, it's a work in more finished work in progress. The software is really in the gateware are kind of where the contributions can still happen, and I definitely it's all community based. So come on down. Essentially, we have the open GitHub repository, which has a group of repositories, my Discord channel, and of course there's my Twitter. But yeah, if you want to collaborate, it's probably best to use the GitHub and Discord, and then you just kind of show off on Twitter. It's kind of how I do it. So that's kind of like the rundown of ICE5 wireless, and it'll allow people to kind of design new IP for the FPGA relatively quickly, and enable like wireless apps for FPGAs that really weren't a thing in the past. So yeah, and that pretty much does it for my slides, which would have left about 3 minutes for questions at the end. So if anybody has anything they want to ask or contribute, that'd be nice.
Hello. Sorry. Sorry. I'm from England. I'm from Taiwan. Actually, I'm secretly admired your work for a long time. And I have three quick questions. The first is how is the MPW7 status? And the second one is is there any kind of roadmap that you can break down to be kind of a GSLC event so people from around the world could join you? And the third one is that as far as if my memory serves me right, that there is some kind of the ICE40 Linux provided by TNT. Is it possible to run the Pi 5 configuration in the future?
Yeah. Okay. So sure. So the MPW7 just actually is about to be. I think the submission deadline is the 18th, so it's about to close. Our Pi 5 design is probably not going to have a submission there because we just didn't have we couldn't get together the funding / resources to pull together to submit for 7, so we're probably going to push it out. But MPW7 was kind of an interesting shuttle in that it was the first shuttle that had the tiny tape out, which was, you know, it was a way to allow like very new developers to design circuits with a graphical interface and actually have their chips fabricated alongside a bunch of other people. And it's going to bring in, you know, people that weren't able to contribute in the past. It's like you don't have to set up the tools. You don't have to do anything like magical to get it to work. You just send either like a design or a Verilog, and then it used GitHub Actions and Magic in the background to pull the design to GDS level, and then it would be integrated behind the scenes so that the people that are working on it don't really have to know about that. Of course, they need to know a little bit because the scan chain that's used to feed all the designs and all this other stuff is really, it's not going to be completely transparent. But yeah, so like our design, we spent a lot of time waiting for the RAM support. OpenRAM was the kind of the generator for RAMs, and it hadn't really been available beyond like one block, and we used that one block in our first application. And there was some work in characterizing the RAMs and making sure that they worked, but there isn't a whole lot of like variations, and we needed a bunch of different types of RAMs for a microcontroller, for the caches and, you know, the main RAM and buffers and what have you. So we wanted the support to be there before so we can explore the space and find the right RAM sizes. So we're still kind of waiting on the results for that. Those have been taped out. It just, not all of them have been verified. Yeah, and it's really hard to find time to do this. I mean, making a chip in your spare time, I found that wasn't really that easy. If I didn't have TNT, I wouldn't have been able to do what I'd done so far. I mean, he pretty much did the majority of the actual work on the project. I appreciate that greatly, and his developments really helped the whole community, and I just kind of facilitated and made too long, didn't read kind of things, and just made sure that everybody was kind of like happy. So yeah, MPW7 we're probably going to push until MPW8, which is sad, but then again, it's, yeah, these things aren't happening lightning fast. You send out for a shuttle and you wait almost a year before you get chips anyways. So it's good to see those other designs on the previous shuttles come through, and they can show people like there was on MPW2, which was the one that just recently got shipped to the second shuttle participants. That actually had some further timing hold issues on the IOs. So there's some work on trying to figure out how to make something productive of that, and then roll in what's necessary to eliminate those violations in the future shuttles. And it was for the first hold time violations in the actual core, which is, I guess I could show you.
Michael, I was just going to mention, so I think you brought this up at the beginning of the talk. This is Chris, by the way. But really, there are so many parties involved in making both of these projects hugely successful.
Yeah.
But the first one is obviously like what a lot of people refer to as the commoditization of the synthesis toolchain for FPGAs, which is, I mean, Claire Wolf, Yosis Next PNR, and of course like F4PGA. But then Skywater 130 is just, it's like a godsend, because I remember 20 years ago, it was prohibitively expensive for a starving student getting to university, you know, and it's just incredible. I think we're a little bit over time, so maybe we'll do one more question and wrap it up. But I just wanted to personally say thanks. So this is I mean, to everybody involved in TNT, Eric, Greg, everybody. This has been pretty amazing.
Yeah, the big players are Clearwolf, Tim Edwards, Tim Ansel, Mohammed Kasim, Mohammed Shalom. There's a lot of people involved though. Is a huge coordinated effort, and it wouldn't have been possible without all that collaboration. So like this piece down here is actually the core, that the RISC-V core that the whole shuttle is actually given, and then our design goes in this little section on the top there. So this RISC-V core, the initial implementation was based on the Pico RISC-V, and that actually went through on the first shuttle, and then they've switched over to VEX in the same area for subsequent shuttles. But that gives you like a RISC-V foundation for, you know, driving and analyzing the design that you put into this space. They have variations of this carrier for analog. So if you want analog pins, they just strip back all the niceties of the pad so that you can have, you know, more bandwidth, less restrictions on those pins. There's been a lot of work. Some really cool work that I saw recently that is very relevant was there was somebody that created a 5 gigahertz transceiver, and there's a RISC-V driving that. I forget what was the name of the project, but that I saw on Twitter recently. And when asking about Linux, there are actually a few designs that set out to do that as well. Pi5 wasn't thinking that, but if we enable certain features in the VEX core, we could definitely run Linux on the ICE-40 shuttle.
Okay, just a quick, does anyone have any last questions, like a short one, or? Okay, well, in that case, let's have a round of applause for Michael and everyone involved. Thanks again, Michael, and apologies for the technical difficulties, but it was great that you were able to make that work.
Yeah, I'm sorry I was late. I put 8 o'clock on my because I looked it up I looked up the design time zone. I was like, okay, so it's 1 p.m. there, right? Is that when it's supposed to start? And I thought that was 8 a.m. here, but apparently it was 7. Luckily, I got up a little early.
Okay, well, it worked. So thanks again for your presentation, and we'll be in touch soon.
All right.
Okay, have a good one. Take care.
let me try. Earlier this year, we found a bug. So can you hear this clearly?
Yeah, it's better than before. Yeah.
Okay. So we found a bug in frequency invariant support on Intel platform, and Chenyu fixed it in 5.18. However, when reading this piece of code, we think there are more places that want further investigation, and we'd like to take this chance to share the problem we found during recent research. Okay, the first slide is about background. Let's read this chart from left to right. So first, as we know, the load balancer balances the load on different CPUs to optimize the overall throughput of the system. And when load balance is triggered on a CPU, we need to find out the busiest SCAD group and then the busiest CPU, so that we know which run queue we should pull the work from. At the same time, we need to classify the type of the SCAD groups. For example, we need to know if a group is overloaded or not, or if it has spare capacity, etc. The U2 average and the load average from the CPU CFS run queue are used as import inputs for this purpose. And then this U2 average and the load average are calculated by the task size in a running delta time. Then here comes the problem: how to describe the task size. Before frequency invariance was introduced, we use clock task, which align to the running delta time. However, this has a problem. As described in the dotted box, clock task can be bigger if the task is running with a slower CPU frequency, and vice versa. For example, the same work can be finished in 2 seconds when CPU is running at 1 GHz, but only 1 second if CPU is running at 2 GHz. That says the task size is a variant based on the running frequency. And the frequency invariance is introduced to solve this problem. First of all, a scaling factor named arc-freq scale is introduced. It is called quotient of the current running frequency and the maximum frequency. With this scaling factor, we can get the scaled task size from clock task, and it is called PELT, which is invariant to frequency changes. In this talk, when seeing frequency invariance gaps, I mainly in problems related to the 3 red boxes in the right bottom corner. Go to next slide. Okay, we already know that arc-freq scale is a quotient of FreeCurl and FreeMax. FreeCurl, ARM and x86 has their own implementations. I don't find any problem during our investigation, so I will not go into details about this. On contrast, for FreeMax, we found that it can be run in many situations. This includes the cases when CPU is in turbo or it's throttled on hybrid CPUs, and also CPU frequency range changes. All the experiments are done on Intel platform. I will illustrate these issues based on the frequency implementation for Intel. But still, some of the problem may be x86 or Intel specific, while some of them should be generic issues. So let's go to details. Okay, this is the simplest and most straightforward way to trigger both FreeMax. First, we choose 2 CPUs in 2 different cores so that they can run at different frequency. And they are CPU 0 and CPU 2 in this case. And then we run duty cycle workload to keep CPU 0 and CPU 2 always 80% busy all the time. Finally, we limit the CPU 2 frequency via SysF interface at the 10th second. The left graph shows the running frequency. CPU 0, as shown by the blue line, is always running at the max turbo frequency. CPU2, as shown by the orange line, its frequency drops at 10 seconds because it's limited from SysFS. And the green line is the freq max the kernel uses. On Intel platform, the fourth entry of the turbo ratio limit MSR, you recall the full core turbo frequency is used as freq max. This is a static value as long as turbo is enabled. So the problem is that when the CPU frequency range changes at 10 seconds, the freq max is not updated. As a result, the graph on the right shows that the CPU2 U2 average drops because the kernel thought the task is running at around 1/3 of the CPU's maximum frequency. Then from the load balancer,
so is the freq max is the SysFS limit, or is it a different?
It's a kernel thing we use. It's basically it's concept, but we use arc turbo freq ratio something to represent this, and it is static value.
Yep.
Okay. So as we can see,
yeah. There are questions in the room.
Okay, yeah. I'm a bit surprised because normally the frequency invariance make that the utilization of your task should remain the same as long as you are not overloading the CPU. So even if for some point, if at some point you can't reach the max frequency, your utilization should not change. Otherwise, it means that it's not invariant.
Oh yeah. So the problem is that it is supposed to be invariant, but in fact it isn't.
At least what we have on ARM, even if you cap the frequency of your CPU, so the frequency will never go above this SysFS, but your utilization average will remain the same. As long as you are not overloading. I mean, typically if you want to run 90% of the max frequency and you cap to half frequency, I mean, at some point you will be over because you will always run, so you can't make any estimation anymore. But otherwise, you should not see that from the beginning.
Okay, you mean that if I don't use duty-set workload, but I use the fixed size workload, the problem will gone.
Okay, but yeah, maybe your problem is that you're running 80% busy CPU and then you divide it by 4 the frequency, which means that. And I can't even understand why you go down to you should go up to the max value.
Actually, one other quick comment is that this is like a okay, to take a step. My first point is that I think the behavior is correct, because one other case where somebody might limit the max frequency from SysFS would be for thermal. Sometimes user space will come and limit the max frequency for thermal. In those cases, we do want the utilization to be calculated the way it is today, because when you later remove the limit, you want the frequency to go back up immediately, because your utilization would have taken up all of the max frequency's capacity if you hadn't throttled it.
There is a question from Giovanni.
No, okay, but in this case, so you're saying that this is a correct behavior, right?
Yeah, you should.
Right. So sorry for interrupting. Can anyone look at the matrix conversation and see, and see if there are questions in there, and maybe repeat them. And so Giovanni, are you on the call? Yeah,
I see he raised the hand.
Giovanni, can you can ask a question if you.
So Giovanni said on the chat, FrecMax is set at a boot at a constant value, the one for the four-core turbo. It was meant as an heuristic. So it can't work on hybrid CPU, Alder Lake.
I also, yeah, so there is a mechanism to update it when we turn turbo on and off, but that's the only one.
Yeah, so that explains why your FrecMax is below the highest frequency CPU can reach.
Yep.
But that doesn't explain why you see that your utilization is dropped down to 250. This should not happen. At least it's not happening on ARM.
Oh, well, this is all x86 specific.
No, yeah, that's right. Yeah,
right
that's,
now. So okay.
But this, my understanding is, so I'd like to say that this is a duty cycle workload. So the task size actually changes. We just keep the CPU busy all the time, no matter what the frequency is.
Oh, okay. Okay. So you're always using 80% of the current capacity.
Yeah. The utilization, CPU utilization is 80%.
So in this case, that's normal because you are using 80% of a quarter of the Mac.
Yeah,
so that's
right.
why you're there.
Yeah.
So your util average is not underestimated in this case. Correct.
Yeah, that's what I was about to say. It's working exactly as it's supposed to work.
Yeah.
So the example is not the best one, probably.
The problem is that what would this bring to the load balancer? From the load balancer of view, CPU2 has a lower utilization util average compared with CPU0. And the CPU0, if I put a load higher, the CPU0 can be overloaded. And CPU2 has capacity. It can be classified as has capacity.
But if you look on CPU0, the task is doing 4 times more things than on CPU2. Though, so that normal that util average is 4 times or 2 times or 3 times, I don't know.
So
I think that's correct.
I think that instead of discussing this example, because we only have like 10 minutes more for this topic, let's just go and talk about the problem, and then we'll see how this is related to the example or not. Because we are spending too much time here.
Okay. Let's go through the slide first. Okay. So let's let's continue this one. So on Intel platforms, the problem is can be worse because we don't use CBPC and we use this static value, and the CPU actual frequency range can be changed in hardware. For example, we have the config TDP feature on client, and also we have the interspeed select feature on server. Also, this feature can result in the turbo frequency and base frequency change, and we never update it.
Okay. So do you have more slides, or is it just this?
No, yes, I have other slides.
Oh yeah, okay.
So
No. All right.
Okay, so next slide. Let's check the turbo and throttle case. This is a big problem in my opinion. So when frequency is in turbo range or CPU throttled, OS can only request the frequency without knowing if the frequency can be granted to CPU or not. And this is subject to challenges. A, FrecMax is unknown, and B, it varies over time. So if the problem in the previous slide is that the kernel does not update the FrecMax when needed, this problem is that kernel does not know what value the FrecMax should be updated to. And when the FrecMax we use in kernel varies from the actual max frequency, problem comes. To illustrate the problem, we make CPU CPU0 and CPU2 be there all the time and put a load on the other CPUs starting from the 10 seconds. So let's check the graph on the left. We can see that the CPUs are running at max turbo frequency in the beginning, and then drop to focal turbo frequency, and then drop and then throttled later due to the TDP limit. And by the way, CPU0 and CPU2 are always running at the same frequency. So the blue line is totally overridden by the orange line. That's why you cannot see the blue line is the right graph, is the left graph. And we can see from graph that during the experiment, the FreakMax kernel uses can either be lower than the actual frequency or be higher than the actual frequency. What could this bring? If the FreakMax is lower than the active max frequency, the arc freak scale is clamped, and we may lose task size accuracy. So simple example, say there are two tasks. Task A takes running at 4 gigahertz and it runs for 1 millisecond. Task B running at 5 gigahertz and also runs for 1 millisecond. Apparently, B is bigger, right? But if kernel uses 3 gigahertz as FreakMax, then the scale task size for both of these two tasks are 1 millisecond running at 3 gigahertz. No difference, right? So, I have actually I have a full slide to illustrate this, but I can talk it later only if we have time. So if kernel sets the FreakMax too low, the real task can run at frequency higher than the FreakMax, and the task accuracy is lost. But if kernel sets the FreakMax too high compared with the active max frequency, the CPU can never reach the high frequency, and again, the utility will be underestimated. That's the previous one.
No, but yeah, that's so for the first part, yeah, I agree that if you go above the max frec, you will not see the difference. But I think Giovanni said it was a kind of a heuristic that have been chosen because you not always reach the max. For the other part,
may I
yeah.
speak? May I?
Yeah.
Can you hear me? Okay, I have
yeah, we can hear.
fixed my mic. Hello, Rui. This is Giovanni Gerdovic from SUSE. So you are correctly saying that the value of FreakMax is not adequate in all situations, but as you know, because you wrote in the abstract of your talk, you are aware that this value is set statically at boot, and it's essentially a guess because x86 has optimistic optimizations, and it's hard to know what the actual max frequency is at any given time because you may or may not have turbo, etc. So the presentation that you are giving is correct. FreakMax is possibly inadequate, even more so on hybrid CPUs. So I wonder what is your proposal to get rid of this heuristic, which in my opinion was very crude but necessary. What is your proposal? The problem is clear, in my opinion. It's a static value at boot, so there is not much to talk about that, I think. Please.
Okay. So you see my proposal, right?
Yeah. So Giovanni was asking what what you propose about dealing.
First, I want to illustrate. My presence was to illustrate these issues at the beginning, and we have some proposals. But for some problems, we're asking for comments and suggestions. And I have a slide for that. Yeah, maybe we can mention it.
Is this working? Do you want a proposal from me, or do you have one?
Oh, if you have one, that's great. Yes, I'd like to get it.
Okay, so if you want to know what the maximum frequency is, the only way you can really know is that you, in the case of this CPU where it's on auto, right? It's in turbo mode or it's in HWP mode. We're not asking for the frequency. We're throwing work at it. And if we run out of idle time, if we're 100% utilized, that is exactly what the maximum frequency is at that instant. So at any given time, when we have no idle time, we know in Linux, we can measure the frequency. We could change this 100 times a second if we wanted to, and have a very accurate picture of the recent history of what max freq really is. That's really the only way to know.
So on the max frequency being the turbo or the 4-core running, I agree that maybe this should be improved. On the fact that when the user space cap the max running frequency, this is already handled, and this, for me, the result is correct because you are using only a quarter of the available capacity. Now the user space cap that, and we have what we call, maybe the name is not correct, we have a thermal feedback, because usually it's the thermal things to say, right now, your max compute capacity is 1K, but user space or for thermal consideration, we have capped that to half or a quarter, which means that if your utilization is a quarter, because the other part is removed by the thermal, you are running at max capacity, current capacity, but not the max of the system if you don't take into account the user space.
Sure. Yeah, the user space cap is different than when the hardware does the limit, right? I agree.
Also, saying max frequency can change doesn't even make any sense. Max frequency is the max frequency you can reach at any point in time. I know what you're talking about, the turbo. I completely get it's opportunistically boosted. In my opinion, the maximum possible boosted value should be the max frequency.
But
And then
you may never reach it.
What?
You may never reach it.
Yeah, that's
In
fine.
practice.
So
No,
what?
it's not.
Why is it not? Tell me why.
Because if you have never reached it, then you'll utilization will be off. It's
Yeah,
not
and-
off uniformly.
No.
Yeah.
So okay.
And
So let's say 1
that's
gigahertz
why
is your current. Sorry, let's say
sorry.
1 gigahertz is non-boosted
Okay,
frequency,
go ahead.
and you can reach 1.5 for boosted. You can always set the max frequency to 1.5, and everything else will work correctly. When if you're running continuously at 1 gigahertz, we'll try to ask for 1.5. You might not
Yeah,
get
yeah,
it.
that's fine as long as you have, as you don't have hybrid system.
Maybe we can talk about that part. But even in hybrid, I'm guessing.
No, because then you can there can be so the difference for you say you have two types of CPUs in the system, and for one of them you reach like 80% of your max, and on the other you
But
reach 90%.
in ARM, we have a solution for this, right? We not only have frequency invariance, we have also microarchitecture invariance, and I think this can be just adapted by x86 to get rid of the hybrid CPU problem.
Exactly.
Maybe, I don't know.
I think we run it for years now on ARM, so
But
that should be fine in Big Little.
So yeah, okay. Well, we can continue, I guess, talking about this topic, but we are running out of time. So I would suggest, moving to email and offline conversations right now, and then let's move forward.
Just
Yeah,
one quick point. Sorry, go on.
All right.
Just thanking Rui for bringing this up because it is a relevant problem, and I was never really cool with that heuristic. So maybe we can make some progress. So thank you for bringing this up to LPC, Rui.
Yes,
Right. Yeah.
Just one quick point is that turbo frequency on ARM has also been done in previous chipset. It works perfectly, no issues with the current code. You
Except
just need
for
to
the
set the
thermal.
turbo frequency as the max frequency and everything works.
Except for the thermal.
Thermal,
feedback.
no, even thermal works fine. Yeah, you get if you get throttled on thermal, utilization is going to be lower.
So I will.
And with frequency invariance,
Let's
you can
go.
above
Let's go back to email. I will forward it.
for sure works correctly.
Conversations to you. Okay. Okay. Let's move on to the next topic.
Okay. Okay, this is the short one. So let me see. Next slide. Yeah. So problem statement. This small zone device register is widely used API. We use it to register small zone devices in many different drivers. And when it is first introduced, we have 4 parameters, and we add some, and remove some, and also add some. And whenever this happens, it's a pain. We need to update so many colors of this API. And if we check the parameters of the current small zone device register, yeah, we can see that many of them, these are just optional. These are just optional, and these are configuration data. It doesn't not necessarily apply to every small zone device. And but we already have a small zone parameter, this structure, which already have some configuration data. So what I'm proposing here is that can we do a clean up once and move these optional configuration parameters into this small zone param structure, and then we leave this API with fixed parameters. And for in the future, when we add new parameters, we just need to update the small zone parameter structure. We don't need to update those APIs anymore. Yes, this is small topic. Just see if this is something that we should do. And this is bad for maintenance, right? Yes, I don't have any more slides. Just this question. I just see if this can be moved to this one, and if yes, and which should be moved, so that we can make maybe we can make a cleanup for it.
Okay, so I guess the problem statement here is that we have too many arguments for thermal zone device register, and the list is growing, right, over time, or otherwise changing, which is not convenient because all the users have to be updated every time, right? So that will be
right.
And because of that, so I think that one way to address this would be to have a single pointer pass to thermal zone device register, and that pointer will point to a parameter structure where there is all information needed, and it can be extensible, right? So we could add more pieces to it as needed without necessarily updating all of the users of it, because which may not care about the new pieces. So the question, Daniel, what do you think? Is this a good idea or is it not?
Yes, I think it makes sense. Makes sense. That's why there is more and more parameters.
Right. So yeah, I guess we can start working on it, right?
Yeah, right. And then what about for these ones? So better we have a list of the new parameters in the new API. So for example, the type and the DB data, and also this TCP pointer. This is something we must keep in the new API. And what about this one? The operation callbacks. Can we leave it with the should we leave it with the new as one API, or can we move it into the small zone parameter structure?
So I personally think that there should be only one argument, and that the structure pointed to byte should contain all of the information.
Okay, just the one single parameter.
Yeah.
Okay, I got it.
That makes sense. I think that overall, in many cases, we are adding and then like if we have several drivers need to update at the same time and it's pain every time.
Yeah.
And if you have a structure, you can even maybe save the time of all seeding everything and use that structure in some list as is. Assume that user has the maybe put a requirement that user allocate real memory and gave you.
I don't know. That depends because then it will need to be allocated, and the caller would need to stick to it after having registered the device. But yeah,
It's
why
okay.
not?
Yeah, I'm not particular about it, but yeah, that helps. for the systems where you want fast boot in the boot up, because if you have like 30 sensors or 40 sensors, they take time.
Well, yeah, so especially if you have like a static definition, right? Anyway, where all the stuff is already populated.
Yeah.
Okay, sounds good.
Okay. Yeah.
Right. So this was easy.
Thank you.
This was easy. Thanks for bringing this up, Rui, again. Giovanni, can you please change it? Yeah, okay, thank you. Right, so that would be, I think, all about the second topic, right? Or is there anything else to add?
This is all about the second topic.
All about it. All right. So now we need to switch over to the real next topic that we have here, and that will be wait for 10 minutes. We can talk about the frequency invariance during the time.
I have a question just about this change.
All right, okay.
Right now I'm doing a rework of the trip points. You might see that there is a huge patch set,
Yeah.
30 patches. So that means that this rework, we do that before or after?
I think it doesn't matter at this point because we will need to change. Well, so if we switch over to a single, if we change, to a single argument, you will not need to change the users of the API anymore, right? At least the majority of them. So maybe it's better to make this change first and then do the trip points rework on top of it, because it may be cleaner this way. Because so for the majority of cases, you will be making one change instead of two, I think.
Yeah.
But I will need to look at at your patch set and see, because it all depends on what's less work, right? Like if we can reduce the amount of work by doing things in a certain order, then let's do that.
Yeah, okay.
That would be my approach. All right, so the frequency invariance. The real problem there is that we use the APERF and MPERF counters for computing the current frequency of a CPU on x86, or at least on Intel, and that ratio can be greater than 1. Now, the expectation of the scheduler, or at least the PELT code, is that the value is less than max, right? So, and that is why we have to guess the real the max freq. Yeah, yes, this is the reason. Because it may be made up. As I said, so you have several different turbo bins. Like you have a single core turbo, you have 4-core turbo, you have 8-core turbo, you have like several flavors. Which one you choose?
Also we change dynamically the power, total power. Very high rate. So
I'm saying pick the absolute max frequency you could ever reach on any of the CPUs, assuming. Huh?
May I speak?
You can. 1 second, let me finish. So you can, but the problem is you're going to end up with the resolution of your real utilization being between 0 to 10 if you pick 100 gigahertz, right? So what you're effectively doing by picking a max frequency is just setting what range of 102 your value is going to end up at. So it's okay if you reach the absolute turbo frequency only 1 second every day, but as long as that number is in like 100 gigahertz versus 1 gigahertz, you're not losing much by setting that as the max frequency. Basically, all you're doing is losing a little bit of resolution by setting the max turbo frequency. That's all you're like losing. You're not really losing anything.
And even if your task never reach 1 key util average, which would mean always running at max turbo max, you can I mean, how it's used in schedutil typically, if you have 900, mean that
say it may or may not.
Yeah, but no, I mean that the goal with the belt and the frequency invariance and the architecture invariance input is that you want a uniform classification of the compute capacity of the CPU. What is the max compute capacity you can achieve on your system without taking into account thermal, without taking into account some frequency slowing down and so on. That's the max you can reach. And everything is scaled by that, which means that wherever your task is utilization will be the same. Doesn't mean, which means that if you are running at the max capacity of your E-core, the utilization will be never above 500, for example, if you are doing some idle things. But that's okay, because 500 is the max compute capacity that your E-core can reach.
Okay, so now you basically are saying this as long as I have SMP. Okay, wait a minute.
No,
Let me finish. As long as we have SMP, we are fine. Even if we have we overestimated the max free, because in that case, we may not reach 100% of utilization, but then every task will be relatively smaller, so we don't care, right? But if we have a hybrid, then there are different turbo levels, and they in one case they are reached more often than in the other case, then we have a problem.
But that's why we have this micro arch input, which will be different for your E-core and your P-core, because obviously your E-core will never provide, even at turbo frequency, the same amount of capacity than your P-core. So even at your max frequency, so with for your E-core, you will have you are using the max frequency, 100 of the compute capacity, but the Arch CPU scale will say this CPU at max is only half of the P-core. So that means 500 of the system. I think that's what is missing for you on your
right. We've got an IPC difference. Even if they could reach the same frequency, the P-core is 30%
that's the purpose
faster.
of this Arch scale Arch CPU FREC, to say that you don't have the same microarchitecture. So even at the same frequency, you will not have the same IPC.
That's exactly what you do in your test tool when you calibrate.
And both of these are mainly to avoid clipping, right? Like if you set the whole point of the upper limit you're setting is just to make sure you don't clip the utilization.
Yeah, okay. Let's let Giovanni talk.
Thank you. I wanted to recall and say my point of view of why this static value was chosen. I see that in the audience there is somehow the belief that we could just set the maximum turbo level for the of the CPU as the max FREC, and there wouldn't be much loss. So I'm happy to learn about this MicroArt part where we could give different FracMax for the different kind of cores. So that's definitely the route to go for Alder Lake. But the presentation by Rui, I believe it's not based, I mean, it describes Alder Lake as a possible challenge, but even on the current status, Rui is not happy. And the reason this was just a constant and not the maximum turbo level is, as we all know, the opportunistic Intel optimizations are so that there is not enough power to have all cores reach the maximum turbo, obviously. And so if you set your max frequency to the maximum turbo, you would have some cores that always appear severely underutilized. Because that is that value is used to compute the share of utilization, and the turbo on x86 server CPUs sometimes is double the maximum non-turbo P state, so it's a large margin. And I mean, you have Len Brown in the audience. There was no simple way to understand what is the actual capacity at this time of the CPU. Someone here says just give it maximum turbo, but in my experiments, we were severely underestimating the capacity of some cores, and because the difference between max non-turbo and max turbo is very large, and turbo is not available for all cores. So this was the reason of that constant, static constant. Thank you.
There are a few points I want to kind of clarify to make sure we're on the same page. The architecture capacity is nothing to do with the max frequency each of the CPUs could reach. It's trying to say for a given exactly same frequency, what would be the performance difference between your performance versus your efficiency core. So at 1 gigahertz, if your efficiency core would be half as performant as your big performance core, then the value needs to be 512. And for the big core, or your performance core, it will be 1024. That's what it's trying to do. It's completely independent of what frequencies each of the CPUs can reach. And the other part is you have, for a frequency range, it goes from 0 to 1024. So you're effectively saying you have the resolution of 0.5%. Like, as long as you don't have 1,000 frequencies, you're not going to lose much because, yeah, I think you get the point, right? We are saying from 0 to 1024 is the number of levels we can kind of accurately model. And as long as you don't have that many frequencies, I think you're okay.
What you're saying is that the turbo can be twice the max at 4 cores. Is that the point? That can be we can have that huge difference. In which case, I can understand from a load balancer point of view, in order to define the CPU as overloaded, the utilization should be above, I think it's 75 or 85% of the max capacity. But now I agree that if your turbo is twice more than the usual max frequency, you will never reach or hardly reach this 85%. You will never be set as overloaded, and you will never trigger the overloaded load balancing. Yeah. So in your case, if there is such difference between the turbo max and the 4-core max, I agree that the assumption that 80% of the utilization means overloaded is no more true for you, because the overloaded case is much lower. That's probably one of your problems for the load balancer point of view.
Yeah,
sorry?
We have 5 times all in some cases. So your guaranteed versus max can be up to 5 times, and also we can change. Guaranteed can change so fast that that's why what Rui is saying is, as you are saying, that there can be huge difference in calculation.
Okay.
Yeah.
I think we need information about what you can actually achieve at a given point in time, and that's where you mentioned thermal pressure earlier. So ideally, if you can't achieve your turbo frequency but achieve something less, you need to know somehow that it's unachievable to get there. So you consider the CPU overutilized already at a lower point.
That the possible, yeah.
Of course, if your max frequency is changing wildly all over the place all the time, it might be difficult to track.
So actually, so we have made a problem essentially, because the problem is that we need to guess a value so that we can overcome the issue about A-perf over ampere being greater than 1 in some cases. Because if that value could be greater than 1, then we don't need the max. We just pass the value and be done.
Yeah, but you still do not know when your CPU is actually fully utilized or not. Is it fully utilized? Do you not have any spare cycles because your hardware can't go any faster, or
I
just
agree,
because it
but
has an increased frequency?
I agree.
You need that information.
But yeah, okay. So we ran out of time for this twice already. Okay.
Quick comment. So Linux does know when we are fully utilized because there's no idle time. We know when there's no idle time by definition.
Yeah, that's a good criteria.
We do know that.
So can we always assume that Intel hardware will run as fast as it can? It will never ever get to a situation where there is no idle time where it could actually run faster. Is it?
Well, Len, but no. This is but let's just go offline with this, because we can continue for the next hour here, and we have other topics. So
just one minute comment. Like just sorry. So
right.
less than 1 minute.
Last one.
Yeah. So if I give you an interrupt every like few hundred microseconds and update the thermal pressure, is that what will be the impact of it? I know I can compute and I can send you that you're reduced every 550 microseconds. Is that okay to have for scheduler?
So you mean in the interrupt context, that's even not taken into account in your clock task, so it's not visible from a task point of view.
Yeah,
that's another compute capacity scale. We have two compute capacity scale. What is stolen by interruption, and then what remain, how you split that between the task.
Okay, I see.
That's even more complex with we have another dimension with the IRQ. Otherwise, that would have been easy.
That's what we get IRQ on lots of cases when we limit something, but we don't take it because of a lot of other things, too much. Yeah. Okay. Sorry, Rafael. Yeah.
No problem. All right. So we'll have a small break still. So to comment on the utilization until we are waiting for the mic. So the frequency scaling is about making things 100% utilized all the time, because it adjusts frequency so that that there is no idle time. So because this is the whole point right now. So that we cannot really say that this is that we are we cannot use this as a criteria for saying that we are run as fast as possible.
Okay.
Right. So yeah, Daniel.
Okay. So yeah, it's a quick presentation about the idea of combining the DTPM with the thermal framework. So DTPM stands for Dynamic Thermal Power Management. So today what we have is this kind of architecture. So we have CPUFREC, DEFREC, in order to send commands to these subsystems. We use the PMQS, which does an aggregation of the request if there are different clients asking for different things. And then we have the PowerCap framework, where the DTPM is built on top of. And then we have CPUFREC cooling device and the DEFREC cooling device. If we provide an energy model, then the DEFREC and the CPUFREC cooling devices can use this energy model to do mitigation, thanks to the intelligent power allocator we have in the thermal framework. And also the DTPM is using the energy model if it's available, or also it's planned to use other kind of mechanism if they are available, and if we can give the information about how much power consumption we are doing, and what is the power limit. So today what we have is we have code duplication and also the algorithm between the CPUFREC and DEFREC cooling devices, because those are doing power consumption computation. So they are trying to read how much power we are consuming, and then it sets power limit. In order to do this power limit, it computes the performance state, and then it sets the performance state through the DEFPM QS. And DTPM is actually doing the same math, except that at the end, what we have is this interface, CSFS interface with the user space, where we can directly act on the power and setting and getting the power. So we have this mixed. So there is a mix for CPUFREC and DEFREC. So if the energy model is not available, we go directly, we provide the state. And if we have the energy model, then we use, and the power allocator, then we use the power computation to do the request and having the state. So it's the mechanism is the same for DEFREC and for CPUFREC. The DTPM is doing the same thing. So it's computing from the power, it's computing the state, conspiring state with the energy model, and then do a request with the state. So the idea here is instead of having this duplicate things, we can say, okay, CPUFREC and DEFREC cooling devices does no longer have any power computation inside, and we move that inside a dedicated power cooling device. CPUFREC and DEFREC cooling devices will be used only by the stepwise governor, while the power cooling device will be used by the power allocator governor. And this one can use directly the DTPM, where it's an unified interface. And because it's an unified interface, whatever the device we have, which is capable of doing power capping, we can be able to access directly with this power cooling device. So we have a generic cooling device being able to handle any devices using this DTPM framework. Also, the DTPM is planned to evolve in the future because there is a hierarchical description of the different devices, so we can allocate a budget on the parent of the group of a group of devices, and then by setting this power constraint, this power limit on the parent, then all the children will change their power in order to always comply with the parent's constraint, where the sum of their power is never greater than the parent power limit. So that means we can easily just plug for a thermal zone with a group of devices and let that handle the cooling easily with this power balancing. The power cooling device will be also very simple because we will just have a couple of, well, basically it's a couple of functions, which is in get and set power. There is no state, it's just get and set power. And also the DTPM is returning the effective power limit. So if you ask, for example, for a certain power limit and the step between the different performance states, we are right in the middle, then it won't make sense to put on the upper state for this upper performance state, but on the lower performance state. So we have a remaining power, and DTPM is returning this value. So we can have the information about still what available power we have. So we have more accurate information. Yeah, so that's it. That's the idea about separating clearly what is power related and what is not power related, where we could only act on the different devices through the state. Does it make sense?
Hi, Daniel. This is Lukasz.
Hi, Lukasz.
Yeah, that makes sense, but I would have a few questions. Because power allocator, as is now, it uses the temperature sensor and it operates only on one thermal zone, while I think your DTPM could operate like on a few thermal zones at once, like in abstract, of course, not in a code. But how you would be able to provide this power cooling device to IPA? Would that be with some kind of a power sensor, or we still have to rely?
Yeah, it's not correlated actually, because the DTPM act not per sensor, but it will act on the devices where they are power capable. So you can set and get the power. On the other side, you can have a group of devices and a group of sensors representing that. And there are some work done today to do the aggregation of these sensors to have just one sensor grouping all of this using this. Well, it's already defined in the DT, so that's some ongoing work today. So effectively, we can have a sensor aggregating all the other sensors, which is reflecting the devices associated with those sensors, and then plug that with the power allocator.
Yes, so why I'm asking, because from my perspective, what we have today in power allocator, there are some limitations. For instance, we have only one temperature sensor for the whole zone, and we monitor only that sensor. So we are not able to check, for instance, per cluster temperature. We can only get, for instance, SOC temperature. So that's one issue. But I can see with this new design, it might be solved better, or with the work now ongoing with the hierarchical sensors with some average temperature, maybe. So yeah, we could discuss this new design. So there is one issue. The other issue currently in power allocator, we don't have information about what's the maximum possible frequency set from the user space for that device, because that's the max power budget for the device. Then based on that, we split the budget across the devices. So there are a few missing features, I would say, in DevFreak and in the CPU-free cooling device currently, which the new power cooling device might have those features. And the third issue now with the power allocator, which also is heavily based on the CPU freak cooling device missing feature, is there is a new utilization signal that we try to derive the input power. So we assume that the power, the average power for the CPU actually depends on the utilization and the frequency at that moment when we are sampling, while this is not true. So the power estimation is wrong, sometimes by quite a lot.
Yeah,
And
right. I think yeah. That's correct. That's parts of the things we should work on to have a better power measurement.
yeah, so I can see opportunity in this new power cooling device actually to put more features in there. I have posted, I think, V2 or V3 with the active stats to track better when the CPU is idle and where it's not, because that's a bit more accurate when comparing to the utilization signal. But for me, this new power cooling device might be better suited for the purpose of IPA, because we have currently quite a few limitations in the freak and CPU freak cooling devices. So it would be maybe good to have a list of those limitations. I can send you on the mailing list, and maybe we could think about this design, the power cooling device, and then the backend as the DTPM. It would be just consumed there, I assume. You will just set the limits via DTPM.
Just set values, and instead of get recursive power, we will just do get power for this DTPM. So I think also the power allocator and governor could be a bit improved thanks to that, because as we have it's only dedicated on power, we can be more accurate maybe on the mitigation.
Yes, and also, so I assume that DTPM will also feed the stolen capacity into the thermal pressure to the scheduler, so that will stay as is.
But it depends on the energy model being accurate, actually, right?
Well, so that will be next topic. Yes, true. Thanks, Rafael. But currently, you have seen the active stats probably a few times now. We already have, even in a known workload, but with some idle periods, we are not able to estimate correctly the power with this correctly derived energy model. So it's a bit disappointing.
Okay.
Well, so you are saying that even if the energy model is accurate,
exactly. Yes,
then
then you cannot derive the power correctly, because we assume the frequency was constant for the last X millisecond, because we are sampling current freak. We don't have statistics. What was the frequency in that period? Let's say 100 milliseconds. So we don't take this into account. Plus, we don't know those idle periods for each frequency in this past X milliseconds. And that's why we can overshoot by quite a lot. Even a known benchmark workload like RT-up with a task which has some idle periods. So that's why I see opportunity in this power cooling device to be a bit more sophisticated than the current CPU free cooling device with the util signal only and sampling of the current freak.
Right. So do you think it could be a replacement for the existing CPU freak and the freak cooling devices?
Yes, definitely. The whole part which is there because of the IPA, this can be removed then. So it will be just the bare minimum for the stepwise governor. But this code is quite heavy to track or to estimate this power correctly.
Right, and it's not doing the job Yeah, as
No.
you said.
No.
Okay, so the direction would be to make the power cooling device work with IPA and the rest, and remove the code needed for that from the other cooling
Yes.
device,
And I
just
can
leave
start,
it. That
yes.
sounds good actually to me.
So I can start a mailing thread with those issues that I know, the limitations that I currently have. And yeah, we can start talking about this design from this power cooling device perspective, how this could be solved, and then combined with the DTPM. What do you think?
Daniel?
Yeah,
Good?
sure.
Right, sounds like a plan.
Okay, thank you.
Thanks. Anyone, any comments on this topic? Not really. Oh, all right. So we are done, I suppose. Okay. So now we have a break, which will be 15 minutes because we started that earlier. So okay.
I can demo. Right now we have things that this will enable. Hardware knob. Which CPU to schedule. First place.
That's where I'm a bit afraid.
I think that's actually. Our hardware. There's a.
My problem is that architecture. That's if we sell, that's it. And screw up the CFL. That's my point. That you.
Question is the
scheduler without saying okay. And we'll use that for the eco.
we know that's going to happen.
Yeah,
we know
but
this is going
what
to
I
happen
would
just
like
because
is a generic.
I'm building a Chromebook. That the product team works is they go, great, let's. Power should be much better here. Not until it works. That's great. That's fine. Now following it the way it was, or maybe it's an accident, and then they platform and they go, holy shit! Oh, it should have worked as we successful. That kind of thread. We'll only know if we're successful till we have a second.
Oh, yeah, I understand.
We can't draw a line with a point. The other thing is concepted on ARM and Intel at the same time and show benefit on both, that would definitely build our.
Not breaking the.
And then we can test.
That's the point. And other
Yeah, so
that you see my
yeah,
only that
sure.
I mean I understand what I think
And in
it's a
some
good
places,
idea.
in some, like in one of my examples, I want it to be fair. I want to be able to say, this task was the best background task. I want it to run at maximum efficiency, operating point on the max efficiency CPU. It can stay there. I don't care if it takes him all day long to get his work done. I don't care if you're totally unfair to him. That's what I want for that guy. Basically like a sched idle for him. Right? In fact, I want to be able to override that CPU, tasks like him, and have them all just stay there, percolate along, not interfere with. Or two, and then you. Yeah. Well,
that's what they are doing with the user.
Yeah, that's what they want, right? I mean, the Chrome guys basically came to me and said, "This is what we want," and yeah, they're. Well, let's just say they're in the same room sometimes. At least yesterday they were. I think it would be. I think that's compelling. Now the question is, are we expressing it the right way? You know, flags, should it be a slider? Should it be unitless? I don't know. That's the important thing is that you walk into it as an application developer, you should read the manual and say, yeah, I'm that. Not say, gee, or should I do number 5? I don't really know. That's what I don't really like. That's why I said I like 1 bit. If we start with 1 bit, it's unequivocal. It's like yes, no. Everybody knows what it means. You've added some ambiguity.
Thousand of different. How do you know how to use without any?
The OS knows.
No, the OS don't know. No, the scheduler don't know. And I agree that you can know, you can provide some.
OS is told.
Otherwise, what we aim to have in the scheduler is that, if I'm welcome SOC and the efficient bit is set, I should do that.
Well, you have that today. You have an EAS.
It's a generic interface. Yeah. You have this kind of way to compute. You can express and describe your platform. But the EAS is not that you have to provide the port. Then we make a clever choice based on that. Whatever the platform. I don't have any Qualcomm specific.
But whatever gave you that generic model.
Yes.
Yeah.
But it out, you see, it's
Not part
out
of the
of
kernel. Sure.
Not the scheduler. So we are getting that from DT, maybe
Okay.
CPI.
Sort of like the class thing Ricardo class in the task structure. It's like, Arch get class, what is it? Oh, okay, there's the class, black. You have to reach into architecture. In the case of the tiebreaker for a scheduling, that you say, Arch, give me tiebreaker based on the class cookie that you conveniently saved for me. All that the scheduler is really doing is that task goes about the system.
Tiebreaker? We need a it's either that or provide another way for the architecture code. Your architecture, where should I
then that's not very efficient, because then you have a big fat pipeline sitting and doing nothing, because you can't fill it up with anything useful to do, because you constantly get flushed because of branch mispredict or other things. But that's why you see all those variations.
One question and I guess one additional point. I'm assuming when you did this, you kind of maxed out the memory frequencies so that that's not kind of playing into your performance numbers or capacity numbers?
Sorry, again, there is a bit of echo.
Did you max out the DDR or RAM frequency when you test so that that's not adding a variation to the capacity?
No, I use the device as is because I don't have access to mess with the firmware on this the shipping device. So all I did was that I fixed all the frequencies. What I did on this particular setup was that all other frequencies than all other CPUs than the one that I was currently measuring, I picked at the minimum frequency, and then I just used setting the max frequency for the one that I was measuring.
Okay, so maybe I guess that's another variability for capacity. If it's not reacting fast enough, the DDR scaling algorithms or governors.
Yeah. So these are benchmarks that run between half a second and 10 seconds.
Okay.
So I think any policy that would have to adapt would have had some time to do that. This is a very popular benchmark in mobile, so I'm sure the system is optimized.
Okay. I forgot the other point. I'll ask for the mic when I remember it again.
I think one thing is clear for us, that we can't overwhelm our customers or our users to provide like a more specific energy model, because currently we just asked for those tuples, frequency, power, and some of them are already overwhelmed. So we can't probably have like a multi-dimensional energy model to take this into consideration, for instance. So there must be something else, like a two-step process, like having the old energy model also to cover legacy, and then in the decision direction from energy model to task placement, for instance, there has to be an entity in the middle providing like information to tweak the capacity utilization characteristics, which comes out of the normal static energy model, I guess.
Yeah, one way to go would be to stay with the energy model we have as a sort of an average energy model, and then have some additional information we can use to overlay or modify that. So if you had hardware hints, you could in theory multiply your capacities with whatever is being classified. The stuff you presented yesterday, the hardware feedback interface you have on Intel, could in theory modify the capacities on the fly.
Do you have an energy meter on your hardware?
On this particular device, there is the possibility of measuring energy. We don't in general. We don't have an architected one.
Yeah, because I think the ultimate solution to this would be, to make the target resilient to what's running and have it build the model on the fly by measuring itself. And it will just detect that it's now draws this curve. And then it would take some measurements and say, oh, well, that's not what we're doing now. Now we're on this curve, and the model has just changed.
Yeah, so we could flip the whole or replace the whole model depending on what workload we're running.
Or really generate it on the fly, yeah.
Yeah, but to generate it on the fly, you would have to sort of sweep all your...
Well, it would be easy for a uniprocessor, right? But the hard part is, okay, now you've got, a bunch of processors, and they're all at different operating points, and you'd have to, because they all have effect on each other, right?
Yeah.
But the nice thing about that is that you would be immune to things that you couldn't possibly know in the energy model. Like, gee, on this SoC, they tied two voltage rails together or something like that, right? And you would just say, well, this is what we see, so this is what it is. It's always going to be right. But for that, you'd need an energy meter, and we don't have one. We have an energy meter, but it's not very good at the low power levels. It's only good because it's really designed to tell turbo where to stop. It's really up by TDP where it's right on, but down by under a watt, forget about it. It's just all it tells you is you're under a watt, and it's swinging all over the place. But if we, in general, had a power meter that could go down to the interesting, through the whole part of the curve, I think the ultimate solution would be to use it.
Yeah. Would it solve the problem where you would have tasks of different behavior? I mean, if you have two tasks running on your systems and they have wildly different.
It is what it is. Yeah, you know, it's, of course, you predicting as always that the near future is going to be similar to the recent past, and we'll be wrong, but it will self-correct just like everything else we do, right? Somebody could be running this weird ISO that's way the right curve. Somebody else could be running the one on the left. They could switch between the two, but it would adapt. And so we continuously update the model.
But you can kind of need both at the same time, right? Because if you're having one task that behaves like the one on the right and one that behaves like the one on the left.
Could it fight? Yeah, that's a good question.
Because in theory, what we could do is that if we allow the energy model to be updated at runtime, we could do something horrible in Android and say, if the vendor detects that you're doing whatever, then they just go in from user space and say, now we replace the energy model with this because I know this workload works a lot better with this.
That might be a start.
But it doesn't solve the problem if you have a task that's behaving like the one to the right and another one that behaves like the one to the left, and you want to place them both the best possible way at the same time.
Right. Yeah.
So can you classify the task? Can we use the PMU or anything else new in ARM, like for Intel, to classify the class to be more memory bonded, CPU bonded?
Potentially we could.
Yeah. No, that because it's look like that could be a good new input to, I would say, scale a bit your power consumption.
Yeah.
Clearly, if you're memory bonded, I mean, highest frequency is just waste of power compared to the capacity.
Yeah.
I did some experiments on something like that before. The problem with that, the workload changes so fast. Like there are sections of code that's kind of memory bound, and then afterwards it's not, or things are moved into the cache. By the time you try to correct for it, and you say, oh, it no longer needs the max frequency, it's actually running code that's going to be more compute bound, and it's like, it is a mess.
You mean inside?
Trying to correct it at runtime.
We have the same problem because our hardware classifier is extremely fast. And so it's saying this, that, this, that. And what we need to do is normalize that to the scheduler's notion of how often it can place a task, which is, I don't care what you've done the last 10 microseconds. I want to know what you've done the last 10 milliseconds because it can take me a couple milliseconds to move you.
I did it in the 10 millisecond range. So even then the problem was that if 5 of those milliseconds you're running fully compute bound, you suddenly lost like 3% or 5% of your performance because you would have allowed it to go to a max frequency, but because of this averaging, you don't allow it to do it. That was becoming, so we just kind of, it's fine, we'll take the hit on power. So the other point is like, I think the workload, I'm just kind of spitballing here too. But to me, I'm kind of more leaning towards doing it on a workload basis or a thread basis, where you can say maybe for these kind of threads, this is going to be the memory model. You can try to measure and kind of put them in one way or another. Just setting one energy model, I'm not sure how much better it's going to be compared to what we have today. Except for the thermal case I see, but that could just be like a dynamic correction you could do. You don't need like 2 separate curves drawn. You could just say just above this value, increase it by 20% or something like that.
Yeah, I agree that for thermal, it's not a problem that each task is different, and therefore you can just update the energy model dynamically. So that would be fairly straightforward.
Yeah.
I think the tricky bit is addressing this issue.
I think for this issue, if you're trying to fix it, I think we should just go with per thread. Otherwise, we are like, I mean, we're trying to improve, but not really improving it. It's like, but all that work for not giving much of an improvement, kind of.
Yeah.
So ultimately, we seem to be leaning towards a solution where each task has its own collection of characteristics. And then when it gets scheduled, then we adjust to what it's doing or has been doing recently, right? Something like that.
Yeah, well, at least you can use it to adjust the performance to be more like your performance axis is moving, not more the power, it's just that you're stretching or not the performance range. So maybe that can be used as an input. Just instead of using a normalized performance value, when you're computing the power, you can just stretch like that. I don't
Sorry, again, stretch it based on
No,
what?
it's just that if you look at that, it seems that I would be curious, but the power range is the same. It's just that the performance is either really small in case of memory bonded. The range is really small because you don't care about, or it's really large. So if you're able to know if your task is memory or CPU bonded in your EES, when you're taking your energy model, the performance you can, of the EES, maybe the performance, you can scale the performance according to your current. We are back to the number of instructions per cycle.
Yeah, it is really that you would like to, I mean, on the x-axis, we can fix it by if we somehow knew that if we're running on a medium CPU and our IPC is X, then if we can predict that the IPC is going to be Y on the biggest CPU, then we can compensate for this error we have on the capacity estimate.
Maybe that's the one that can be learned, like Len was saying. Maybe you could learn that value because at some point, if you leave with the default energy model, it's likely maybe you would migrate to big, and then you realize, oh, the IPs isn't what I thought it was. It almost feels like you need per thread arch scale, maybe.
I remember someone asked me if the PMU was efficient on ARM64. If we can use that all the time, if we can reserve one channel.
We can't use the PMU all the time because it's reserved for debugging purposes, but we do have counters that can give us a few things on ARM. We have instruction to target and things like that.
That was the question. And we just say, okay, we keep one counter for the scheduler or the thread running currently on the CPU.
We could do that, but whether we can use that information to predict what will happen on a different core, I think that's the tricky bit. Because just because you have a low IPC on one microarchitecture doesn't mean that you have a high or a similar IPC on a different one.
No, but you know what is the max IPC per core? So you know how efficient you are. I mean, how many stall cycle you have right now in what you have to do. So you can predict, even if let's say that on the low core, you have a low IPC. It means that it's really a memory bonded. So you know that even
no,
going
that's
on
not. I mean, this is true for memory bound. You would have lower IPC, but I don't think you can just make the generic assumption. Too many variables.
One more thing. I think that you really care about asymptotic behavior and not about momentary behavior, because that can change all the time. You know, if the system is noisy, then you can't do much about that anyway, right? Because it will be noisy.
Yeah.
You'll have a lot of random stuff. If it's kind of stabilized, you want to avoid having a pessimistic case there, right? You want to, like, if it gets bad asymptotically, you want to move away from that state.
Yes.
Essentially.
Yes.
And that's what all of that should be used for. So that's your target, basically, that avoiding a case where you have totally off, the system is totally off. It could be much better than this.
But how do you detect that you're off?
Oh, that's a good question. But this is really the interesting case, because otherwise you cannot help the noisy situation.
I think there are only really two parts. Either you have some counters that can help you tell you when you're off, or enable you to do this correction of what is your true throughput, some kind of IPC prediction.
Yeah, you need to be more monitoring things. That's for sure. Yeah, this way or another.
Or you could cheat. You could just know, like we already talked about verticals, and you could say, oh, I know I'm running this app on Android, and it's going to be box number 3, and you don't really need box number 3. You're just going to tweak the X into a single model, and that's the tweak. It tweaks to the input to the model.
Yeah.
which I think is a good observation.
So we are running out of time for this topic. Yeah, I think I'm right.
Yeah, we're out of time. I just wanted to throw the problem out there so people are aware that don't trust the energy model too much on a modern system, and think about how we can actually improve it. Okay?
Yep,
Thank
sounds
you.
good. Thank you. So who's next? Daniel is next. We need a mic switch again.
There is some overlap with the previous year, but that's good. I mean, it's complementary. So it's this quick presentation is just to discuss about trying to describe this energy model. So in the previous presentation, I showed this power cooling device. So in order to have, so this power cooling device rely on DTPM. And of course, if we want to have more control on all these devices, we need to have more power information. And today it's very restricted. It's restricted to CPU, GPU, and sometimes DDR. So this presentation is, try to put the foot on this discussion, saying, okay, so since a long time now, we are talking about power and we are doing some progress. Maybe now it's time to go forward and provide more power numbers, even if they are not very, very accurate, but at least consistent. So what we have today is in the device tree, it's not clearly defined what we have for the power model. We have to infer this information from different coefficients we find in the device tree, which are maybe arbitrary. And so we just are able to compute the dynamic power. There is no static leakage information about the device. For the different changes in the performance state, we don't have the cost in terms of energy for these transitions. Also, we can see in the description on some platform very well known, there is no frequency set and there is no voltage specified. So we just have performance indexes to act on the CPU FREC driver. And finally, we have this adaptive voltage scaling things, the change of the hardware is doing the change in our back with the voltage. And another description is the CMI. So as far as I can tell, there is a per performance level only and energy associated with this performance state. So the energy model exists in the Linux kernel. So we have the code, and there is a place where we have the energy model. And initially, this energy model was designed for CPU, for the EAS, and it does not really appear to be generic. And it's focused on performance domain. That means if we have other kind of power information to set like CPU idle, I'm not sure it makes sense, but if we want to add CPU idle information for this energy model, is not designed for that. On the other side, we find this energy model structure is inside the Struct device. That means everything is already set in the kernel to have a pointer to the energy model from any device, so we can access this information from everywhere. But we can see that the energy model, so as stated by the previous presentation from Lucas, we can see now that the static leakage is no longer negligible like what we had before, and the temperature has a great impact on the power consumption with this static leakage. And also, there is the usage of this device. So obviously, if there is a CPU at the highest frequency, there is a power computation. But if there is no usage at all, it's not consuming any power. So we have to compute this power given the usage of the device. So here we are in a paradox, because we know that the SOC vendors are very reluctant to share this power information, but they need this power information and they want this power information for the energy hour scheduler. On the other side, we see that there is a power-based control, like the thermal and the power capping, the ES. We know also that there are some SOC having energy counters embedded on the system, on the hardware. And also, digging around, I found some out-of-tree kernels having a very complex energy model description inside the device tree. So that means it's open source, that means we should be able to access this information, but we cannot have that upstream easily. So maybe it could be a good thing to provide what is necessary to put power information for the board by implementing a nice energy model in the kernel with all the information. So I do believe that since we are talking about this energy model for this system, for the SOC, since 10 years now, the EAS has energy information and using it, and it's very much more efficient with that. We have also have this power capping appearing little by little, and the thermal capping, the thermal power mitigation. So I think this idea of sharing the power information is moving forward, and maybe we can, if we do provide a framework and a description for the energy model, maybe we will see some SOC vendors sharing, even if it's not for the most recent board, but at least for the some boards, share these power numbers. There are new platforms where embedded platform now where we can get the power consumption on different places of the board directly. It's embedded and it's integrated into the SOC. So that means this idea of having this power information available is also having more success. On the other side, the discussion I had on the mailing list and with the Chrome OS people, they are trying to have a better power management on the Chrome OS, the Chromebook, and they are looking for these power numbers in order to improve all the power management on this platform. So the idea is, shall we propose a generic energy model? And so we can give the opportunity to the SOC vendor to share this power information. Maybe we can go to something relatively simple. So dynamic power, static leakage, and the energy needed for the transition. And all this is not a frequency, but an index in terms of index for the performance. And all depends on the temperature, which is tied directly on the sensor, and this temperature is optional. So if we don't specify this temperature, then we don't have the change with this power computation. So the main idea is we don't have any inference now in the description. We clearly describe an energy model with the power information, the transition, the static leakage. And we can express that with, for example, linear regression or a pair of temperature and value to have this, yeah.
What's the transition latency cost? Transition between what and what? Transition energy cost.
Yeah.
What is it?
So the cost to change the state to go from one performance state to another performance state. And I put that there also in case if you want to use CPU idle, describe the different idle states and what would be the energy transition.
Well, the cost is going to differ depending on what the states are. There could be a lot of different costs for each state could have a different distance away in energy. So that could be, there could be a lot of those.
Okay. Okay.
In general, that could be a large data set for any system. Like, I'm saying that it could be a large data set for, yeah.
Very big a lot of information.
Big file of information, yeah.
Yeah, and can we have some kind of equation for temperature with a linear regression and
anything is probably better than 0, right? So,
I mean,
yeah, but I mean, then we can generate the values directly from this at any time.
For simplicity, maybe you can just have cost from the minimum frequency to each of the other frequencies, and you can do the math. It won't be right, but it'll be maybe close enough.
Yeah.
Right. So you'll have an array for cost from Fmin to each of those frequencies, and if you're jumping from the middle to the max, you subtract it. Won't be ideal, but better than nothing. But the other point is also if you're how often are we changing it to start making a difference? The transition energy cost for frequency switches, like at least on phones, I see frequency not changing sooner than 10 milliseconds. Is it going to make a difference? I don't know.
Yeah, I don't know what's the latency for changing the.
I'm more worried about all the dependencies because here you assume that each domain is controlled independently.
Yeah.
And one of the big problems we have is that on a real piece of hardware, it's not. Can you hear me? Okay. I think a much bigger problem is that you have dependencies between your various domains where you can control power and performance. For example, on the device I showed you before, the level 3 cache happens to be tied to the little core on that system.
I have an example of that too.
Yeah.
And that changes everything completely because then you can't really assume that the little core can run efficiently because if there happens to be something running on a medium or a big core at the same time, then the policy for the level 3 cache frequency will pull up the voltage and frequency for the level 3 cache, which also includes the little cores. Therefore, the little cores are less efficient if you have something running on the other cores in your system. And capturing things like that, that's going to be highly platform specific. And I don't know how we are going to capture that in a generic model.
Does it apply to separate all the energy description, and when we describe the dependency, we are able by this separate information to compute this.
Then you need to replicate the whole policy for controlling the frequencies in the entire system to be able to predict the power accurately.
Okay.
You said before that the performance domains, that means CPUs in the same frequency domains, this is something which is not 100%. So is this per CPU here, or is this per, what's the resolution of the information? Because EAS just needs performance domains, so CPUs in the same frequency domain.
That will be per device. I mean,
So that's a lot of overloading because of different use cases, probably also.
Okay, so we have questions from the matrix also. So could you read that? Because I.
So there were a question from Agathe. Is the current energy model available on a CPI system? Tests that have no DT nor SCMI. Maybe via SCMI.
SCMI maybe, but
No
not from DT, obviously.
So please send a link for a patch set which have been sent by Pierre Gondois, which seems to enable a CPI, ES for a CPI and CPPC. Can you check the link?
Yeah, we don't have all the bindings to produce a full energy model,
Yeah,
but
CPPC,
but there are one or two bindings that we can use to sort of extrapolate an energy model, and feeding that into EAS actually brings you some benefit, but nowhere nearly as accurate as a real thing. So I think the short answer is that there is no support for ACPI systems.
Not really. Yeah, agreed. So the CPPC thing is kind of derived from CPC data, right? I mean, not the CPC, but the register. Yeah, of the Intel, but generally CPC registers. But that's depending on also on what registers there are in CPC, because some of them are optional and may not be supported, right? So that yeah.
Can I add something? So here you say that we would like to have
Lucas, do you have questions or comments?
Yes, I have a question. Can you hear me? 1, 2, 3.
We can hear you.
Oh, great. Yeah.
So if you have
yes,
any,
I have.
can you please ask them on the matrix? We could then we could then read them out loud. Out loud, that is. Right. Are we following this?
so this idea of creating this description clearly, an energy model, even if I agree it's not so easy because there is all this dependency. I don't know how to solve that, but the idea, this idea of instead of having this information being in every place in the device tree, but instead of having that, just have a clear description saying, okay, this device consumed for this performance state this amount of power. Does it make sense, or is it? I don't know.
Well, yeah, in principle it does. In practice, it could be difficult to achieve because as I said, that's a lot of data for a single system. Somebody needs to collect that, put it in some usable form, and then put it into ADT and ship this. And that may be challenging. So I don't know. To me, it would be better if we had like power meters and could use those to measure things on the fly and derive the information from there, because it is first more reliable, and second, I think generally speaking easier to get, even though it may be more expensive from hardware, design perspective.
I'm not too sold on that, because my thought on that is there are too many variables that could affect the instantaneous measurement of the power. Like, as for example, like Martin was saying, your little CPU could be consuming more power because the cache is high at a higher frequency. They share the same voltage rail. Or maybe you should move.
You can.
So yeah, I think there's too many variables and you don't know which variable is affecting it. So I don't think, at least I personally don't think it's a good idea to go by power measurements.
Look, I just write on the chat. Static power is a bit tricky to account in this array, even with the new dimension of temperature. It took me a while to re-engineer those information. It would be really hard in practice and without vendors sharing this info. You can only measure the total power. You have also to build a water cooling to fix temperature.
Well, I think at the end of the day, we want to be careful that perfection not get in the way of goodness. And it just has to be good enough to make a scheduling decision. And Morton said this 10 years ago, right? It just has to be good enough. I remember when you came up with the AES, there was some like Samsung guy in the corner of the room that says, you guys are nuts because you're never going to be able to model our SoC. And you just said, this has to be good enough. What we really want to know is, when is the lack of an accurate model screwing up a scheduling decision? And can we make it good enough so that
But in this case, it's not just about scheduling, because Daniel is talking about
generic
things like the temperature, thermal control based on the energy model, and it's way more than this. It's about device power and memory power and other things.
So what
Idle
you need,
power.
Daniel, is to decide how good it has to be, and then see if we can make it that good. But you can't strive for perfection. You could way over-engineer this.
Yeah.
Maybe it's okay to over-engineer it in the DT representation or whatever, so that you have the information and then you choose it, you use it the best you can. Because once you put a binding in DT, now everybody starts using the same thing and you can't keep changing it. Maybe it's okay to over-engineer in DT. This is my 2 cents. Ask for all the detail you can, they'll give you the best you can, and you use the best you can out of it. Maybe today you wouldn't use transition energy, and maybe they won't fill it up today, but 5 years later, maybe that's the issue you need to resolve. But you at least have the data from now.
I think it's worse if you ask for it and somebody then makes up that information and puts in there for you because you asked for it, and it's off, and that has happened in the past. Right. I think we are. We still have 2 minutes for this topic. So for any final comments or something like that, and we need to switch over to the next one. So I guess we can do the mic switch right now.
Raphael, can you help me change this? Okay.
Cool.
Yeah. The floor is yours.
Cool, I'll start. So we have been playing around with VMs and at Google and Android. A bunch of talks about it. So I decided to play around with it to see how does it react to DVFS, or how does DVFS react to workloads running on VMs. It wasn't behaving well, but before I start, my ideal goal here is to, if somebody chooses to run a use case in host versus VM, they should not have to worry about the performance suffer or the power suffer just because it chooses to run it inside a VM, outside of the obvious overhead of VM, right? Other than that, it should just kind of magically work. That's kind of what I'm hoping we can get to. And another way to put it is if your host is idle and if you run the workload inside a VM, the CPU performance states you end up at and what thread gets placed in what physical CPU should kind of be mimicked inside the VM. So that's the kind of high level goal on this one. We started running this is synthetic benchmarks or synthetic use cases to see what's going on. We use RTApp for this. So all these slides is going to be top is host, bottom is VM, generally be two CPUs. One is the little CPU, second one is the big CPU. That's the theme of these slides. Oh, is it? I think it is full screen.
Yeah.
This one? Oh, sweet. Way better. Thank you. Yeah, so generally first one is little CPU, second one is big CPU. This is just a thread running continuously on a host, and it reaches the max capacity of the little, it gets migrated over to the big, eventually ramps up. If we run it on a VM, it wasn't moving to the big vCPU at all. Obvious issue here was that we didn't set the capacity, so that was wrong. So if you don't set the capacity explicitly, it's going to think all vCPUs are the same. So load balancing doesn't work right. So we did set the capacity of both the vCPUs correctly now. So we pinned vCPU 0 to the little, vCPU 1 to big, we set the capacity. But now the problem was in the host, things work fine like before. But in the case of the VMs, the threads migrated to the big CPU way too quickly because if you don't have the CPU frequency driver, it assumes you're running at max frequency, right? So just to kind of give a comparison, we set the host to max frequency on the little, the big, it can dynamically scale it. And if you see, it took like 41 milliseconds before it migrated to the big CPU on the host. But in the VM case, it took about the same time, even though the actual physical CPU was not giving it the same performance. The VM thinks, oh, I'm running at max frequency. In 34 milliseconds, you reach the capacity of the little and you go to the big. So that's also not good. It's going to unnecessarily move all the little threads into the big CPU. That is bad for performance. Oh, and then despite things getting moved to the big, it's still going to be kind of bad in the VM because when you migrate a thread from the host, and on the host side from little to big, the utilization is also migrated to the proper run queue of the proper CPU. So you start off at a higher frequency, start off at a higher utilization. But in the VM case, it's always the vCPU thread, which is what is dictating the frequency of the physical CPU. That starts off at I'm using it for the first time, so it starts off at close to 0 or whatever you set it to. So it takes much longer to ramp up to the max frequency. So it's like the worst of both worlds is what you get. You move little things to the big CPU when you don't need to, but things that do need the big CPU take much longer to get to the performance point. There's also some new thread boost features that we have, I think on 5.19, and that doesn't reflect at all. So one of the features, again, I only partially understand it or aware of it, but if you start a new thread, you give it some initial utilization that's non-zero, so that when you start off, if you have lots of new threads, you get to Fmax quickly. But all of this is happening inside the vCPU. The host has no idea, so it has zero impact on the performance points chosen by the physical CPUs. That's kind of what I was trying to show here. In 26 milliseconds, it reached the max frequency. Even if I count from the first transition, it took at least 77 milliseconds to reach the max frequency of CPU 0. Other known issues, a util clamp inside the VM is not reflected on the host side. Util est of the guest threads isn't used. That doesn't transfer over either. Another thing is if the big thread migrates from little to big, in the host side, you drop the frequency of the source CPU. In the vCPU case, as long as the vCPU is still active, you don't drop the frequency, so it takes time for the frequency to come down when the load has gone down on the CPU. So those are all the synthetic use cases I had, and I had prepared the slides for this LPC. And the Chrome team came and said, hey, hold on, we have actually a real use case you can share. So they're trying to run Android inside Chrome, either as a container or inside a VM. So what you're seeing here is Android running inside a container on a Chrome OS device. They're running a game. You'll see most of the big threads are here. Not much is going on the little CPUs. They were getting about 27 FPS. And frequencies actually do change here, if you can see the CPU frequencies. If I'm not mistaken, I think either 6 and 7 or 4, 5, 6, and 7 are big. 6 and 7 are big. There we go. And then if you run everything inside the VM, if you run Android inside a VM, you get only 10 FPS. It's like horrible. 60% cut. And you see the threads are spread all over the place. So we're obviously only looking at vCPUs. You can't look at the real threads here. But you can see it's kind of all over the place. All the CPUs are active. CPU frequency is almost hardly changing here. So it's not surprising. You see kind of terrible performance here. That's the kind of all the data I have to show how it's bad. Kind of looked into it. This is the current proposal I have. Maybe it's the dumbest idea. Maybe there's a better idea. Good, happy to hear. But before talking about the proposals, some of the other things I considered, and I think this is what I've settled on, is that there's always an option of allowing the vCPU threads to migrate between big and little. At least for this use case, I'm not convinced we want to do that, because you still want the ability inside the VM to say, hey, these are going to be background stuff. I want to run them only on little CPUs. So they should have a fixed notion of what is going to be a little vCPU. That's one assumption I'm making here. And the other one, oh yeah, I don't think you can even change the capacity runtime in a sensible way once you boot a vCPU. For a vCPU, yeah, a lot of assumptions that seem to be made, which says early on in boot you set the capacity and it's not changing. So I'm not even really keen on dealing with that part. If we need to, we can. That's kind of my current assumption when I'm making this proposal. It looks like Martin wants to say something. Should I finish my proposal and then, or do you want to? Okay. So yeah, the current proposal is pin the vCPUs to the, so like all little vCPUs can migrate between the little physical CPUs, but not to big. That's kind of the pinning I'm hoping we can do. And then all the big vCPUs will stay within the big. And we make sure we set the capacity correctly. So the only real missing piece is for the VM to know what the frequency is of the actual CPU, and also as the internal utilization is changing in the VM, you want to kind of send it out of the VM. For that, I'm proposing having a pseudo CPU frequency driver for VMs. This will just kind of work across all machines, not just for this particular use case, but it'll just say, okay, what's the real physical CPU frequencies? Those are the same frequencies I'm going to claim I can support inside the VM. And then every time you have your frequency switched, you just kind of pass it back out. And you either set the vCPU's util est or util. We have to figure out the math that if you just go update the util, you can end up with some minor errors that can either let it go all the way to max or min. There's some stuff that we need to figure out, but at a minimum, you can set util est or even util clamp of the vCPU if you need to. And then for figuring out what the frequency of the real CPU is, if you have AMUs, it's already solved. You don't need to do anything. But in the case where you don't have AMU, an equivalent of that is to just every scheduler query the original CPU's frequency and update your.
So we have a question from Srinivas on the virtual. Srinivas, do you?
And that's pretty much all my points.
Srinivas, can you hear us? You have raised the question hand.
Yes, I'm.
If you're speaking, I can't hear anything, Srinivas. I think maybe the audio of the remote is not playing on the.
Yeah, so the audio is not working. So Srinivas, please ask the question on the matrix in the matrix chat, and we'll repeat it here.
I did on matrix. Yeah, I did on.
I think in the meantime, my main comment is that you just
can you keep it closer?
Proven that running a workload inside a VM just undid all the improvements we've done in scheduling and power management the last decade. Because we add this extra indirection that everything is now run inside a vCPU where we have absolutely no knowledge about what's going on in there. I think the most important thing is to decide who actually does the power management. Is that the guest or is it the host? And one thing I don't think you covered is what if you have two guests?
Oh, yeah. Yeah. So I was initially thinking about, should we just fake a frequency of 0 to 1024 inside the guest? And every time you have the utilization change by X amount, you send it outside to the host. But then the problem with that option was that if you do have an AMU, the frequency you compute by looking at the cycles will not match with the fake frequencies you're reporting inside the guest.
No, and the other problem is that inside the guest, you might have time disappearing because.
But I think because you're counting the actual clock cycles within the guest, as long as that's virtualized correctly, it should be okay.
Yeah, but you don't see, if you have something that would take 2 milliseconds to complete if you were running on the host, not on a virtual machine, you can't tell inside the virtual machine how fast you actually complete there, can you? I mean, you can be preempted, your vCPU can be preempted in the middle and it might go off and do something
but if
else.
I'm not mistaken,
and that I don't think you can observe from the AMU because the AMU will only count what you're doing inside the VM.
Right, but I also thought the time doesn't pass inside the VM if it gets context switched out, at least the scheduler time.
Yeah, it doesn't, but real wall clock time will pass. So if you're doing.
So it depends on what we're using for the AMU when you're dividing by.
So if you're doing like rendering or something like that.
Actually, sorry, it goes a good sidebar I had, which I wasn't planning on getting into. But technically, all you need, this is not going to easily apply to what we have today, but this is an idea I had. All you need to figure out a normalized utilization, which is normalized for both architecture difference and for frequency changes, is you just need the CPU cycle count. I can go into this, but I want to give Srinivas a chance to speak, but I can kind of talk about this too.
Okay.
How much time do I have left, by the way? 15 minutes?
How many time? Oh, let me check.
Yeah, I think so. I think I have 10 minutes, 10 or 12 minutes. Sorry, go on.
Yeah, two things. Either you're using a SMP virtual CPU, rely on the host to do everything, or you have to replicate in your VM all the information that we've got in the host.
You're talking about, you're trying to answer Martin's question? Okay. And I don't think that mic is working well. But...
Oh, really?
Okay,
or maybe
it's better.
Yeah.
Okay.
And then, have you looked at the SCMI backend for your VM? It provides you CPU freq information.
How to get the CPU freq information? I haven't done that part yet. This is like fairly new because it had synthetic data.
The SCMI is just a protocol, and then you can just simulate.
Yeah, I'm not too worried about how you get the frequencies, right? We can get them whatever's the right way, but is the idea okay where you fake the original frequencies inside, and then when you set the guest frequency, you pass it out. It still has the issue that Martin was talking about, where if you have multiple guests running, it might not be ideal, but I'm sure it's going to improve the performance than what's there today. So
it probably will, but you also proven that using containers is way better because then you don't mess up all the power management.
Sorry.
If you were using containers instead, then you don't have all these problems.
True.
I think it's an inherent problem.
So whether
of
you want
using VMs.
That's one example use case, but there are going to be other use cases for VMs too. So I don't want to stick with that. And even in that case, there are other reasons it chose to use the container versus VM. So they're moving towards a VM.
Yeah, of course, because it has other additional properties that are attractive. I understand that, but the way we do virtualization is not great for power management because we can't reason about what's going on inside a VM at all.
Yeah. So does this proposal seem like something that's acceptable as a first, something we could land as a first step? You can always improve on it if you have other thoughts.
I think it can work if the guest is the one that uses your system the most. I mean, you have very little activity outside the guest, but if you do have substantial utilization in your host or in a different VM, then I think you need a lot more coordination to make things work.
So I mean, let's just split it into pieces, okay? So like the piece about pinning, about restricting the vCPUs, the big vCPUs to the set of big CPUs, it makes sense to me. Like because it's better to live in the same room, right? In a maybe.
And then, another point on that.
Enough. But did you? I wanted to ask. But you are talking about this from a theoretical standpoint, or have you tried it and then?
So I haven't tried this solution. I was going to try it. Just hadn't happened.
Oh yeah, it would be good to check if it helps at all. Like,
obviously, if it doesn't help, I'm not going to send it out.
Yeah. Okay.
Right. But based on the data I've seen, I believe it'll help. So.
Well, I think fundamentally, as Morten said, you still have the two cooks in the kitchen problem. So you're looking at this from an Android point of view, and then you showed a slide that said, oh, and here's Android running inside Chrome. Do you think really Chrome OS is going to want Android doing the power management on the Chrome system? Probably not.
Right. It's true, but it's not doing the power management. It's passing the hint over to the host saying, hey, this is the amount of work that's running inside me. Do the power management. So it is not doing the power management.
Okay. Okay.
Right? So what I'm saying is when the CPU frequency inside the guest is set, you pass on the utilization to the host. So the vCPU's utilization can be adjusted to reflect what's inside.
Can't the host see the utilization? It knows what idle is and what idle is not.
No, it does, but those are the kind of problems I was kind of trying to show here before, where it can't deal with things migrating, for example. That's a simple example. So,
but these are real physical CPUs, this migration here, right? And
no. So in this case, what's happening here, in this case, what's happening, this is vCPU 0, this is vCPU 1. So inside the guest, inside the VM, the guest thread has migrated from one vCPU to another.
But if
that's what you're seeing here.
But if they're pinned, then those really are a physical CPU migration, right? And the host can see that.
No. The host, all it can see are the two vCPU threads, right? From a host perspective, it's just two threads running all the time. The actual guest, so in a sense, you're limiting what physical CPUs the guest can migrate to if you kind of like translate it into what physical CPUs it's actually running on. But from the host side, it doesn't see any of that. It's completely abstracted.
Oh, that's a problem.
Yeah. So I'm saying it's completely hidden. If we don't want to pass all the information, let's pass the crucial information, which is
yeah. So basically, the capacity computation in the VM doesn't and the host are completely independent, right?
I didn't hit the last part.
The capacity computation, the VM and the host are completely independent. So the host has its own, and the VM has its own, and they may be off.
Yeah. So
okay.
Depending on how much you configure the vCPU, it's off by more versus less. You set the capacity, at least the capacity-based calculation is right. You want to go to the chat?
Yeah, I have an idea, but crazy is that no, it's just that.
Can you speak into the mic?
Yeah, I'm coming back to the SCMI backend. We can have something running in user space as a SCMI backend, which will be shown to your VM. So the VM can say, I want this frequency, I want this utilization. This backend running in user space in your host can then apply some uclump value on the C group of your vCPU. So you will be sure that your vCPU will run at the minimum compute capacity that has been requested by your VM.
But why do you want to go through user space for that? This will just work, and this is going to work for all the systems, right?
But it's not going to work for all the systems because you've got a very isolated use case of one VM and one host. As soon as, like Morten said, as soon as this goes to 2 VMs, or as soon as you want to map a subset of CPUs into one VM and a different subset into another VM, this completely falls apart.
But how does that work? I'm open to other solutions for that. I don't know if that's going to
The
work.
host is still in control. I think you're at the two cooks in the kitchen problem. You got to decide who's going to make the final decision.
In this case, it's still the host, right? Again, the only thing I'm doing is I'm setting the utilization of the vCPU. If there are 2 vCPUs that are saying this is my utilization, the host is still going to add them up and set the total frequency to be higher. Right? Is that clear here? Me.
But only if there's one guest. Right?
No, there can be.
Yeah, but in your proposal, you're hacking or you're updating directly the utilization of the vCPU based on the internal utilization of your VM. How do you translate this information?
Not internal utilization of the guest threads. Yeah. The RQ is util inside the vCPU. I'm kind of think of it as copying it over to the thread that's representing the vCPU.
Yeah, but it's not. You're creating a direct link between the Linux RQ and your vCPU in the host.
Yes.
Now, what if you have another VM that's a Zephyr running? How do you do that?
Okay, so the only problem that I am aware of with having two VMs is that you don't update the util often enough. That's the only thing. But everything else is correct as far at least my understanding of what my proposal is. So are we on the same page there or are we not? Because if you have 2 VMs running, they could still calculate the utilization correctly. They'll both set their corresponding vCPU threads utilization correctly. Yes. And if they're both running on the same CPU, you add them up and then you set the frequency.
I would still recommend to do that as a proof of concept, and then see if it helps at all.
Okay.
And if it does, then maybe share this information with everyone, and we can see, right? Because if it doesn't, then it's completely academic, right?
Yeah.
Cool. I think you might be able to come up with something that can work for very specific setup, but
even so.
But I want to go to Len's comment of let's not have perfect be the enemy of the good. Right now, it doesn't work for anybody. Even if it works for the case that's only one VM, I'll take it.
So
until somebody else can come and say this is shit and replace it, happy, please delete the code. Right?
Even if it's a limited case, then it is sort of if you have the time and are and resources for doing this research, then this would be a good thing to know by itself, right? This does help really.
Yeah. But you would still have the problem that you would have 2.
Then
but
are we on the same page on how 2 VMs will cause an issue? Or are we still not in agreement on what the issue is when you're having 2 VMs? Right. The only concern is like one VM might say, hey, it's time to bump up to the next frequency.
So the other VM can be a completely different operating system, like Zephyr or something else, and then
yeah, that's a whole other issue. Yeah, true.
But even
I'm only talking about Linux inside Linux. True.
But even if they're the same, then if you have both EAS or something like that working inside your VM, saying, "Oh, this task needs to go on a big CPU," and I put it on that vCPU, and that's pinned to a specific big CPU on the host.
It's not specific vCPU, so within the vCPUs it can move around.
But you can still have a scenario where the host has already fully utilized your big CPUs, and the guest now insists, I want my high priority task to run on a big CPU too, and the host will just say, okay, that vCPUs are going to get.
But what would be the right
50%
solution in that situation, though? That
The right
almost
sol-
seems like an overloaded.
The right solution there is not to use VMs because it can't deal with this.
Okay, I'm
Right.
talking about the VM. Okay.
Right. So I think that we really are talking about a limited use case, which is running Android and Chrome in a VM. And in that case, the sort of implied assumption is that the user will not hang themselves and try to do one thing at a time. And that would be the Android in the VM. And that should work.
Looks
in
like
principle,
two more people want to
right?
talk. John and
So I guess two things. One is it seems like one solution to this might, I haven't thought about it a lot, but might be to fully unpin all of the, so we'll unpin, but then dynamically update capacity in the guest. And so like essentially if you could somehow figure out that the host is really busy and then subtract that from
Okay,
some of the
that's
guest
different
capacities,
from.
but-
I know what you're. Okay, I know what you're trying to
I'm
get
just
at.
trying to figure out,
Yeah, you could,
like
but-
everyone wants to use, all the guests want to use the big, right?
My point is basically that we there are problems and we know about it, and we don't want to address all of them because it's just not possible to address the case. And you can think about nested VMs then, right, and then continue from there. So, but the use case, the example you showed is really simple. Just run one VM in one host and run the workload in this VM, and that example should work. And it doesn't today.
Right.
And that's a problem. Okay, we have exhausted our time slot.
So time's up?
Yep.
Okay, cool. Thank you.
So let's have a break, 10 minutes, and then come back.
I was going to ask a quick question, which was, would it make sense to have something like a VirtIO sched, where you basically just have an abstract CPU, and it doesn't even have to be matching with the host, set or just two or whatever, and then basically every time you go into the scheduler, you call to the host, and then the host decides which of these threads you run on based upon where it's placed the threads. Deciding.
I'm not fully sure I understood the last part, but it looks like for every context inside the VM, you want to call into the host, switch all the way back to the host, update.
Just
and
let
come
the
back
host
in.
decide. So basically try to create a transparency from the guest.
Yeah,
into
that's
the
like a
host.
whole nother can of worms. That's not my domain. I think that's a lot of overhead.
So we need VirtIO DVFS, we need VirtIO clock, we need VirtIO regulator. I mean, we're starting to get into pretty.
Hopefully you're
big can of
joking.
worms.
Okay, I'll step off.
Yeah, I like the SCMI idea actually. That this actually is
Testing, testing. Can you hear me? Hello, hello. Can you hear me?
Yes, I can.
Brent, do you still need my audio? Okay, can you hear me, Brent? Brent, can you hear me? Testing room. Can the room hear me?
Yes, I can hear you. And can you hear me too? Good.
Yeah, we're doing an on-site test.
Okay.
Thanks for letting me know.
You'll be able to talk to him there.
Yeah, I'm the next presenter, so I want to make sure that
Hey,
I
you can hear me now?
Yes, now I can hear you, Brent.
Okay, you can hear me.
Yep.
Okay. We're hearing him fine here.
Great.
Just a second, Dylan. Stay on the line.
Okay, staying here.
Say again.
Staying here.
Staying here. Here it is. Talk.
Hello, hello. Can you hear me?
That's it. Okay. Thank you, Dylan.
Yep.
Yeah, okay. Okay, so let's get back to our session. The next presenter is Srinivas from Intel. Srinivas, you already have the control of the session, so yeah, you have the floor. And go ahead. And the audio should be fixed for us.
Can you hear me?
Yes, we can.
Okay, great. Audio is fixed finally. Looks like in previous session we were speaking, but you couldn't hear or something. Yeah.
Yeah, right. But now we can hear you. No problem.
So time to go, or shall I wait? Can I start?
Yes, please.
Okay. Hey, good morning and good afternoon, everyone. I am Srinivas Penduwada and I work at Intel. And one of the area which I focus is on power and thermal performance, mostly on both kernel and also in user space. For some specific use cases, what I'm trying to bring in, per core idle injection to x86. So today I'm going to talk about some of the effort which I'm doing and some of the challenges which I have. And from the use case perspective, from the use case perspective, I'm targeting both clients and servers. So on the clients, primarily for thermal control, as we know that we have now 45 watts TDP systems with like 20 threads and 14 cores, and the laptop form factor like some of the XPS 15 from the Dell, or those laptops are very thermally challenging, and it has like NVIDIA high-end graphics cards. It works fine, but when you want to really use it and put it on your lap, we have lots of heuristics where we control lap mode, but that's really a big hammer approach where what we call RAPL, running average power limit, we drop to the floor, but then also it's not, it works, but then it affects the user experience, right? Like, for example, I'm watching some YouTube video, or playing some song, or very basic stuff, or like sometimes you can see when the typing, if you are really type very fast, you can see it's not very good user experience with that. So I tried various approaches. Some of the approaches where I know that I can target some CPUs which we know that are which are high performing here, and which turbos to much higher, and so I want to basically force them to idle and very quickly and come out very fast when the use case is done. And also, I'm also thinking about integrating with GNOME power saver mode inside the power settings. I'm not sure anybody is here from distro. I think this will be a very useful feature because these laptops, if you are really traveling for 6 hours flight, it's not going to be friendly for 6 hours unless you are in some low power saver mode. So I'm trying to also bring in low power saver mode into the laptop use case. And there also I play with power, but at the same time, I'm also optimizing which CPUs to use. And in the server we already have the Intel Speed Select technologies where we can adjust the frequencies on other cores by sacrificing on something. And so that use case also can utilize this idle injection work. Somehow my slides are not updating. Okay. Did you see that?
Yeah, it has a bit.
So one of the prime requirement I have in this case is I want to run it on Linux distro. We don't, it's not a vertical segment which I'm targeting. It should work out of the box.
Srinivas, the audio cut for us. So could you repeat the last sentence?
Yeah. So my prime requirement is it should run out of box on a distro configuration. And without intervention. It's not a vertical segment which I'm primarily targeting here. So like the users can customize, but don't expect they can do much. So that's why that's why I'm doing other heuristics and trying to come up with in user space some policies. And one of the requirement is, we can do lots of C group or offline, online, but everything has limitations. Like online, offline, primarily, it affects it takes time to enter and exit, and also it breaks affinity. Users are not happy if I remove the CPUs from them. And also, my scale of in and out of this idle mode should be in hundreds of milliseconds. So I don't want any high-handed approach where you should do, like offline and wait for it to come online again, depending on what device, which driver is breaking it. So the idle injection in Linux is really not a new concept. It's we are like Intel Power Clamp driver is there from last 8-9 years, and we use it for for thermal control when everything else fails. Just before, if either you power down or want to survive, that's the time we definitely use it. And the per CPU idle injection is also present in Linux, and thanks to Daniel, he developed it, and it's used in ARM-based system for a while. So it's not a new concept, but we never used the per CPU, idle injection on at least on Intel platforms. So the solution I come up with is we wanted to basically reuse whatever Daniel did. We reuse the power cap idle injection, but at the same time, we want to make sure that power clamp also works. And so to bring into power clamp into the same work, using the same framework, I had to modify the base idle inject so that we can have some callbacks for compensation. So why we need power clamp driver to use the same framework, because both of drivers can play call this play idle loop, and they can both same time. So if you have one framework, one of them can back out. So it's using, the other one cannot use it at the same time. So that's why I modified the power clamp driver to use the same power cap idle inject framework, which Daniel developed. And this way that we avoid this conflict. And then I started experimenting, on various configurations, how this performs. So I encountered various issues, and some of them are minor, some of them are slightly major. For example, if you run, sometimes you see my kernel log has warnings, like those warnings are, something like this. These warnings, user will not be happy if they see a warning, and particularly if I release this to some distro, they will not take this unless if there are warnings like this in kernel. And these warnings comes because like in the play idle loop runs on a FIFO task, and the case of soft IRQ, when like it's running, it's scheduled, it can wait, and it can race with it, and obviously FIFO will win the priority, and we will try to enter into idle, but when we try to stop the tick, you will generate this warning. So that's the one issue we cannot have warnings. And second thing is we can go to the same slide. And also what I observed is in what kernel you use, it breaks. It behaves differently. So like in kernel version 5.18 and before, tick used to not stopped, because because of this, whenever this warning is generated at the same time, it basically said don't stop the tick. But 5.18 and above, that path is optimized, and now it is broken. Basically, good part is it doesn't generate warning anymore because there is a bug. So, and there are two bugs basically. One of the bug is very very logical. There is some issue, and I've sent a patch for that. It's in the tick scheduler. And other one is also assuming that unless you have you have config preempt RT is always configured, which is not true. So that fix, I have a fix for that, but I'm going to talk to Frederick and see if what's his opinion on it. So I was working with Frederick on solving and also with Peter how to avoid these warnings and some of the delays, because these delays can be pretty long. Like for example, I saw delays like to 18 milliseconds. Depends on what hertz you are using, and so Frederick come up with an approach where he basically checks. So when you call do idle loop, because currently we only check for need resched, but he added a check for if there is a soft IRQ depending, we basically come out of the play idle loop and we call for sched timeout for one Ziffy, and we go back to do call go back to the loop again. So in this way, the soft IRQs don't get delayed. They get some delay, but they don't get delayed by like milliseconds, lots of milliseconds, basically, if you don't have this. And in addition, we need to do, like in this case, you may have storm of IRQs, right? So, somebody's trying to ping you, or somebody's running some test timer program, you may have storm. So we need to also prevent that case. And so I introduced so there was how to do that. I tried to add some range, like uSleep has a range. I tried to add range to play idle loop so that if you don't permanently, you don't stuck in that because of somebody is trying to, break your system by IRQ flooding. So that patch also I have added. And with that, at least it seems working, unless anybody has question here till now. Seems everything is okay.
I have one question. How long is your idle period when you are injecting some idle? Is it seems to be quite long to generate this warning, isn't it?
No, this warning generates even like I have 10. I tried 10 millisecond, and also power clamp used 24 milliseconds. So I want to stuck with power clamp, but 10 millisecond or 5 millisecond. This race can happen anytime, right? There's no. Okay. So generally what happens is you don't see case soft IRQ running case, because what happens is when you run IRQ, the soft IRQ on the IRQ context only, it runs the the whatever soft IRQ. Only time when it's used, it cannot do it. It tries to schedule a soft IRQ rethread. So that optimization is already there in our kernel. But so you won't see all the time. You need to hit that case where he schedule a case soft IRQD. So that's why probably you don't see it in Android, but it's very obvious. You will see it if you ever hit that condition.
But if you're just idle for, let's say, 10 milliseconds every 24 milliseconds, that's what you were saying? Mm-hmm. Your case of IRQD should be able to move forward during this non-idle period.
Yeah, but it's it will throw the warning when you enter a play idle loop. But you're trying to. Yeah, so when you try to enter play idle, and when he finally it will try to call this tick stop or something, and it will say, okay, can I stop it? Can I stop the tick? And he will check if the soft IRQD is pending. He'll say, okay, something is pending, so I want to give you a warning. Because normally it should not happen, right? Because when you're real idle loop, you shouldn't have that issue, because need reschedule will be always set by that time.
Yeah, so this is because of stopping the tick. Like when we try to stop the tick and software IRQD is runnable, it will complain, because that's that shouldn't happen. This is a condition that normally shouldn't happen. So.
Shouldn't happen because because we are running a FIFO task and putting and then calling the do idle. So you're running with highest priority task and calling an idle loop. So that's why you see this. One solution is that you're going to get it, so remove the warning, but that may not be the right solution. So that's why this optimization is done.
Yeah, this approach looks correct to me. I mean, just let it run and then go back after a while.
Yeah, so I have the patches. I have at the end of the link. I didn't post to mailing list because it didn't get reviewed internally first. So. And also one of the issues which I have is the timer test, right? So if you run timer test, you see the last, if you put 95% idle, you have a lot of jitter, which is, and this is particularly more pronounced in your pin timers. The problem with that, there are very few users of pin timers. One is like there are 3 users which I can recall. I didn't go really why if I remove their MCE, of course we cannot migrate the IRQ, but for the IPv4 case, I think that if I move the IRQ for the Ethernet or task or whatever source, I probably can remove that issue. But you will have some timer issue, some jitter, which is so obviously I think this shouldn't be much problem because we are targeting a use case which is not real time, and there is jitter. Even if you don't do idle, you see there is a lot of, it's not like it's all the time it's correct. You have a jitter, but jitter is more pronounced when you have when you have so much idle. You're forcing it. Anybody has any comment on ignoring timer issue here?
So the question really would be if that is causing any power difference. I mean, any energy usage difference. I mean, significant energy usage difference.
Yeah, so in this case, of course, I assume, this is a really hard time, this is a really timer testing the latency. So obviously this is flooding the timers, but real use case, you may not have this many timers flooding it. So probably it won't be that pronounced that I'm showing here.
So just your timer jitter, so you see a lot of jitter, but is it much larger than otherwise without using this idle? I mean,
it is larger, but it's more. You see, even if I don't do it, it's still large, but it is not that, it's not that dense. Yeah.
You have a lot of more occurrence, but not worse than without that.
No, not worse.
You have other case to go out of idle anyway.
Yeah, it's not really. So so this is probably I'm not because I don't think there is a good solution for this because we accept the playing with source. Because timers are doing what it is supposed to do.
Does Power Clamp have this problem too? Like if you use a Power Clamp?
Yes, we do have Power Clamp problem, but the only difference in Power Clamp problem, because the use case of Power Clamp is basically you're deciding between almost power down the system and running. But here we are trying to do it in more normal cases. We are so that's the
I see. So this is okay. So Srinivas, we have only 2 minutes left for this topic.
So I have the remaining cases, 2 cases I did not check. Is one of them is the impact of no hertz full CPUs. How do I find, because I want to do it from user space, not really from kernel. Of course, the actual mechanism in kernel, but the actual driver, what we are doing from policy from user space. I don't know no hertz full and those CPUs, what's the impact of it and how can we deal with it? Because, some users may have no hertz full with some CPUs and I may not be able to inject idle on that. Because there are some other warnings in no idle full path, which may occur if I do that. Okay, I think that's my last slide is, I have lots of, in my, I show the traces and why this is happening. And you can, if you have time, you can see why, why this is all the errors which are happening and why the jitter and all. And what's the 519, how the 519, 518 plus changed the soft IRQ path. And why the timer delay. And I have patch link, if you have time, you can look, but later anyway, I will post to the kernel mailing list once it's really baked in fully.
Srinivas, I tried to download your slides, but it didn't work. Maybe you can delete them and re-upload them or something on the website.
Okay.
Yeah.
Okay, I can do that. Yeah.
I don't know. Does it work?
It worked for me.
It worked for them. Never mind. So it's working now. Thank you.
Maybe so. Okay, that's all I have. So if you have questions, or you can always send me a message or email. Anything is fine.
All right. Thank you, Srinivas.
You're welcome.
It was interesting. Good topic. Okay, so we have two more topics. The two lightning ones, like 10 minutes each. Both are both have remote presenters. The first presenter will be Ray from AMD. Ray.
Yes, I'm here.
Oh yeah, you are here. Okay, cool.
Okay.
So either I'll try to make you a presenter. If I
looks I cannot share my screen. Okay, yeah, it's okay.
Yeah, you are a presenter now. You should be able to control the session.
Thanks.
So, okay, you have the floor.
Yes. Do you need? Do I need to upload my slide
You don't
deck?
have. You use the actions. The actions button on the left down left side corner on the screen. Oh yeah, there you go. Okay, 10 minutes.
Okay. So can I start?
Yeah.
Okay. Thanks.
Yeah.
And so okay. And hello everyone and good afternoon. My name is Rui Huang from AMD Linux team and focus on the Linux kernel enabling work on the CPU power management and the GPU kernel DRM graphics compute support for many years. And this is my first time to present discussion in the Linux Primal conference. So it's my great honor to have the opportunity to discuss with all of you about fine-grained frequency control with the kernel governor. And the main discussion module is the new MDP state driver that we are upstream earlier of this year. We are using a fine-grained frequency control mechanism instead of traditional several P states. This is a new policy in our AMD processor platforms. And we found, and we also found quite a few problems with the new policy. And we have some additional, we also have some additional hardware level functionalities which need to find a good way to support it in the Linux kernel as well. So so I would like to raise the discussion and and the question here in the Linux Palmo conference for talk. So thank you so much for any suggestions and comments. Okay, move to the background. In Lexi processors, which we will support ACPI standardized, it will provide several P states such as the P0, P1, P2, and both state to the OS kernel for the frequency management, and according to the system workload in the traditional CPU processors. And look at this picture. We map 3 P states inside of this range, but these 3 P state P0, P1, P2, and also have the both state, but they are not fine-grained. But in recent AMD CPU processors, we support collaborative the processor power control. We call it CPPC. It is follow the ACPI standardized, and we also to customize some AMD specific functionalities as well. We have 4 performance values such as the highest perf, nominal perf, and lowest nonlinear perf, and the lowest perf. So we map the highest perf as the boost frequency, and the nominal perf as the P0, and the lowest nonlinear perf as the P2, and the lowest performance as a minimal frequency in the system. And this is the comparing with the ACPI CPU Freak and the MD state module, MDP state module. And the ACPI CPU Freak is using the 3P state, which emulate it in the PSS object in the ACPI table as system BIOS. So please look at this table down here. And the PSS object will have the frequency and the register entries for the ACPI CPU Freak driver. And recent in recent some Zen 2 and Zen 3 processors, some of the Zen 2 and Zen 3 processors, we will support CPPC and for MTP state driver. And there were 2 types of hardware implementations. One is the full MSR solutions. Another is a shared memory solution. Full MSR solutions provides architected MSR set of CPPC level registers to measure the performance hints, which is the fast way to control the frequency updates. However, in shared memory solutions, is that CPU only support a mailbox model for CPPC register in the system memory. We have to map the system memory, which share with the CPPC, and use the kernel RCU logs to measure the synchronizations with the way in the kernel ACPI CPPC libraries. Okay, MDP state is a fine-grained processor, fine-grained performance control with the CPPC plus kernel governors. Processors provide CPPC performance capabilities and controls in the kernel driver, and MDP state as a CPU Freak driver, is a new CPU Freak driver, is able to control these interfaces with the kernel governors, such as the scheduled hill, on demand, and something else, and so on. The initial driver is developed on the 4 MSR processors that we can get better performance per watt scaling in some of CPU benchmarks. However, we still face some performance drop, which compare with the Lexi ACPI CPU Freak driver in the shared memory solution processors. So we still use the parameter and not enabled shared memory processor by default at this moment. The traditional kernel governors, such as the on-demand scheduled queue, and might not fall suitable for the fine-grained frequency control in our platforms. So because there were about 166.
Right. You are still showing the title slide of your presentation. Is it intentional or is it?
Sorry.
Or is something not functioning?
Oh, okay. So is that a share my screen? Okay, I'm sorry.
Yeah.
I remember I just share my screen.
Also, you have 2 more minutes for this topic, like maybe 3. So.
Yeah. Okay. I can go quick. Can you see the screen?
Yep.
Okay. Okay. And there was 155 255 performance states in the MDP state. Let's compare with only 3 ACPIP state, and CPU and the CPU CFS scheduler governor might not face more frequency performance change in the MDP state. There is another reason. That's the Lexi ACPI P state control in the PSS object is actually the MSR register, which is faster than the shared memory with the in the CPPC. So that's probably a reason which at this moment the the MDP state driver is still as good as the ACPI ACPI CPU freak driver in the shared memory processors. So we are trying to seeking and enhance and optimize the kernel to implement the shared memory support processors here. So that's the first question for discussion. And another is we will introduce the energy performance reference, and in further, so we will support the energy performance reference to provide a hint to hardware if the driver want to bias towards the performance or energy the efficiency. But this feature is in once this feature is enabled, the design perf will inactive anymore. And currently we will provide 4 OS profiles with the different EPP hints, which they can control by user space manually and do the hardware-based dynamic frequency management in the hardware side. But we would like to find a way to manage the max, minimal, and EPP hint with the kernel governors. So the current kernel doesn't have the way to manage the max and the minimal perf so far. Yeah, that's the question.
So they are controlled by user space via SSFS, right? That's why.
Yeah. Yes, right.
Okay. So we have exhausted the time slot, so I suggest moving this discussion to the mailing list. And also, I saw that you have you have posted the patch set for EPP control interface, right? To the mailing list, so we can continue the discussion there if needed. So because we have one more topic that I would like to mention, and we have 5 minutes left, so let's just move over to there to the offline discussion. Okay.
Yeah. Okay. And okay. Let's quick finish the last page. 1 minute. Or just to switch. Okay.
Yeah.
Okay. Thanks. And
let's synchronize on the mailing list, because we also have preferred cores on Intel processors, and we already support them. So it will be good to get to synchronize on this too.
Yeah,
okay.
That's what I was about to say.
Yeah. All right. So thank you very much.
Okay.
And as I said, we have one more topic, which I'm going to speak to because we have 5 minutes, and then it's a very simple one. Let me see. That would be suspend, right? Yeah. I'm just so okay. I will speak to this one because I don't want to. I want to do it really quick. So the problem there is that when you suspend the system as a whole, drivers can have veto power on it. Essentially, in driver, if a driver returns an error from its suspend callback, the whole thing gets canceled, rolled back, and it doesn't suspend. And that's problematic if you have a laptop and you close the lid, and if one driver does this, then you think that the laptop has been suspended, which in fact it is not. And now, the hell breaks loose, essentially. And now the question is what to do about that. So there are drivers that do it every time. Like when there is something wrong, quote unquote, in one transition, they will return an error every time after that. And that's very unuseful. And now, the whole problem is based on, what to do about that behavior. Should we ignore the errors from drivers in the suspend path, or should we not? Or what to do? I have to say I don't really have an answer. It's just a topic for discussion, so that's why I reserved 5 minutes for it, just to state the problem and then leave it for discussion going forward.
So I think the question to be answered is, say the user has asked to suspend the system, and now the fight is between the driver, a device. Is there a case where a device should ever override what the user asked for? If the answer is yes, it should have that power, and the answer is no, it should not have that power.
Yeah, right.
I don't know if there's a correct answer for this, but I think that something that I miss in terms of hardware enablement is with S3, you had a big hammer to tell the sleep to go away. And it'd be nice to have that back. And it's be nice to have some way to deal with hardware not coming back when you resume. But I think that, yeah, in terms of having a way to override a device at the system level so you can not have, a system burning in your bag would be really nice.
Right. So, Kevin.
So, I guess the question here is, what does broken mean? I mean, if it's broken, it suggests that it needs some quirks and that the system should override this and suspend anyway. But I mean, if it's broken, it means we can detect that it's broken.
Yeah, well, so that the problem is that when error is returned, we don't really know if anything is broken at all, or just the driver decided to return an error because it thought it would be a good idea to actually terminate the suspend transition. We have no idea what happened.
So the common example we get is a networking driver that actually failed to resume, and the subsequent suspend, it goes, oh man, I failed to resume, and I tried to reset my device, and I'm broken. So it returns an error. It's like, well, it wasn't even working in the first place.
Yeah, this is just one example, but there are more, and the behavior is similar. So they say try to write to a register, and it doesn't respond. What to do? Well, return an error. That's easy. Well, normally it would be easy.
Reset device fails.
Yeah, but in this particular case, it just messes up with the whole, system power management, and that is not good, right? So again, there is a question for discussion. Like, what do we do anything about it? Like, if we do something, then what to do, and so on. Oh, really trying to to get my attention. Yeah. So yeah, that's it. Because we have reached the end of our time slot for the micro conference. So with that, thanks a lot everyone for showing up, and thanks a lot to the speakers. Yeah, and thanks a lot to the sponsors again. And
thank you to the volunteers, Raphael. Thank you very much.
Yeah, thank you, and to everybody who helped to to have this conversation, which was very useful, I think. So thanks a lot, and see you next year, if possible.
Thank you.